Welcome. In this section, I will teach you something really practical. I'm going to teach you how to design a proportional and a proportional derivative and integral controller, otherwise known as a PID controller. And I'm going to do it from a calculus point of view. So let's get started. First of all, what is a controller? I'm going to use a water tank example to explain it to you. So let's imagine that we have a water tank here that can contain a maximum of 100 cubic meters of water inside it. However, right now, at this moment, you only have 50 cubic meters of water. So the blue one is water, and it's the reality. It's how much water there is now. And now, we're going to put a red line here, and we're going to call it a reference line. So it's like a target. It's how much water you want. So the blue one is how much water you have right now, and the red one is how much you want to have. It's a reference line. And now, you can calculate an error, which is reference minus volume. In other words, how much water you want minus how much you have right now. And right now, it's equal, right? So you want 50 cubic meters of water, and you have 50 cubic meters of water. So your error is 0 cubic meters. However, now at this moment, you have 50 cubic meters of water, but you only want 20 cubic meters of water. So this is your new target. This is your new reference line. So this is how much you want now, but you have 50 cubic meters of water. You calculate the error, which is reference minus current volume, and your error is negative. It's minus 30 cubic meters. So what needs to happen now? Water needs to get sucked out of the tank. You need to get rid of some of the water in order to meet your target of 20 cubic meters. So what happens now is that this water tank has a sensor. And this sensor measures the volume of water every 0.02 seconds or at 50 Hertz. Now you can get this frequency by dividing 1 by 0.02 seconds. In other words, what that means is that the sensor measures the volume of water 50 times a second. So in 1 second, it takes 50 samples of the level of water, and so what happens next is that the pump starts taking water out of the tank. So the amount of water in the tank decreases and decreases and decreases until it reaches the target, the reference line. And now the amount of water that you have equals how much you want to have. So your error term is 0 cubic meters. Now, for some reason, now you want to have 80 cubic meters of water in your tank, but you only have 20 cubic meters. So if you calculate the error, you have a positive 60 cubic meter error. Now again, you have the sensor that measures the volume of water at 50 Hertz, and now the pump starts pumping water inside the tank. And so the level of water increases and increases and increases until it reaches 80 cubic meters. And now you have 80 cubic meters of water, and you want to have 80 cubic meters of water. So your error term is 0 cubic meters. Now, if we start generalizing it, if we think about our water tank, what is it exactly? Well, it's a system. We can say that our water tank is a system, and you can have all kinds of systems. An airplane can be a system. A rocket can be a system. Some kind of heating device can be a system. So whatever you can imagine or whatever you're working with can be a system. So right now we are working with a water tank. So we say that our water tank is our system, and that system has an output. And it has an input. So what is exactly an output? An output of a system is something that we can observe, something that we can measure. and it has to be relevant. So let's say we could also measure how many molecules of water we have in the water tank, right? But we wouldn't do that because it's not relevant for our situation. For us, the relevant value is the volume. It's how many cubic meters of water we have in the tank, not how many molecules of water we have in the tank. So an output is something that we can observe, something that we measure, typically with sensors. And the input into our system is a mass flow rate. Its unit is kilograms per second. So it's how many kilograms of water flows into our tank per second. And if we think about the input, then the input is some kind of action that causes output to change. So let's say if we increase our input, if we increase our mass flow rate, we have more kilograms of water flowing into our tank per second. Then that influences our output, right? Then our volume increases. And if this mass flow rate is negative, if it's not positive, if it's negative, if it's a negative value, if it's, let's say, minus 50 kilograms per second, then it causes volume to decrease, right? So the input, depending on what we put here, it influences our output. So a positive mass flow rate would increase the volume of water, and negative mass flow rate would decrease it. And now, let's see where a controller fits in all of this. This is our system. This is our water tank system, right? And it has an input, which is a mass flow rate, how many kilograms of water per second flows into the tank. And then on the other side, we are measuring the output with a sensor. We're measuring the volume of water, a relevant output. So remember, we are only interested in relevant outputs, relevant measurements. So now we need to decide how to best influence our input, in our case, our mass flow rate, in order to achieve our desired output. And the controller is nothing but a brain that decides how to best influence our system input in order to achieve our desired output. So for example, if we want to achieve our desired output very fast, then the controller might decide that, okay, let's put a lot of mass flow rate in here. Or if we want to achieve the desired volume in a slow way, then the controller would say that, okay, let's not put so much mass flow rate in here. Let's just put a little bit so that the level of water would increase, but slowly. So the way it works is that this is your output volume, right? And your volume goes here, and here this is your reference. Like this is the red line, right? This is how much volume of water you want. And this is how much you have. And so here you have a plus sign here and you have a negative sign here. So reference minus volume will give you an error. So a controller will take in an error term, which is reference minus volume. It will take in the error term. And so for the controller, the input is the error term. And then the output for the controller output would be actually the system input. It would be the mass flow rate. And also the system input, since it's controlled input by the controller, right? Then we also call it a controlled input or a controlled action. So the controller decides how to best influence the mass flow rate in order to achieve your desired volume. And it does so by trying to drive the error term to zero. So you want the error to become zero because then your reference equals your volume. And a very simple controller would look something like this in a mathematical way. Let's say if your error is less than 0, then let your mass flow rate be minus 10 kilograms per second, right? It makes sense that if your error is negative, then that means that your reference is less than your volume. So you want your water to go down. So your mass flow rate should be negative. Then that means that water gets out of the tank and the amount of water in the tank decreases. If your error is 0, then the controller says apply 0 kilograms per second. And if your error is bigger than 0, then apply 10 kilograms per second. So now you want the level of water in the tank to increase. So you apply a positive mass flow rate, and so this is a mathematical form for it. It's a piecewise defined function. However, in a code, it could be like an if statement. If the error is less than 0, then let mass flow rate be minus 10 kilograms per second. Else if error is bigger than 0, the mass flow rate equals 10 kilograms per second. Else, a mass flow rate equals 0 kilograms per second. So that could be a case when you want the level of water in the water tank to increase or decrease slowly. But if you want it to happen faster, then the controller could be something like this. The same logic, but instead of 10 kilograms per second, you would have 100 kilograms per second here. Minus 100 here and 100 here. So, in a way, nowadays a controller mostly is a computer algorithm. It's some kind of algorithm that decides based on the error that it gets. It decides how to best manipulate the controlled input, the control system input, to achieve a certain behavior of your output, right? But does it always have to be a computer algorithm? Well, no. You could be a controller. You could be sitting somewhere and you could be looking at this water tank and your eyes could be like a sensor, and then your eyes look at how much water you have in the tank. You know in your brain how much you want. In your brain you calculate the error term, and then you are the one who turns the pump on or off with your hands, which are your actuators. So you could be a controller as well. However, nowadays, in most modern systems, a controller is a computer algorithm. So you can think of it as a brain. It's a computer algorithm designed so that you could achieve your desired output by tweaking and playing around with the system input. And finally, I want to explain to you the difference between an open loop system and a closed loop system. So what's the difference? The difference is that when you have an open loop system, then you only have this part, right? You have your system, and then you have your input, and you have your output, but in an open loop system, you don't have controllers. You don't have any feedback. So, in other words, there is no sensor that will take the measurement of the volume and then compare it with a reference, and then a controller that takes the error in to decide how to tweak the input in order to influence the output. So all that doesn't exist in an open loop system. It all exists in a closed loop system. So a closed loop system is what we have been discussing so far. It's everything. It's everything that you can see here. But an open loop system just has a system and some kind of input and some kind of output. And now it's very important to understand that in an open loop system, since there is no controller that controls the input, that changes the input based on the output, since there is no controller, then in an open loop system, the system input is pre-planned. before you turn your system on, in this case a pump, before you turn your pump on, you pre-plan the behavior of your input, the behavior of your mass flow rate. So what do I mean by that? I mean that if I turn my system on, then I say that as a function of time, my input will behave like I intended to. So this is a time axis here, and this is a mass flow rate. So this mass flow rate, it's this input here. And here it's constant as a function of time. So let's say it's always 10 kilograms per second, right? It never changes. And if it's an open loop system, if it's only this part, then since there is no controller, then this entire thing it's pre-planned, okay? So it will always be 10 kilograms per second, and it will never change because it can't, because it doesn't get any feedback from the output. It doesn't know whether it should change the input in order to influence the output somehow. So it's pre-planned, or you can pre-plan it in such a way that as a function of time, your mass flow rate increases linearly. Or it can be simply like that. So you can also have this kind of mass flow rate function, but the important thing to understand is that it's pre-planned and it doesn't change. So before you turn your system on, you plan your system input. You say that as a function of time, it's gonna be like that. So maybe at the beginning, it's gonna be 10 kilograms per second, and then let's say at 5 seconds, it will be 15 kilograms per second, and then at 10 seconds, it's gonna be 20 kilograms per second, but it's pre-planned. And during the operation of the system, while the water tank is operational, during that time, the system input does not change, okay? Now here, this is a comparison of an open loop system versus a closed loop system. So in an open loop system, the input is pre-planned. It never changes. But let's say in a closed loop system, since you get feedback from your sensor, and then your controller, based on that error, will change your input in an unexpected way. So in this case, in a closed loop system scenario, your mass flow rate might change in an unexpected way. Okay? So that's the difference. So in an open loop system, you pre-plan your input and it stays like that. It doesn't change. It will behave like you had planned it before, but in a closed loop system, it changes based on the need. So for example, just as a simple example, you want to go from 50 cube meters to 80 cube meters, right? And you think that you're going to achieve that by applying this kind of system input as a function of time. So you apply this kind of mass flow rate as a function of time. So first you give less mass flow rate and then you increase it. And then you think that you're going to go from 50 to 80 cube meters in your water tank. But then what happens is that there is a leak in the water tank and you're not aware of that. You don't know that. So that means that if there is a leak, then in a given time frame, you're not going to go from 50 to 80 cube meters. You're going to go maybe from 50 to 75 cube meters, right? Because there is a water leak. And because of that, some of the water gets lost. And since there is no feedback, you don't know about this. But if you have a closed loop system, then the sensor will notice that, okay, the error is bigger than expected. So the water level is not rising as fast as expected. So the controller will increase the system input, and that's why if you have something that you have not accounted for, then you need a closed loop system for that. Because then the controller will make unexpected adjustments, and maybe because of the leak in the water tank, it will increase the amount of mass flow rate to compensate for the water that you lose because of that leak. Alright, thank you very much, and I'll see you in the next video. Okay, here I want to show you a water tank example, and here I'm employing this controller, the control that we talked about, so that your mass flow rate is minus 10 kilograms per second when your error is less than 0, and when your error is bigger than 0, then your mass flow rate is plus 10 kilograms per second. And when your error is 0, then your mass flow rate is 0 kilograms per second. And you can see that, okay, the controller works. It is following the reference line, but it's too slow, right? So if you look at this timeline here, it's 5,000 seconds. So that's around a little bit less than 1.5 hours. And let's say that you need this tank to fill in quickly, and then you need to empty the tank quickly as well, but the controller is not able to meet the target within the given time frame. So it is following the reference line, but it is not able to meet the required targets in the given time frame. So let's see if we're gonna implement that other controller that we talked about. So instead of minus 10 and 10 kilograms per second, maybe if we increase our mass flow rates to minus 100 and 100 kilograms per second, maybe then we will be fine. So let's see. So now the mass flow rates are minus 100 and 100 kilograms per second, depending on the error. And you can see that now the controller is able to control the level of water in the water tank within the given time frame. So that's very good. And you can see a little bit of wiggling here, right? That's because when the water level reaches the reference line, then, you know, at some point it's a little bit above the reference line, a little bit below the reference line, and that's why the controller switches the mass flow rate from negative to positive, and that's why you see this kind of wiggling behavior. But overall, now the mass flow rate is capable of achieving its targets. So what it is doing, it's very simply either pumping more water inside the tank per second, or it's taking more water out of the tank per second. So that's how these two controllers work. Welcome back. So now what I want to do, I want to explain to you what a proportional controller is. So you already know that a controller takes in an error term and it gives you a mass flow rate in our example. So an output for the controller is an input into your system, and your system was a water tank system. And so based on the error that the controller receives, it will give you a mass flow rate so that you would achieve your desired volume in the water tank. And you will achieve your desired volume in your water tank when your error becomes 0. Now there are many different controllers, and one of the controllers is a proportional controller. And essentially a proportional controller is a gain. So your error term is multiplied by a gain, and then you simply say that your mass flow rate equals that gain times your error. So from this you can see that your mass flow rate, right, your system input is proportional to the error. So maybe it's even better to see it in this graph. So your mass flow rate, your system input, it's proportional to the error. So the bigger your error, the bigger your system input, right? The bigger your mass flow rate. And also if your error is negative, then your mass flow rate is also negative. So your m dot is proportional to your error. So essentially this gain that we talked about, this gain is a slope for this function. And by choosing Kp, you choose the slope for this line. Now, this Kp, it has the units of kilograms over seconds times m cubed, and that is because the slope, the Kp, is nothing else but delta m dot over delta error. And if you look at their units, then you will get your units for the Kp. And so when you choose your gain, then for example, if you choose a very large gain, then this function would be something like this with a big slope. That means that if the error increases or changes a little bit, then you will have great changes in your system input. However, if you give your controller a small gain, then your function would look something like this, and that means that if there is some kind of change in your error, then your mass flow rate won't change that much. So that's what you're doing when you choose your Kp, when you choose your gain for your controller. You're choosing a slope for your function, right? You're choosing how your mass flow rate is proportional to your error, whether it's proportional in a strong way or it's proportional in a weak way. So let me just show you very quickly how a proportional controller would influence your water tank. So you can see that now the response is different. It's not linear. So at the beginning, right, when the error is great, then also the mass flow rate is huge. But then as you get closer and closer to your reference line, your error becomes smaller. And because your mass flow rate is proportional to your error, when you have a small error, you also have a small mass flow rate. And then when you have a huge error, then obviously you have a huge mass flow rate. So that's why you can see this kind of response. So at the beginning, you have a huge slope, and then you have a smaller and smaller slope. To design a good controller that works well in real life, it is important to simulate it in the computer first. In real life, you measure, for example, with sensors, the output, and based on that, your controller decides how to change your control input. And in our case, that input is a mass flow rate. In a simulation, however, you need to calculate the output from your input. So since our input is a mass flow rate and our output is volume of water, then you need to calculate your volume from your mass flow rate. So you need to have some kind of mathematical model that takes in your input variable, a mass flow rate, and then you compute your output variable, volume. Now, one thing that you need to take into account always is that real life will always have a different output compared to what your models give you, because your models, they will never take into account everything in the world. However, if the difference between your model and real life is small enough and you're happy with it, then you can use it. And so now what we are going to do, we're going to create a mathematical model for our system, the water tank, and then we're going to take our proportional controller and we're going to apply it to our system, to our mathematical model of our system, and then we can simulate the entire closed loop behavior. So now what we're going to do, we're going to create a mathematical model for your system, which is a water tank. In order to create a mathematical system, what we need to do, we need to find a mathematical model that takes your system input, a mass flow rate, and from your mass flow rate and other parameters, that mathematical model will be able to to calculate your system output, your volume in the water tank. So we need to have some kind of mathematical equation that takes in your mass flow rate, and then what you get out is your volume. So how would we do that? Well, first of all, let's think about what a mass flow rate is. So in your water tank, you have water, so you have some kind of mass, right? You have a certain amount of water, so you have a certain amount of kilograms of water in the water tank. And your mass flow rate is just a derivative of the mass of your water with respect to time, right? And that's why it's in kilograms per second. So it's d mass water with respect to time, so dt. So the operator is d over dt, and then you apply it to your water mass in the water tank, and you get your mass flow rate, right? Now, next, the mass of your water can be expressed the volume of your water, cube meters, times the density of water, kilogram per cube meters, right? Or using another notation, you can notate density as rho, but the mass of your water is the volume of your water times the density of your water. Now, knowing that, instead of the mass of your water, you can put here volume of your water times the density of your water, right? And now you take this with respect to time. You take the derivative of this product with respect to time. And when you do that, then the product rule, when you take the derivative, will look like this. So first of all, you take the derivative of your volume with respect to time, and you multiply it by the density of the water, and then you take the derivative of the density of your water with respect to time, and you multiply it by volume. Now, since we only have water in our water tank, no other liquid, then the density of your liquid inside the water tank is constant, right? And so if we take a derivative of it with respect to time, this entire term becomes zero because the derivative is zero. So you are only left with this part here. So a mass flow rate, assuming that we only have water, which is our only liquid, our mass flow rate is the change of volume of water with respect to time times the density of water, right? So that's your mass flow rate. Next, we can rearrange the equation. We can put rho on the other side of the equation, and then it would look something like this. The derivative of your volume with respect to time equals 1 over your water density times your mass flow rate, right? So that's your equation. So what do we have now? We have a function where we have a time axis here, and then we have the derivative of the volume with respect to time here. So this is cube meters per second, right? It's the change of volume with respect to time. It's how much volume changes in the water tank with respect to time. And so you have a function of it, and this function is this one. In the mathematical term, it looks like this. So what would we have to do in order to get rid of the derivative sign and just get volume as a function of mass flow rate? Because remember, our objective at the beginning was to get this, our system output, our volume, as a function of our system input, right? So not the derivative of this with respect to time, but the actual volume with respect to your system input. That's our goal. So in order to get that, we have to get rid of these d's, right? So we have to take an antiderivative, which is an integral. Now, one thing that I want to show you here is that, you see, one way how to mathematically notate when something is constant is when the derivative of that thing with respect to time is 0, right? Because if, for example, d rho with respect to dt equals 0, that means that the density does not change. And so then you can say that the density of the liquid is constant because its derivative equals 0, because the derivative means change. So if the derivative is 0, then the quantity doesn't change, so the quantity must be constant. And the mass flow rate here is not constant, and sorry about this one, I cannot do anything about it. However, if you look at the mass flow rate, then the mass flow rate is not constant. And mathematically, it means like this. So the mass flow rate with respect to time does not equal to 0. In this case, then it means that the quantity is not constant. Because if it's not equal to 0, then that means that it is changing. And the mass flow rate does change with respect to time, so it's not constant. And mathematically, you would notate it like this. So when you see something like this, and the derivative is 0, then it's constant. And when a quantity, its derivative with respect to time is not 0, then it's not constant. But now, let's continue with this part. Now, our mass flow rate is a function of time by itself, right? So what we have to do, we have to take the integral of this function, and then we will get rid of the derivative, and then we will only have the volume of water as a function of a mass flow rate, which is exactly what we want for our mathematical model. So the way it would look like is this. Since you have dt here, you can put this dt on the other side here, right? And then you would only be left with d volume equals 1 over rho times m dot times dt. And that's what I've done here. So d volume equals all this. And so the first thing that you see is that I put this 1 over rho out of the integral. Why? Because it's constant, right? The mass flow rate is not constant, it's a function of time. So that's why it has to stay inside the integral. And then I multiply it with dt. However, 1 over rho is constant, so it can be out of the integral. And then you take the integral on this side from 0 seconds to t seconds, and t is an open variable, right? And now on the other side you have d vol. So you have the water volume here, the d water volume, like a small change of water volume, and you integrate that from the initial volume to some kind of open variable volume. So this one will be a fixed number, it's your initial condition. And then this one will be then your output variable that will depend on time. So when you perform this integration, you will have something like this. You have volume as a function of time minus your initial volume. Alright? And that equals 1 over water density, integral from 0 to time, mass flow rate times dt. And then you can put the initial volume of water, it's how much water you have at the beginning, you put it on the other side, and then that's how you can express your water volume as a function of time in this form. Right now we still have this integral form here. However, here you don't have an integral anymore. Here you can just say the water volume as a function of time equals an initial volume. It's a specific number, your initial condition, how much water you have at the beginning, plus, and then this term. Now, the question now becomes, how are we going to get rid of this integral? That's the question. The thing is that if we knew how the mass flow rate depends on time, if we had some kind of concrete function, if we knew exactly how mass flow rate changes as a function of time, then it would be easy, right? Especially if the function is easy. If it's a parabolic function or a straight line function, it's easy. Now, the problem is that we don't know how this mass flow rate changes with respect to time. Well, first of all, we don't know it because we don't know how the controller is going to influence this term, this variable, this mass flow rate, right? And the second thing is that sometimes you can even have functions that are so complicated that it is very hard or even impossible to integrate them analytically. And in that case, and in our case, when we simply don't know how mass flow rate will change, in that case we have to do something called numerical integration. Now, what is a numerical integration? Numerical integration is essentially integrating something, but in a discrete way. Integration can be seen as calculating the area under the function. Now, if you have some kind of function that is explicit and you know the function and it is not hard to integrate, then you can just integrate it analytically. But you can also approximate the integral, right? And so the way you do it, you calculate the area under the curve in an approximate way. And there are all kinds of different ways you can do that, and some of them are more precise, some of them are less precise. The easiest, or one of the easiest numerical integration techniques is called a trapezoidal rule. And the way it works is that if you look at these shapes here, what do you have here? You have trapezoids, right? You have a trapezoid here, you have a trapezoid here, and then you have a trapezoid here. And so if you want to calculate the area of this trapezoid, then what do? You have A0, which is here, plus A1, which is here. You divide it by 2, and then you multiply it by delta t, and delta t is this interval here, which is 0.02 seconds. All right? And then you can get the area of this trapezoid, which is approximately the area under this function curve. And then you can calculate another trapezoid, which is this one, A1 plus A2 divided by 2 times delta t. Then you will know the area of this trapezoid. The same thing you can do with this trapezoid. And so when you add up all these trapezoid areas, then what you will get this term here, all right? So this is the term that you will get when you add up all these trapezoids. And then this initial volume here is the same thing like here. These are the same terms. So when I tell you that let's integrate something analytically, it means you use those calculus rules. However, it's not always possible. Either you don't know the function, or the function is very hard to integrate, or even impossible to integrate. And then you have to integrate it numerically. And that's actually how computers do it. So what computers do, they start from time equals 0 seconds, and then after a small period of time, they calculate the area under the curve. Then a little bit later, they calculate another area under the curve, another part, and then another part, and then they add them together. That's how computers do it, and that's how engineers do it with complicated functions, or let's say when they don't know the function of the mass flow rate. Because let's say if you don't know it, if you don't know how it's going to change, then when you're at this point at time equals 0.02 seconds, then let's say only at time equals 0.04 seconds you know that the mass flow rate changed and then your function went from here to here. So when you were here at time equals 0 seconds, you didn't know that you would end up here. But when you're at time equals 0.04 seconds, then you know that you are here, and so your computer can then calculate this part and add them together. So it's like looking back into the past. Okay, so that's how we would do it. We would use the numerical integration to compute this term here, and then we would add the initial volume term here, and then that's how we would get our water volume as a function of time. Now, one thing that I want to show you now is this. If you look at this term, the initial volume plus the first trapezoid, right? Then what do you get? You will get the volume of water at time equals T1. So here, it makes sense, right? You take your initial volume, you add the first trapezoid, and then you have volume at T equals 1. Now, if you add another trapezoid to it, then you will have volume at time equals T2. So this one, right? And then this entire thing here, all these four terms, 1, 2, 3, and 4, if you add them all together, you will have the volume of water at time equals T3, right? So the other way you can write this entire thing is like this. For example, you can say that volume at T equals 3 equals volume at T equals 2, which is this one, plus A2 plus A3 divided by 2 multiplied by delta T. Instead of writing this, you just write volume at time equals T2 plus and then the last term, right? And you can generalize it, and in fact it's a generalized algorithm that you can program into your computer. So if you look at it, then it's volume at time j, right? And j can be whatever number, so it's generalized variable. It can be either 1 or 2 or 3. So volume at time j equals volume at time j minus 1. J minus 1 means that if here you have 3, then here you have 3 minus 1 equals 2. So it's the same thing like here. Here volume at time equals 3, which is here, equals volume at time equals T2, which is here, which is j minus 1, plus 1 over rho times m dot at time j minus 1, plus 1 rho times m dot at time j, divided by 2 multiplied by delta t. So in other words, this A2 and the A3, it comes from here. These A's, right? It's this. So you have this function where you take a derivative of your volume with respect to time equals 1 over rho times mass flow rate. That means that the height of A3 and A2 and A1, they come from here, right? And therefore, when you have A2, then this A2 can be written in this way: 1 over density times mass flow rate, m dot, and then instead of j minus 1, you would have 2. And so A3 would be 1 over density, m dot, at T3. All right? So j in this case is 3. So if you compare this equation with this one, this is a generalized version of it. So instead of 3, you can have j. So that means that j minus 1 equals 2. And so you can put this algorithm into your code, and then what's going to happen is that this algorithm, it will be updating itself all the time. So first of all, you will calculate volume at T1 using volume at T0, and then the mass flow rate at T0 and the mass flow rate at T1. So using all this information, you will calculate volume at T1. Then 0.02 seconds later, you will calculate volume at T2 using information from volume at T1 at m dot T1 and m dot T2. This j can go up to 100, 1000, 10,000, depending on how many iterations you have in your loop. And so here you have it again. It's just to make it clearer. So volume at T1, at T2, and at T3 using the information from the past, from 0.02 seconds ago. And so now, this is our entire closed loop system with our water tank system and our controller. And so our goal was to find a mathematical model for our water tank where we take in the mass flow rate and we get our volume, and we've done it. So this is our water tank here. Only now we are describing our system in a mathematical way. And in fact, there are two ways in mathematics how we can describe it. We can describe it using continuous mathematics or discrete mathematics. And as far as computers are concerned, the computers, they of course operate in a discrete manner. So when you code, then you would actually use these discrete formulas to write your code. So in a continuous way, mathematical model for your water tank looks like this. Volume as a function of time equals your initial volume, and then 1 over density times the integral of the mass flow rate, which itself is a function of time, and you multiply it by dt. Now, since you don't know in advance how this mass flow rate is going to change, then we derived a discrete version of it. And this discrete version, right, this is a discrete mathematical model for our system. And this one can be implemented in a computer program. For example, inside a for loop or while loop. And so this is your discrete mathematical model of your water tank. And here is your output. Again, in red, it's the discrete version. In black, it's the continuous version. It's a notation. I want to show you how you can notate things using continuous mathematics and discrete mathematics. And so this is your output. This output goes here. You have your reference volume. It's what you want, the continuous version, and then the discrete version. Then you have your error term, which is here, continuous and discrete. And then that goes into your controller, into your proportional controller. And with that, you're going to calculate your new mass flow rate. So a continuous version is here, and then the discrete version is here. And the way you calculate it is, because it's a proportional controller, it's very easy. You just take your error term and you multiply it by this gain, Kp, which is a slope of a function. Now I put here this red line just to give you like a sense of what's really happening here. What I want you to understand is that it's a continuous loop that goes around all the time, right? So this loop it gets updated, in our case, at 50 Hertz, or every 0.02 seconds. So every 0.02 seconds, the information here gets updated, this mass flow rate gets updated, and then the volume of water gets updated using the information 0.02 seconds ago. So the way to look at it is like this, that, okay, let's assume that on this side of this line, the variables are a little bit in the past. They are 0.02 seconds ago. And on this side of the line is the present. So here you have J, and here you have J minus 1. So here you have the volume reference, 0.02 seconds ago, and here is your actual volume of water inside the tank 0.02 seconds ago. Alright? So all that is 0.02 seconds ago. And so you calculate the error 0.02 seconds ago. So this is a little bit in the past. And then you go through the controller, and now you calculate your new mass flow rate, which is mass flow rate now. It's what you're gonna apply to the water tank, to your pump right now. So you've calculated your system input using the information from 0.02 seconds ago. So now you've calculated your new system input, your new mass flow rate, and you feed it into your water tank system, and then you get your water volume now. So this is now present. So it's important to know that this entire thing is a loop, and all these variables, they get updated in our example every 0.02 seconds. So what you have here in 0.02 seconds, they will be here. So what you have here in 0.02 seconds time, they will become the past, and they will be here, and then you will have a new value here. So that's how a closed loop system works. And so that's how the controller works. The controller takes in the information 0.02 seconds ago, and then it will calculate the new system input that will influence your water tank, and that water tank will give you a new output, which again you will feed back into the controller, and it all happens at 50 Hertz. And now I'm going to show you a couple of Python simulations where we're going to test this code, and we're going to give a certain reference values for the water tank, and those reference values, they're not going to be fixed. They themselves, they will be changing, and so the job of the controller is to track this reference line. So when the volume reference changes, then the actual volume in the water tank needs to change as well. And so you will see it in action in the next video. Thank you very much, and see you there. So what you're seeing here is a proportional controller with a KP value of 100. And you can see that it is going in the right direction. The volume changes in the right direction. However, the response is very slow. So it is able to track the reference line, but let's say the reference line changes faster than the volume inside the water tank, and that is because the KP value in the controller is too low, and because of that the controller tells the pump to apply some kind of mass flow rate, but that mass flow rate is just too low. That's why the response is not fast enough. Now the other thing that I want to show you is this. Look, when you're very far away from the reference line, then the volume here changes faster. And when you get closer to the reference line, then the volume changes slower, because it's a proportional controller. And so when your error is less, then your mass flow rate is less. And when your mass flow rate is less, then you have less changes of volume inside the water tank. And when your mass flow rate is greater, then you have bigger changes in your tank. So you can see it here as well. So now let's change our Kp value to 1000 and see if it's better. So here I've applied a controller with a Kp value of 1000, and now you can see that the response is much quicker because a greater Kp value in the controller now tells the pump to apply greater mass flow rate magnitudes, and because of greater mass flows, also the volume in the water tank changes faster, and so now it is able to track the reference line much better. And now we're going to switch to another system, and it's going to be a train on magnetic rails trying to catch objects that randomly fall from the sky. So what you're seeing here is a train, which is this blue platform, on the rails. And so these are the rails here. And we are assuming that it's a magnetic train, so it uses the magnetic forces. So essentially it a little bit floats in the air due to magnetic forces. Then we don't really have to worry about friction because it's almost non-existent. So it's easier to model our system mathematically. And the objective of that train is to catch randomly falling objects from the sky. And they are random both in height, the initial height is random, and also the horizontal position is random. And the train does not know from where those objects are gonna start falling before they appear. And only after that the error between them is calculated, and then the train tries to catch them. However, this train is not using the proportional controller. In fact, a proportional controller cannot be used here. If you used only a proportional controller here, then the train would not be able to catch these objects. You see, a proportional controller is a very limited controller, and it does not work for many systems. It worked for our water tank example. However, for many systems it does not work, and it does not work for this magnetic train system either. So we have to use a controller that is slightly more complicated, and we're going to use a PID controller. I'm going to teach you the logic of a PID controller, a proportional, integral, and derivative controller. And we're first going to start with the logic of it. I'm going to explain to you exactly why a proportional controller wouldn't work here, and also how a PID controller works. And then you can also download this code in this section. Alright? So thank you very much, and I'll see you in the next video where we are going to start with a PID controller. Welcome back. This is a quick follow-up video. First of all, I want to thank you for enrolling in my course. I'm very glad that I can be your teacher. I would like to point out that the simulation codes in this course for the PID section are at the end of the first section, the last lecture, and the codes for the MPC part are at the end of the MPC coding section, last lecture as well. Also, I want to thank you for all the reviews that I have received from you. However, to be honest with you, I would love to have more of them from you. It is very important to me to get your feedback, and it's also important for my future potential students so that they would know your opinion about this course. Your feedback is very valuable. Thank you very much, and let's continue with the course in the next video. Welcome back. So in this section, I'm going to teach you what a PID controller is, and I'm going to use it on an example, which is a magnetic train on the tracks. So this is the train, the blue block, And last time I showed you a video where that train was able to move diagonally like that. However, right now we're going to start from a simpler example. We're going to start from a case where the train can just go left and right. Alright? So let's talk about the situation, what's happening here. So you have the magnetic train, and like all objects on the planet, it has a gravitational force pulling it downwards. However, since there is no inclination, since the train can only move left and right, then this force of gravity doesn't influence the motion of the train. It would influence the motion of the train if we assumed friction. However, since it's a magnetic train, so in the end the train floats in the air a little bit due to magnetic forces, we assume that there is no friction, which makes our system easier. And so the train can move left and right, and then you have this object here, this cube, and this object, it can fall down from the sky randomly. So the random position can be a random horizontal position. So let's say one object starts from here, it falls down, and then next second another black object appears here or here, and it can also have a random height, so it can be here or here. And then the force of gravity is also applied on that object, and so that object will fall down. The objective of the train is then to do what? The train, what it does, it calculates the horizontal error. This is your x-axis, alright, your x dimension. And where your object is, this is where your reference x is. So let's say maybe if this is 0, maybe your XR is here. So maybe it's 5 meters. And then your train is at 15 meters, right? So what you do, you subtract x from XR. So this is your target. This is where you want to be, right? And this is where you currently are. And so if you perform this operation, XR minus X, what you get an error. And in this case, this error would be negative. And so we also assume that in this direction, the X is positive, and if you go up, then Y is positive. So if you go down, then Y is negative, and if you go left, then X is also negative. And so when the object falls, the task of the train is to move quickly and stop here and catch the object. So this is the height here, the position Y, and it changes as a function of time. So as the object falls, also the Y position changes. And one more thing that we need to know is that the magnetic train, in order to move, some kind of horizontal force needs to be applied to it. And so this horizontal force is this FA. So it stands for F applied. And so it's produced by magnets in the magnetic system here. And so if the object is here, this applied force is applied to the train, which makes the train move. And then the train will be here to catch the object. Now, if you have another situation where, for example, your object is here, right, and you are here, then it's exactly the same situation. The only difference is that now your error will be positive. Why? Because your XR, your target position, is here, and then your current position is here. So your target position is bigger than your current position. And so when this object appears in the sky and starts falling down, then an error, a horizontal error, is calculated by subtracting x from XR, and in this case you would have a positive error. And so the train would apply some kind of force by magnets, and it would move here to catch it. Now the question is, how much force you apply in order to be here on time? You know, because if you apply very little force, then you're not going to make it and the block will just fall through. But if you apply too much force, you will just overshoot, right? You will just go there. You go too much to the right, and then you will miss the block. And so that's what we're going to be now learning. And for this kind of task, a proportional controller is not quite enough, because you will see that it will cause an overshoot. A proportional controller will cause the train to just shoot through the target, and so you will simply miss your target in that case. But a PID controller will be able to manage the situation, so we're going to learn about that. So let's get started. So every time when you have some kind of control problem, and every time you want to design a controller for your problem, you first start with a physical setup. So here you have your train, and then here you have your block that is falling down. So you want to create this physical setup, because then you will understand better what's going on. And you can also put force vectors wherever you have them. So it's good to do it like this. However, in order to now design a controller and solve your control problem, it's then also good to put your problem in another form, in this kind of form. So this is not a physical setup, but it's a good setup for control problems. So first of all, what you do, you take your system, which is your train, and that train has some kind of input and it has some kind of output. Now remember, the system input is some kind of action that you can control, and it's produced by some kind of actuator or some kind of motor, right? And then you use that input in order to influence the output, and the output is something that you measure, for example, with sensors. So in this sense, in this case, we have our system, we have our train here, and what we're interested in measuring is our position. It's our horizontal position, our X position, right? So we measure the position. And so what we do then, we feed our position back and we compare it with target position. And then we calculate the error. And note that the units are the same for everything, right? So this is your current position, where your train is at right now. And this is your reference position. It's where you want your train to be and to stop, right? So it should also stop there. And so then you calculate the error, and then the error also has the same units. And so what you want to feed that error into your controller. And by the way, when I said that the train also needs to stop at XR, this is the reason why the proportional controller in our situation wouldn't work, because the proportional controller would take the train to the target position, but the train wouldn't stop there. And I'm gonna explain it to you more in a minute. But the point is that you calculate your horizontal error, your error in the X direction, and then you put it into your controller block. And right now it's like a black box, but we're going to uncover it. We're going to open the box, and we're going to see that you will have a PID controller there. So we're going to design a PID controller, and it's going to be instead of this box. And so this controller will then have an output which will then be fed into your system. So the output for the controller will be the input for the system. And so the input for the system would be then the force, which will be produced by magnets of the train. And so the controller will try to figure out the right amount of applied force in order to move this train to your target position. In other words, to make this error zero. And so in control problems, it's good to put the problems in this kind of block form. It's very common to do that. And now the question is, okay, so what's our mathematical model for our system? Because now what we have to do, we first have to model our system, not our controller, but our system. We have to model it mathematically. How do we go from applied force to position? Now, before we move forward, I just want to make it even more intuitive for you. See, this form that we have, right, it can be applied to many systems. So right now we have a train, but also when you have a water tank, then it's the same logic. You have some kind of input. In our case, it's a mass flow rate, which is created by a water pump. And then on the other side, it's our system output, something that we measure by sensors. With a magnetic train, the system input would be applied force created by magnets, and then our output is something that we measure. It's the position that we measure by sensors. It could also be a velocity. It's what we choose, okay? It's what we choose here and what we choose here. It's up to us to decide. You can also have an airplane system, and for example, you can also have a robot, right? And so in the case of a robot, then with sensors you measure its position in XY, for example, or in XYZ. But in order to go to these positions, first you need to apply some kind of torque to its joint motors, right? And so in this case, the torque created by joint motors would be the system input, and then the position would be the output, something that you measure. So this kind of logic can be applied to a lot of systems, and it's very common to do that in control engineering. But okay, let's now continue with creating a mathematical model for our system. So remember, our system now is this magnetic train. Our system input is applied force, and our output is our position in the x direction. So now our goal is to derive some kind of model, a mathematical model for this train, so that when you put your applied force into the model, it will somehow give you the position. And you need that in order to simulate your system in the computer so that you could accurately design your controller. Okay, so let's start. What could be our applied force? So what is a force exactly? Well, if you have a momentum is mass of a body times the velocity of a body. So that's a momentum. The second law of Newton says that force is the derivative of the momentum, or the change of momentum, with respect to time. Now you've heard that it might be the mass times acceleration, but mass times acceleration is only in special cases. It's when your mass doesn't change, when it's constant. The most general rule is the change of momentum with respect to time. And so when you apply the product rule, then you first take a derivative of m with respect to t, so it's how much your mass changes. Then you multiply it by your velocity, and then you take the same thing with velocity. You take the derivative of the velocity with respect to time, and times mass. Now, since our magnetic train has a constant mass, it doesn't change as a function of time, then this entire term will become zero. So you will only be left with this term. And as you can see, this term is mass times acceleration, because dv dt is acceleration. Now if we had a rocket instead of a train or an airplane, so when a rocket or an airplane flies, then it consumes fuel, right? And when you consume fuel, then your mass changes. In that case, this term would not be zero. But in our case, it's zero, alright? So our applied force could then be written in this form. The reason why I put here applied force is because it's the only force in this x direction. So if we had another force, then we would have to either add or subtract these force vectors, and then you would have some kind of net force, and then you would have a net force here. But right now we only have the applied force. So we know that our applied force is mass times acceleration. So what we can do next is that we can take this m and we can put it on the other side and down in the denominator place. So you would have our acceleration equals 1 over m times the applied force, right? And then the applied force is a function of time. So next, what you do, you take the integral. So what you have here, you have this acceleration axis, and then you have the time axis. And so this curve here, and it's just for illustrative purposes, it's just a random curve. It doesn't represent anything right now. But we can assume that this curve is then our function, and the function in the mathematical form would be the acceleration, dv dt, equals 1 over m times your applied force, which itself is a function of time, right? So you could imagine that this could be like 2 times t cubed or 3 times t squared. If this axis is your time axis and this axis is your acceleration axis, then let's say if we say that this is our function, then a question to you is how would we go from this form to velocity, right? Because this is acceleration, but acceleration is the change of velocity with respect to time, right? So it's dv dt. So in order to go from dv dt to v, to velocity, then you do antiderivative, which is an integral. And mathematically, it would look something like this. So if your acceleration is dv dt, and you make it equal to 1 over m times your applied force, then what you do, you put your delta t on this side, onto the right side, and you will be left with dv equals 1 over m, and then this expression, and then your delta t would be here in the end. And so when you take the integral of it, then you put your integral operator here, and so this is from where you start, and this is where you finish. So in this case, you start from an initial velocity. It doesn't have to be that your train at the beginning is at rest. Maybe your train already has some kind of velocity. If it doesn't have any kind of velocity, then you would put 0 here. But let's say if it already travels 5 meters per second before you hit the counter, then that would be your initial velocity here. And then your final velocity doesn't have to be a specific number. It doesn't have to be a constant number. You can treat it as a variable that changes as a function of time. So in other words, you could treat it like, okay, I take the integral from 2 meters per second to 5 meters per second, or I take the integral from 2 meters per second to v that changes as a function of time. And so on the other side, you put another integral operator here. Since mass is constant, the mass doesn't change with respect to time. You're taking the integral with respect to time here. That's why you have here dt. And because your mass doesn't change with respect to time, you can put it outside of the integral. But your force does change with respect to time, so it stays within the integral. And so you integrate it from 0 to t. So you start your counter at 0 seconds up until whatever t you have. If your final t would be 5 seconds, then here you would have velocity at 5 seconds. If your final t was 10 seconds, here you would have velocity at 10 seconds. Okay? Next, if you now integrate this part, then you would have your vt minus your initial velocity, right? So this is your variable that changes as a function of time,
minus your initial velocity, and you leave this part unchanged, then you simply take this initial velocity and you put it on the other side. And so that's how you have your velocity as a function of time equals your initial velocity plus this entire term. And now, since we don't know what this function is, and we have to implement this thing in the code anyway, then we're going to transform this continuous form, this continuous mathematical form, into this discrete form. So this is a discrete mathematical form, and this is something that you can directly apply into your code. You can do it inside a for loop or while loop. And so when we work with the water tank example, then I showed you how we can go from the continuous form to the discrete form. So here now we work with these time intervals. So our time interval was 0.02 seconds. So then this is our present, right? And then this is our past 0.02 seconds ago. And again, this is our past 0.02 seconds ago. And this is our present here, tj, right? And so if you want to numerically integrate, then you would have something like this working as a loop. Now, what we have our velocity as a function of time, right? But this is not our system. What was our system? Our system was a position, not velocity, not meters per second, but our position. So it's not enough what we have done so far. Right now we only have our velocity as a function of time, right? So this dx dt, it's v, right? It's our velocity. And now what we have our velocity as a function of time. But our main goal was to get x as a function of time. So what do? Well, we take another integral, right? So we have another function now. So this is our velocity that we got by taking the integral of this function. So now we have this function here, and since v is dx dt, is the change of position with respect to time, if we want to get position as a function of time, if we want to get x as a function of time, so what do? We take another integral. All right, we now integrate our velocity. Now we have a velocity as a function of time, and so we integrate that, and then we get our x. So it would look something like this. So the same logic is just instead of v's you have x's here, and here instead of the force you would have velocity. And so you take this integral like this, exactly in the same way, right? Exactly in the same way. Only now you have your initial position, not the initial velocity, but the initial position. And then your changing final position. And here, instead of 1 over m times your force, you simply have your velocity. And so you integrate it like this. And now you have your position as a function of time. And this is your discrete form, right? Now you're taking the integral numerically that you can apply in the code. And so what we have done here, we have taken two integrals. So this could be our mathematical model of our train system. So our system input was the applied force that was produced by magnets, right? Next, what we did, we divided this force by 1 over m, and then what we got our acceleration, because if you divide force by m, then you get your acceleration. Then we took the integral, we got our velocity. And then we took another integral and we got our position. Okay? And our mathematical model for our system would be all this. So the continuous form and then the discrete form here. Okay? And also here you would have the continuous form and the discrete form. Our mathematical model would then consist of two parts, right? It would consist of two parts continuously, and it would consist of two parts discretely. So if you want to represent your mathematical model in a continuous way, then you would have two equations here. One equation is here that takes you from fa to dx dt, and then the other equation here is to go from dx dt to xt. And this is the same thing, only in the discrete way. Alright? So now, let's try to apply our proportional controller, what we had in the water tank example, to this example. Let's see how it works out. See you in the next video. Okay, let's carry on with our PID exercise. So right now, you see a simulation of the train, and we have taken away the inclination. So right now the train only goes to the left and to the right, and the controller that I have applied to this train is the proportional controller. It's the same controller that we had applied previously in the water tank example. It's the same controller. And so I've also switched off the random function that makes the block appear randomly. So its initial position starts only from here. We want to see whether the proportional controller is able to do the task and catch the block or not. And as you can see, it's not really doing its job. I mean, it is trying to be where the block is. It is trying to reduce the error. However, the problem is that the train is not stopping where it should stop. It is overshooting. And if you're very lucky, you might catch the block on the go if your timing is right, but that's not the goal. The train should stop here and then catch the falling block. So the proportional controller here is not working. And now we need to examine why it's not working. And after we know the reason, we can then design our controller or modify our controller to complete the task and to eliminate the shortcomings of the proportional controller. Alright, so let's see that in the next video. So what we saw in our simulation was our train oscillating around this reference point here. So here in the middle we have our reference point, and the train was oscillating around it. So it first starts going from here in this direction. While it's on this side of the reference line, you have force directed to the left side. Then the train goes here. As it goes to the left, but since it's on the left side of the reference frame, you have force to the right, right? Because now the error is positive. Here the error was negative in the first case. In the second case, the error is positive, so the force is also in the positive direction. Even though the train itself is going to the left, now the train is going back to the right, but it's still on this side of the reference line, so the force is also to the right. And now when the train crosses this reference line, then even though the train goes to the right, but the force vector is to the left, because the error here is again negative. So the error on this side is positive, because it's xr minus x, and then on this side the error is negative. So that's how the proportional controller controls the force for the train. But now let's analyze the behavior of the error. So if you look at this picture, and if you look at this picture, then essentially this graph represents what's happening here. As you start moving from this point to the left, at the beginning you have a negative error, right? Because you are on this side of the reference line. your reference position minus your actual position will give you negative error. And that's why you start from here, right? And then as you move and you cross this reference line, when you are on this side, then your error is positive. So you are here. Now, this block here, right? You are also on this side of the reference line on the left side. So your error here is also positive. So you would be somewhere here. And when you're here on the right side of the reference line, then you will be here. All right. So as this block moves like this, you can see how your error changes as a function of time. First negative, then positive, and then negative. Now, one thing that I want to show you is that if you have a proportional error, then what you do with your error, you multiply it by Kp, and then you get your force, right? But then your acceleration is force divided by mass. So your acceleration is actually Kp divided by m multiplied by E. And this Kp over m, this is also a constant number, right? So this is also some kind of constant. So essentially you are multiplying E by some kind of constant, which is Kp over m, and you get acceleration. That means that your acceleration function, which is this one in red, has the same shape like the error function, right? If you look at it, this is your error function, and this is your acceleration function in red. And it has the same shape. Now, of course, it has a different magnitude because you multiplied the error by some kind of number, which was Kp over m. So you might have a different amplitude here, either bigger or smaller. However, the shape is the same. So this is your acceleration function, right? And now, in order to understand why that block was overshooting, like we need to go from acceleration, first of all, to velocity. So now I'm going to try to explain to you why the train overshoots when it reaches its target position. So this is the place where I would ask you to pay really close attention to what I'm telling you, because you need to focus on what I'm about to tell you in order to understand what I mean. So let's start. So first of all, that was our case, right? The train started from here, it went here, and then back here. You had negative error here, you had positive error here, negative error here. You can see it on this graph, alright? Now, when you have your error function, you get your force out of it. You get your acceleration if you divide Fa by m, force by mass, or you can just get your acceleration if you multiply your error by this constant, which is Kp over m. It's the same thing. That means that your acceleration function has the same shape like the error function, right? So when your error is 0 meters, when you're here, when you're at time equals 2 seconds, and also time equals 6 seconds, but let's focus on time equals 2 seconds, right? When your error is 0 here, when you're here, then your acceleration is also 0 meters per second squared, because your force is 0 newtons. The applied force here is 0 newtons, because your error is 0. Okay, what does it mean? If you integrate acceleration as a function of time, if you integrate it, then you get your velocity. What is acceleration? Acceleration is the change of velocity with respect to time, right? So when your acceleration is 0, then for that brief moment of time, your velocity, the velocity of your train, for that brief moment of time, it stops changing. The slope of your velocity is 0, right? At time equals 2 seconds. The derivative of your velocity, with respect to time is 0. But that doesn't mean that the velocity itself is 0 meters per second. In fact, it is very high here. It's negative, right? Now, what happens when you have a velocity as a function of time and you take the integral of that? What do you get then? You get position, right? So your position starts from here. You are on this side of the reference line. So this is the positive position, and then this is the negative position, and again this is the positive position here. This function, it represents the position of your train. So the proportional controller, it makes sure that when error is 0, then your acceleration is 0, and in fact it also makes sure that your position is 0, right? However, the problem is that when your acceleration is 0, you have something in between. You don't go directly from acceleration to position. You first go from acceleration to velocity, and then from velocity you go to position. So when your error term is 0, then your acceleration is 0. That means that your velocity at this point is not changing, but it doesn't mean that it's 0. Here, velocity is negative. Now, when your velocity is not 0, then it is impossible that your train reaches its target position and just stays there. It can't, because your velocity is not 0. What is velocity? Velocity is the change of position with respect to time, right? It represents how your position changes. So if at time equals 2 seconds, your velocity is not 0, then what's going to happen? Obviously, you're going to continue driving in your direction. And the same thing here. At time equals 6 seconds, your error term is 0. That means your force and your acceleration is 0. And also your position is 0 meters. You are where you want to be. The problem is you don't stay there. Why? Because even though your acceleration is 0 meters per second squared, the next step from acceleration is your velocity. Your velocity, however, even though at this time it's not changing, it has a 0 slope. Your slope here is 0, but your velocity itself is not 0. It's a positive value. And because your velocity is not 0 meters per second, it's impossible that your train reaches this point, this reference point, and then just stays there. It's impossible. Your velocity is not 0. So you continue driving forward, and that's why you see this overshoot. Because we control acceleration, we make acceleration 0 meters per second squared, but we don't take care of velocity. We don't make sure that our velocity is 0 meters per second here. And that's why we have this overshoot. What we want is something like this. So this is our position function. And if you look at this green line, so we want something like this, right? So we want that at time equals 2 seconds, when we reach our target position, we want to stay there, right? We don't want to overshoot. We want to stay in that position. In order to stay in that position, if you look at this green line, we need to make sure that our velocity also stays 0 at time equals 2 seconds. And the problem with the proportional controller is that the proportional controller is not powerful enough to achieve this kind of behavior in this system. Why? Because if you look at your system, then our system, our train system, it has 2 integrator operators, right? So you have 2 integration. You need 2 integral operators. You need the first one to go from acceleration to velocity, and the second one to go from velocity to position, right? And the problem with the proportional controller is that a proportional controller cannot handle 2 or more integrators. It can only handle 1 integrator. So the proportional controller would work if, for example, our system was different. If, for example, our system input was a force that would become an acceleration when we divide force by mass, right? And then our system output would be velocity. So if I were to tell you that, okay, I don't care about the position of my train, I just want my train to reach 5 meters per second. So I want the velocity of my train to be 5 meters per second, and I want it to stay there. And then my system input would be force. Then I could use a proportional controller. Then my proportional controller would make acceleration 0 when my velocity was 5 meters per second. Or for example, if I were to tell you that I care about position and I use velocity to control my position, not force, not acceleration, but velocity. And I say that, okay, I want my target position to be 10 meters. And then I regulate, somehow I regulate velocity of my system. And then my proportional controller would make velocity 0 when I reach my target position of 10 meters. So your proportional controller would work if your system only had one integrator. And in our water tank system, you only had one integrator, right? You had a mass flow rate, and then on the other side you had your volume, and you only needed one integrator to go from mass flow rate to your volume. But now the system is more complicated, because now, first of all, you have applied force that you transform into acceleration by dividing the force by mass. That's okay, this is just a constant. But then you need to integrate your system 2 times in order to reach your system output, right? In order to get from acceleration to position, you need to integrate it twice. And for that, we need something additional. A proportional controller alone won't be able to cut it. So we need something additional. And the next thing that we are going to introduce is a derivative controller, which will be combined with the proportional controller. And you will see that when you combine them both, then they can handle 2 integrators, and then you can have something like this. So now let's look at the derivative controller and see how we can combine it with a proportional controller. So how do we achieve the behavior of our system, of our train, as we want it? How do we achieve this velocity function, this green one? And how do we achieve this exposition function? How do we use a derivative controller to achieve that? So now I'm going to show you what a derivative controller is and how you can combine it with a proportional controller in order to achieve a system response like that. And by system response, I mean how your system reacts to your input, how the output reacts to your input, which is force created by magnets in our case. So let's see. First of all, let's pay attention to this graph here. So in red, this is our error function, right? It's the same thing that you saw before, that this is the error function in red. So if you take your error and you multiply it by Kp, then before you got your force. And that force was then the force that the magnets applied to the train in order to move the train. But as we have seen, it's not enough. So we need something else. So we can use a derivative controller. So this is a derivative controller, right? So how do you get the derivative controller? Well, it's very easy. This is your error function, and you take the derivative of your error function, and then you get this blue function, right? So this blue one is dE dt. And the reason why you have x here is because we're dealing with the horizontal error, right? So this is your dE dt. So this is your derivative. This is how your error changes with respect to time. So you have this function, this blue function, and you multiply it by another constant, which is kd. And kp and kd, in both cases, they are slopes. They are different numbers, but the logic is the same. their slopes. And so in red, you have a proportional controller, and in blue, you have the derivative controller. And so if you add them together, the proportional and the derivative controller, then it's a PD controller, so a proportional derivative controller. And when you add them both together, then you will get your force, your final force that magnets will create in order to move the train. But let's look at it a little bit closer. So now you know how to create the derivative controller. If you look at it, then okay, so this is the proportional part and this is the derivative part. So note that the difference here is that here you have error. In the proportional part, you have error. And in the derivative part, you have the change of error with respect to time, right? So now this axis is dE dt. And if you multiply it by some kind of slope, then you get the derivative part of your force. And here's your proportional part of your force. And if you add them together, then you have your final force. Now, why is it useful? So let's see. We start moving from here and then we move here. So this block still moves to the left. Then now here this block moves to the right, and here the block still moves to the right. Okay, so if you look at this dashed line, it indicates from where this block is going. So here you know that the block is moving to the left, here it's moving to the left, here it's moving back. This is where the block has just recently been, so it's moving in that direction. And here the dashed line is here, which means that the block is moving to the right, so it's moving that way. If you look at this graph, then what you can see is that when you're in the first case, let's divide this graph into 4 parts, right? So we have 4 parts because here we also have 4 parts. You have here where you move to the left, then you are on the other side of the reference line where you still move to the left, but you slow down. Here you go back, you move to the right towards the reference line, and then here you're again on the other side of the reference line, but you move away from the reference line. So you have 4 stages here, and these 4 stages, they can be seen here. So we divide this plot into 4 parts. So we divide it with these orange dashed line. Alright, so this is the first part, the second, the third, and then the fourth. So in the first part, we move towards the reference line. So let's see. If we move towards the reference line, then our proportional controller gives us a negative error and therefore a negative force. So you have a negative force, right? You have force to the left, and to the left means negative. However, if you now add this derivative part, then the derivative part will give you a positive, because even though your error here is negative, but the slope in this section is positive, and therefore the derivative here is a positive value, and you multiply it by kd, so it will give you a positive number. Therefore, there will be a component of the total force, Fa, that is positive in this direction. Now, this is very good because before we applied our derivative controller, we only had our proportional controller, so we only had one force pushing this train towards the reference line. But now what we have a proportional part that is pushing it towards the reference line, but then you have this derivative part that is slowing it down. Now, if we now go to the second section, now we are here, and it's this one, right? Here we are on the other side of the reference line, but we move away from the reference line. And what happens here is that both the error term and the derivative of the error, both of them are positive. That means that the two force components are positive in this direction. So think about it now. Your train is moving away from the reference line, but you have two force components pulling it towards the reference line, right? So that means that this train, even though it is moving away from the reference line, these two force components are slowing it down and pulling it towards the reference line. That means that this train is slowing down faster than it was just in the case of a proportional controller. Now, the next section would be this one. So that corresponds to this situation where you now go towards the reference line, right? Now you move towards the reference line. And so the proportional controller pulls you towards the reference line, but the derivative part points in another direction. So it slows your train down. So you still move towards your reference line, but you're slowing down. And you can see it from this graph that your error term is positive, but the derivative of your error is negative because you have a negative slope here, right? So this blue line is the slope of the red line. And so here, the derivative of your error is negative. Therefore, your force vector of the derivative part is negative in this direction. And so it slows your train down as you get closer and closer to your reference point. And finally, when you are again on this side of the reference line, you move away from your reference line, but you have both the error and the derivative of the error. They are both negative. So you have two force components pulling the train towards the reference line. So you can see that the derivative part, in this case, it's working in your advantage, okay? And the thing about the proportional and then the derivative part is that you can choose what values you choose for Kp and Kd. Note one thing, Kp and Kd, they have different units. Kp is Newton per meters because you have error here and then you have force here. But in terms of the derivative controller, here you have the derivative of the error with respect to time, and here you have force. Therefore here the units here are meters per second and the units here are newtons. So your Kd is actually Newton per meters per second. However, one thing that I want to explain to you is that as you design your controller, right, you can choose the values for Kp and Kd, and it's at your discretion, and depending on the system, you try to find the right values, and that's called controller tuning. So one thing that I want to talk about now is about controller tuning. What does it mean when I talk about controller tuning? In this case, it only means that we try to find the right value for Kp and Kd in order to achieve our target in the best possible way. Kp and Kd, what are they? They're just slopes, right? So if you choose a strong value for Kp, then you will have a very high slope here. And if you choose a very low value for Kd, then you will have a very small slope here. So in that case, the proportional part in your controller would be stronger than your derivative part. And vice versa, if you choose a strong value for your Kd and a weak value for your Kp, then the derivative part of the controller will be stronger and then the proportional part will be weaker. And so you can regulate how strong is the proportional part in your overall controller and how strong is your derivative part in your overall controller, and that will of course affect your system behavior. For example, if you say that your proportional controller is very strong, right, but you want your derivative controller to be weak, then you choose Kp to be a big number and Kd to be a small number, and then the result of that would be that here you would have a very large force vector, the red one, and then the blue force vector would be smaller, and in that case okay, this blue force vector would still slow down your train in this condition. However, the slowing down effect would not be that strong. However, if you do it vice versa, you choose KD to be a big value and you make your derivative part of your controller very strong and then the proportional part weak, then you will have a small force vector here pulling the train towards the reference line, but you will have a bigger vector in the other direction, and so the slowing down effect will be bigger. Now you might think that if you choose a KD factor as a very big value, then you will make your derivative part very big compared to your proportional part, and then you would have a very huge vector here, the blue one, and then a small vector here, the red one. And so according to this, you might think that the train might go in another direction. It might go to the right, away from the reference line. However, that's not what's going to happen, because remember that the derivative part doesn't only depend on this KD value. It's KD times the change of the error with respect to time. All right? And this derivative controller, the derivative part, has this effect of resistance. So the train wants to go towards the reference line, but the blue line here, the derivative part, it resists. So at the beginning, you have your error here, right? And if your KD is very strong, then what it will do, it will resist. That means that the train will be moving very slowly and its error will change very slowly. If its error changes very slowly, then even if you have a strong value here, you have a big value here, but because the error changes very slowly, you will have an extremely small value here. So that is why you won't have a situation where you have a big vector here and a small vector here, because in a way they're linked. They're linked through the error terms, right? So a strong KD will make the error E change very slowly. And if the error E changes very slowly, then dE dt will be very small. Let me say it again. If KD is very big, it has the resistive nature, so what it will do, it will not allow the train to move very fast, right? So because at the beginning your error, it's negative, but its slope is pretty much zero, right? So even though you have a very strong value here, but at the very beginning your slope of the error is zero. That means that whatever value you have here, this term here is zero. So this entire term will be zero at time equals 0 seconds. And only when the error starts changing, then this term will appear. And because this term has this resistive nature here, if you choose a strong KD, it will cause the error to change very slowly. And because of that, you will have a very small number here. So even if you have a big number here, this entire term, KD times dE dt, it still won't cause a situation where the train would just like move to the right. So now I'm gonna show you a simulation where we can tune a little bit of KPs and KDs and we see how they react. Okay, so see you in the next video. So I'm gonna present a simulation now, and this is the code for it, and you can download this code in this section. So feel free to download it, feel free to study it, reverse engineer it. You can look at what I did, you can experiment. The only thing is that if you want this code to work for sure, I only recommend you to change these 7 variables here at the beginning of the code. And if you want to change something else, then it's better if you make a copy of this code and then experiment on the copy. Alright? So here we can change Kp and Kd, and the next one will be Ki, so the integral part, but right now we're going to focus on Kp and Kd. So I choose Kp to be 300, Kd to be 100. The mass of the train is 100 kilograms. We are on Earth. The Earth's acceleration due to force of gravity is 10 meters per second squared. Right now the inclination angle is 0 radians. And so let's see how the system is going to react. Well, it managed to catch it, so that's very good. So you can see that now it does overshoot because Kp is still pretty strong compared to Kd, but Kd, the derivative controller, is able to slow down the train and damp out this oscillation. And by the way, here you have the derivative of the error with respect to time. So this is the error, right? And this is the derivative of the error with respect to time. So let's test more. For example, if I say that Kd is 50, then now the resistive nature is weaker. So if it's weaker, then you're going to overshoot more and you will fail. All right. How about if we make them equal, 300 and 300? So in this case we have Kp and Kd, they're equal, both 300, and you can see that for this specific case the PID controller is pretty well tuned, so it is able to slow down and stop where it is supposed to stop and then catch this falling cube, right? So it is able to damp out the oscillation of the train pretty well. And so you can see this is the error here, and you can see that it very smoothly becomes 0, and this is the derivative of the error with respect to time, and also it is very smooth, and it also becomes 0 very smoothly, just like the error. Now let's see what's going to happen if instead of 300 and 300 we're going to make Kp 300 and Kd 3000, so 10 times stronger. So now Kd is going to be very strong and the effect of the derivative controller is going to be very strong. Let's see what's going to happen. As you can see, the resistive effect of the derivative controller is so big that it doesn't let the proportional controller to move the train towards the block. So the train moves towards the block very slowly, and therefore it is unable to catch it. So like we talked before, even though Kd is a lot bigger than Kp, the train is not moving to the other side, right? It's not moving to the right. Why? Because in the derivative part, Kd is multiplied by this. It's multiplied by the derivative of the error with respect to time. And at the beginning, the derivative is 0. And because it has such a strong resistive effect, the train is not able to start moving fast enough, and therefore the change of the error is not big enough. So they are linked in this sense. The greater your Kd, the less your error will change, and so the end result is that your train will move towards your block, but in a very slow fashion. However, there is one thing that you have to keep in mind. When you design these kind of controllers, you cannot put just like random numbers, because if you put completely random numbers, then your controller can go crazy. So I'm going to give you an example. 7,000. Let's see what's going to happen now. So you see, now the system is becoming unstable. Okay? So it's becoming unstable. And that's because, when you have values that don't make sense, that are very big or very small, then, what's happening here is that you have a code running, right? And your code is always calculating something. Your controller is always calculating something. So if you have weird values, then it might become unstable. It might start giving you big values in some areas of the code, in some areas of the controller that won't make sense, and they just make your system unstable. So, for example, if I make it 10,000, then it will be more apparent. You see? Like, it just doesn't make sense. So, when you design your controllers, you shouldn't put whatever numbers you want. So it's just something to watch out for in the future. And now I'm gonna turn on the random function to see if the block appears randomly, will the controller be able to catch it? So what I'm gonna do now, I'm gonna make KD 250. I'm gonna make trials 5. That means that there will be 5 random positions from where the block will start falling down. And what I have to do, I have to change one thing here. So it's here. I have to comment this part and I have to turn on the random function. And let's see. Okay, it is able to catch this one, 3 times more. Now they appear randomly. So it seems that when your KP is 300 and KD is 250, then the controller in this environment works pretty well. Okay, so in the next video, we're gonna start discussing about the last part of the PID controller, the integral part, because there are situations where even proportional and derivative controller combined cannot handle. So we're going to discuss one specific problem called a steady state error. I'm going to show you why the proportional and the derivative controller can't solve a steady state error and what a steady state error is, and how the integral controller can solve it. And then we're going to combine them all together and you will see the entire picture. Now in the next part you will have an inclination, so the rails will go up diagonally. Welcome back. So now we're going to start learning about the final part of the PID controller, the integral part. And this is what it stands for, PID, proportional, integral, and derivative controller. So we have so far covered the proportional part and then the derivative part, but we still need to cover one more part, which is the integral part. Let me show you one example where that integral part can be relevant. So now we're going to include an angle here. So now the rails, they don't only go horizontally, they also span horizontally and vertically, right? So now the train not only can go left and right, but it can also go up and down, right? So now let's think about what it means. First of all, if we start putting forces on our bodies, then, okay, we still have this applied force that is applied by the magnets to the train, but now we also have a force of gravity. Now before, force of gravity didn't matter because since we ignored friction, because it's a magnetic train and so it basically it levitates a little bit, so there is no friction, almost no friction, but it's so small that we can just neglect it. And here as well, we neglect friction. However, what we can't ignore anymore is force of gravity. Why? Because force of gravity acts on this train vertically. However, because this train is on rails that are at an angle, you have to take this force of gravity and you have to decompose it into a component that is perpendicular to the rails, right? And which is tangential to the rails. Now, the component that is perpendicular to the rails is this one. And we call it the gravity normal force. And you get it by multiplying cosine theta by force of gravity. So this is our force of gravity here, right? So essentially it's the mass of the train multiplied by g, which on Earth is 10 meters per second squared, or more precisely 9.81 meters per second squared. And this theta here is the same like this theta here. So if you want to decompose this vector into the normal component and the tangential component, then the normal component would be fg times cosine theta, and then the tangential component would be fg times sine theta. And now you can shift these vectors, and what we're going to do, we're just going to shift this vector here. And so this normal component of the gravity force, it is balanced out by the normal force, right? So it's just like when you're on the ground, you don't go through the ground because the ground applies normal force to you, which is equal but opposite to the force of gravity. So that's why you don't accelerate when you stand on the land. However, in this case, since the train is on the inclination, then the normal component is not completely down, it's in this direction, and it is balanced out by the normal force. Now the tangential force of the gravity force, however, is the force that if you don't do anything, it will make the train slide down, alright? And so now you have this extra force that you need to think about when you analyze your system. And let me just show you a simulation where I'm going to switch off all other forces and I'm just going to let the tangential force to do its thing. Alright? See you in the next video. So right now I have switched off all the components of your applied force. So I have made Kp, Kd, and Ki 0. So there is no applied force. And because there is no inclination, because the rails are completely horizontal, the train is not moving anywhere, right? So now what we're going to do, we're going to introduce a 15-degree angle, alright? So let's do it, a 15-degree angle. So 15 degrees in radians is pi over 12. And so let's see what's gonna happen now. So you can see that this 15-degree angle, there is now a tangential component for the force of gravity. There is a normal component that does not affect the motion of the train. However, the tangential component is affecting it, and it is accelerating. Oh, wait. Oh, I thought that it was gonna catch the cube. Oh well. So this tangential component of the gravity force is going to now make the train accelerate along the rails downward. So now when you apply your force produced by magnets, you have to take into account the tangential component of the gravity force. Alright, let's go back to the equations. I'll see you in the next video. So when we look at this drawing, then we have now two forces along the rails. Our falling object, our falling cube is here, our train is here, so that means that our error is this one, alright? This is the distance, and it's a negative error, and so you have the force from gravity, the tangential part, it's in this direction, and then you also have this applied force produced by magnets, also in this direction. So what really happens is that you have to sum them up, the tangential component of the gravity force and then the applied force, and then you will get a net force that you can now decompose into x component and y component, because at least in my code, the calculations are made separately in the x direction and in the y direction. And there are several ways you can do it. You can also define a different reference frame. You can say that, okay, this is your x and this is your y, but I didn't do that, so I prefer to just decompose this vector into x and y. I still use this as my x-axis and this as my y-axis. So this is your net force here, alright? So now if you want to know the acceleration of your train, then you need to take this net force and then you divide it by the mass of this train, and then you get the acceleration, the real acceleration of this train. Now, if we have another situation where the cube is here, right, then you have a positive error. And so the tangential component of your gravity force is still in this direction. However, your applied force by the magnets is in another direction. So in this case, what happens is that your net force will be smaller, because your net force will be Fa minus Fgt, because they are in the opposite direction. So the difference is Fnet, and that just means that in this situation, your applied force has to be greater in order to go up, because it also needs to counter this tangential gravity force. Okay? So this is the setup of our world, and if you want to derive equations for this situation, the logic is exactly the same. Now the difference here now is that because you have two dimensions, right, and because at least I do it using still this axis as x and this axis as y, I do it in two dimensions. Because of that, what you have to do the same thing like you did before, only you have to do it twice, in the x dimension, and you have to do it in the y dimension. So essentially what you do, you take your fnet and then you decompose it, fnet x and fnet y, and you work with them separately. And so you first of all get the acceleration in the x dimension and in the y dimension, then you get your velocity in the x dimension and y dimension, and then you get your x position and y position. So it's a double integration, but you just do everything twice in the x and y dimension. And now let's look at the specific case where I'm going to show you why you would need an integral controller. Alright, so now let's look at a specific case. Imagine that this is where your block is, right? And you're exactly where you have to be, okay? Your block is here and you're exactly where you have to be. So what happens when you're exactly where you have to be? Well, your error is 0 meters, right? And you're at rest. If you're at rest, then also your E dot, so your error derivative with respect to time, it's also 0 meters per second, right? Now, if the angle here was 0 degrees, or 0 radians, if we only had this horizontal problem, if we didn't have this force of gravity, this tangential component of it, then we wouldn't care. Then everything would be nice. However, now we have a problem, because let's think about it. If your error is 0 meters, right? And if your E dot is 0 meters per second, that means that if you look at your proportional and derivative controller, then this term is 0 and this term is 0. That means that your applied force is 0. 0 newtons. Okay, now if your applied force is 0 newtons, but you have this force of gravity, this tangential component of the gravity force here, but your error and your E dot are 0, that means that there is no other force to counteract this gravity force in this direction, right? So what's gonna happen in this case? The train will start slipping down. And so when it starts slipping down, then your error and your E dot, they are not 0 anymore. And so the black would be the proportional part, and then the red would be the derivative part. So as you go away from where you have to be, from your reference line, now there is an error, and that error will produce force in the positive direction, right? However, if you sum them up, they are still smaller than this gravity force. So because of that, because the gravity force in this direction is still greater than the addition of these two forces to the right, because of that, the train will still continue sliding down. Okay, but now let's imagine that when it slides down a little bit more, the error will increase even more. So the applied force will increase, because remember, we have proportional controllers, so at least the proportional part will always increase the further you get from your reference line. So at some point, you reach a point where the total force, the applied force, is equal to your tangential force. Okay? So now the forces are equal but in the opposite direction. And now what happens is that the train is at rest. Now when the train is at rest, then the error doesn't change anymore, right? If the error doesn't change anymore, then the derivative part of the applied force is 0. Because the derivative part of the applied force can only exist when the error changes. But since the train is at rest, because both forces are equal in magnitude, but they are in the opposite direction, because of that, you don't have the derivative part anymore, but your proportional part, the proportional part of your applied force, is equal to the tangential part of the gravity force. Now, if the forces are equal, then, well, you're kind of trapped, aren't you? Your controller doesn't know what to do, because it can only increase the force if your error changes, but it's not changing. So it's trapped. So this is now one situation where it's not enough to have a proportional controller, and it's not enough to have a derivative controller. So you need something else, and that's why you need the integral controller. And I'm going to explain to you how it works. But again, just to make you really understand what's going on, the train is not moving. Therefore, the error that you have here is fixed. Because it's fixed, the derivative part is 0, and the proportional part of the applied force is not 0, it's a number, but this number cannot change. This number, the proportional part, produces force which is exactly equal in magnitude to the force of gravity, and because of that, the train cannot move, and so because of that fact, your error stays the same, and because of that fact, your applied force cannot change. So you're just stuck, okay? And this kind of phenomena has a name. It's called a steady state error. And to counter that steady state error, there is another idea. The idea to counter this kind of situation, the steady state error, for that, we need to use an integral controller. So let's look at this graph here. So you have two graphs here, okay? So first of all, in the upper graph, the first thing that you see the error function, okay? So if we start looking at our story again, starting from the beginning, where we were at the place where error and then E dot were 0, then on this graph, it's this place here, okay? Now, as we start sliding down, we had two components so far, our applied force, right, the derivative part, and then also the proportional part. So this is this one. We divide this graph into several sections. And so this first section from here, from the beginning till this dashed line, it's the time period that it takes for the train to go from this initial position up until the position where your forces are balanced and you get stuck. So this is like the intermediate time frame. During that intermediate time frame, you have this proportional, and then you have this derivative applied force, right? And it makes sense that both of them, they are pointed towards the right because your error is positive, and then your E dot is positive, and you also assume that you choose Kp and Kd as positive numbers. And that's what we always assume. I mean, you can also choose negative numbers for them, but then you would reverse everything. But in this example, we assume that Kp and Kd are always positive. And so the error and E dot, they are positive. So both forces, they are pointed towards the right direction. Now, starting from here, this is where you get trapped. So from here till here, you have the steady state error. And this is the time axis, by the way. So this is the evolution of your error term and your E dot. So from this point up until this point, we assume that there is no integral controller, all right? So it's strictly Kp times E plus Kd times E dot. So we ignore this final term, which is the integral controller, right? So from here till here, there is no integral controller. From here till here, you have the steady state error. This is when your error doesn't change, which means that your E dot is 0, which means that you only have your proportional controller working, right? And there you go. You only have this proportional controller to the right side. And so you're trapped. Now, in order to get out of the trap, at this point here, we turn on our integral controller. And the integral controller is just like proportional and the derivative controller. It also has a constant, Ki. Ki is also like a slope, so it's also a number that you choose. And now you multiply this Ki not by error, not by the derivative of the error, but by the integral of the error, right? So when you integrate the error function as a function of time, then that just means that you sum up the area under the curve of the error function. And you can look at this graph. So here your error increases, and then as you sum up the area under the error curve, this function is the integral of the error. So it continuously increases because it's a summation of what you have here. And so when you're in this section, that's when your error doesn't change, right? Your error stays the same, and your E dot, because of that, is 0. However, what changes is the integral of your error, because even though your error is the same, but the time is still ticking, and so as time goes by, you continuously scan the area under the curve of the error function, right? And you continuously sum up the area under the curve, and the summation is shown here. So you see, even though your error is constant, but the integral of your error is not constant. And so, starting from this point, we turn on our integral controller. So now we have a complete PID controller. We have our proportional part, our derivative part, and our integral part. Okay? And now, when you're trapped, because your forces were balanced, right? When you turn on your integral controller, which is here, then you will have your integral of E, this one, you multiply it by Ki, so you will have an additional force towards your reference line. So you see, you were trapped before because your proportional controller was equal to your tangential gravity force, but now all of a sudden you have this extra force that comes from the integral part. So now your entire force to the right and up is greater, so your train will start moving up towards your reference line. So what happens next is that as you get closer to your reference line, your error starts going down, right? It makes sense because you start going towards your reference line, so the distance between your train and the block, the horizontal distance, is decreasing. So your error goes down. When your error goes down, that means that your E dot is negative, right? And because you have a linear function here, then the derivative of it is just a constant value, but it's negative. And that's why the derivative part of your PID controller points to the left. Here your error is still positive, so your proportional part points to the right. And also your integral part, you have the summation, which is positive here, so it also points to the right. Now at some point you reach your reference line, right? You reach this point, you're here. But let's say that you overshoot a little bit, right? Nothing is perfect, so you overshoot a little bit. So now you are on the other side of this reference line, right? And so now you have a negative error, right? You have a negative error, but your slope is also negative. So both your proportional and the derivative forces, they point to the left. But as you can see, even though your error is now negative, which means that your integral of your error now starts going down, right? But it's still positive, so the integral part still points to the right. Now here, again, you are on this side of the reference line. However, now you move back towards the reference line, okay? And because of that, your error, it's negative, but it's decreasing, and so your E dot is positive, right? And your integral part is also positive, so that's why you see that your proportional force is to the left, but your derivative force and your integral force are to the right. And now let's assume that you finally reach the place where you have to be, the place where you have your block, okay? And again, like at the beginning, your error is 0, your E dot is 0, right? And you can see it from here. That's where you reach that place. This is now you're at your reference line, and your error is 0. The derivative of your error is 0. But now you don't slide back anymore, right? You stay where you're supposed to stay. Why? Because now you also have this integral part of your controller, and that integral part will provide the force that has the same magnitude like the force of gravity in the tangential direction. It has the same magnitude, but it's in the opposite direction. And so now your forces are balanced and you stay exactly where you're supposed to stay. And that happens because even though your E and E dot are 0, but your integral of your error is not 0. Why is it not 0? It's constant, right? Because your error now is 0. So when you integrate your error, the integral of your error does not change because your error is 0 all the time as a function of time. But the integral of your error is not 0 because, you see, the thing with integrals is that it doesn't only take into account the present, right? It also takes into account the past information. The final result of your error integration depends on what your error is now and what it was in the past. So in a way, you can think of the integrals as a reflection of what your variables did in the past. So even though right now your error is 0, but it wasn't 0 in the past, and that's why the end result of your integration is not 0. So it has some kind of number, and if you multiply it by ki, then you will have this term. And so when you're where you're supposed to be, then your proportional term and your derivative term will be both 0, and your train will only rely on this term, on this ki times integral e dt. So again, when you're where you're supposed to be, your train only relies on the last term, because the other terms will be 0. And the reason why the last term is not 0 is because the integral of your error, even though it's not changing anymore, but it's not 0 because it also takes into account information of the error from the past. Okay, so an integral is like an evolution. Think of the integral like an evolution of something. And that's how the integral part enables your train to actually stay where it is supposed to stay. Alright? So now the integral part provides you with this force necessary to keep your train where it is supposed to stay and to counter this tangential force of gravity. And that's why you need the integral part. Now let's put everything together. If you want to look at your PID controller in a schematic way, then it's very convenient to look at it like this. You have your error, and this error is fed through the Kp number. So this is the proportional part. Now the error is also fed through the dt operator. So this is the derivative operator. You have E dot, the derivative of error with respect to time, or the change of error with respect to time. You multiply that by Kd, right? This is your derivative part. And then your error is fed also through the integral operator. And then you have your integrated error, or the summation of the areas under the curve. In other words, you have this thing after you go through the integral operator, and you multiply that by ki, you sum them all up, and you have your applied force, your total applied force. And so you can tune the controller by choosing which part of the controller you want to be stronger and which one you want to be weaker. So you can put a strong value here and weaker values here and here, or vice versa. It depends on the system. Each system is different, and it requires you to understand your system properly, and it requires a lot of experimenting and experience. But in a way, that's what controller tuning means. So every 0.02 seconds you have a new force, new x value, new error. In this case, only the reference value here stays the same. So the reference value in our case is not changing as a function of time. But this position changes as a function of time, applied force, the error term. So your position goes here, checks it against the reference position, it calculates the error enters your controller, goes through all this, and produces this applied force that is fed into your system. That applied force will influence the system to get your x closer to your reference x, so that your error would become 0 eventually. So that is it. What I'm gonna do next, I'm gonna show you the simulation with the train, and it's gonna be the case where you have this angle. So I'm gonna run a couple of trials where we'll see how our PID controller is able to catch the falling blocks. Alright? See you there. Okay, so now I'm gonna show you the simulation of the most difficult case. The entire controller is working now and applied to our train. So I have 5 trials. the angle will be 30 degrees, pi over 6 radians. So the inclination, the rails, with respect to the horizontal line, it's going to be 30 degrees. And then Kp is 300, Kd is 250, Ki is 50. So let's run it and see what's going to happen. So here it is trying to catch it, and it managed to do it. And if you pay attention to this window here, this is the integral of the error, right? And so, oh, it missed it, so it's not very well tuned for this situation. So this is the error window, error as a function of time, the derivative of the error as a function of time, and the integral of the error as a function of time. And then this is acceleration, this is velocity, and this is position here. Now, we didn't tune it so well, so let's see if we can now tune it a little bit better. So what I'm gonna do, I'm gonna decrease the Ki. I'm just gonna say it's 10. I'm gonna make Kd 300, and I'm gonna leave Kp 300, and let's see what's gonna happen. So now the resistive effect from the derivative part is greater. So perhaps we're gonna be able to catch all the cubes. Or maybe not. I'm gonna leave the code in this section that you can download it, and you can play around with it as much as you want, and also the water tank code. You can also play around with that one. Okay, so this time we were lucky, so congrats. We did it. So thank you very much, and I hope you've learned a lot. Welcome back. This short video is for those who haven't really worked with Linux and macOS terminal or Windows command prompt. So if you're like me some years ago, who hasn't really encountered terminal or command prompt, then this video is for you. If you are familiar with terminal or command prompt, then please skip the video. This video is really for people who have almost never encountered Linux terminal or Windows command prompt or macOS terminal. Both the terminal in Linux and in macOS, and then the command prompt in Windows, they're very similar. And in this course, I recommend you to use terminal or command prompt to run Python files. And so I'm going to give you a short explanation of how to use terminal or command prompt for the purposes of this course. Essentially, I want you to know how to launch Python programs using terminal or command prompt. So if you look at the screen, then you know that I'm in my desktop. And so now I'm going to go into my default home folder. So you see that I'm in my default home folder, and then I have a lot of files here. And now from this default home folder, I want to enter into my desktop folder. And my desktop folder is right here. So I'm going to click it, and you see I have my files here. These files that you see here, these are these files here. So it's the same thing. And now, let's say that I want to go back into my default home folder. So I'm going to go here. Okay, this is how most people in the world use computers. However, there is another way to navigate through these folders. Here I have my terminal, and in Windows it would be command prompt. And in macOS you also have terminal. And so I have opened my terminal, and actually here inside my terminal I'm inside my home folder. So I can write here ls, and that command will show me all the files that I have in my home folder. And there you go, you see, I have all my files here. And by the way, if you are in Windows, then you don't write ls, you write dir. But in Linux you write ls. So being here is the same like being here. Now if I don't want to see those files anymore, then I'll just write clear. And now, just like we went from our default home folder into our desktop folder, and then we went back to our home folder, what we did, we navigated through folders, but we can also do it through the terminal. And we do it like this: CD, and then we write desktop. And now what we have done this. We have entered into our desktop folder, but through our terminal. And by the way, in Windows and in macOS, it's the same thing. If you want to change your folder in Windows, you write CD, and the same thing applies to macOS. And now if I want to see what I have inside my desktop, then I write ls, and you can see I have the same files here. So right now I'm in my desktop folder, in my screen, and also in my terminal. And now let's say that I want to enter my folder here. So you see I have more files here. And I can do the same thing in my terminal. I write cd, which is change directory, and then the name of the folder, MPC PID Udemy course. And by the way, in terminal, you can complete the names of the folders or the files with a tab button. So for example, I have only written this part, and then I click the tab button, and it has auto-completed the name of the folder. And then I click enter, and I'm inside the folder. I write ls, and as you can see, I'm now inside the folder called MPC PID Udemy course, and you can see that the same files that I have here, the same folders, I also have them here, all of them.
Of course, you need to have that specific folder in your current location. Only then you can enter into that folder through this cd command. If you don't have that folder in your current location, then you can't do it. You can only enter into the folders that you actually have in your current location in your computer. Just like when you're in your desktop, you cannot enter into the folders from your desktop that you do not have on your desktop. The same logic applies to terminal and Windows command prompt.
If I want to go back, I write cd space 2 dots, enter, and then I'm back. And so again, if I want to go one folder back, I can just write cd 2 dots, and guess where I'm at right now? Well, I went 2 folders back, and now I'm again in my home folder. And so if you haven't really worked with terminal or command prompt before, then do like I do. When you write your Python script, then just save it in your desktop. Just save it here. And so when you're in your desktop, then you can see that your saved file is here. And so when you're in your home folder in your terminal or command prompt, then just go into your desktop folder, cd desktop. Again, cd is in Linux, Windows, and macOS. Now when you are in your desktop, then you write either ls in Linux or dir in Windows command prompt. In macOS, it's also ls, and then you can see the files that you have in your desktop. So you have 2 Python files here, this one here, and this one here. And remember, Python files, they need to be saved with this .py extension. And so when your file is in your desktop and you are inside your desktop but through your terminal or Windows command prompt, then in Linux terminal you run your Python file like this. You write Python 3 and then the name of the file, which in this case is this one. and then you press enter. If you have an error there, then it will display you this error. For example, I have an error here in line 15. In that case, you have to enter into your Python file that you had saved in your desktop, which is this one here. And so I have a bunch of stuff that I haven't commented out, so I'm just gonna delete it. And so I'm gonna save the file. This is the file that is saved here in desktop. And then I can close the file. And so I'm gonna clear my terminal. But you can see that I'm still in my desktop. And so in order to run the file, I write Python 3 and then calculus sim straight line.py and enter. And there you go. You see, the Python file is running. If you want to close the file, you just press X, and that's how you run a Python file with your terminal. Now, if you have Windows command prompt, then it's a bit different. Well, in fact, the only difference is that in Windows command prompt, you don't write this. Once you are in your desktop, you simply write the name of the file. So this would be in Windows command prompt. This one is in Linux terminal and in macOS terminal. So in Linux terminal and macOS terminal, you have to write Python 3 and then space and the name of the Python file. And don't forget the .py extension. In Windows terminal, you simply write the name of the Python file with this .py extension, and then you press enter. And that's the only difference. And now if I want to print something, so let's say that I enter into this file again, and let's say that I want to print this distance array. Then I write here print distance, I save it, I close it, and then if I run my Python file again, then of course I cannot do it like this because I'm using Linux. In Windows command prompt, you would do it like this. But in Linux, I write it like this. And by the way, terminal remembers your previous commands. So let's say that you're in your desktop, and if you press the arrow up, then you get your previous command. You press the arrow up again, and then you get the command before that. So with this command, I run my Python file. I have my animation here, and as you can see, I have printed my distance array. So if I make it bigger, then there you go. This is your distance array. So we write clear, and by the way, there are many commands, both in Linux and macOS terminal and Windows command prompt. You can copy paste files using terminal or command prompt. You can move files from one folder to another folder using terminal or command prompt. You can delete files and install programs using terminal and command prompt. And the thing is that if you get used to it and you do it many times, then you might be faster working in your terminal or command prompt than in the traditional way, where you would enter your folder and then either press Ctrl-C, Ctrl-V if you want to copy paste it, or click the right click and then copy and then paste. And so it's a nice thing to learn to work with terminal or command prompt. And there are many good tutorials on YouTube that I have used to learn about it. And so let's say that I want to enter into my MPC PID Udemy course folder again. So I'm here. Now you already know how to go back, right? CD and then space and 2 dots. However, what happens if I don't put those 2 dots? If I only put CD, then no matter in which folder you are, you go back into your default home folder. And so that's it on the terminal and the command prompt. Thank you very much. Welcome back. In this video, I would like to show you how to install Python and the necessary libraries in order for you to be able to run the simulations in Python. I'll first start with Linux, Ubuntu, and then in the next video I'm gonna do it in Windows. At the time of this recording, the Python version that you should install is Python 3.8.5. The newest out there is 3.9. However, I've checked that, and the libraries such as NumPy and Matplotlib, they don't work well with Python 3.9 yet. I guess it's too new. Perhaps they will later, but not at the time of this recording. So you should have Python 3.8.5. If you have Ubuntu 20.04, like I have it here, then Python 3.8.5 should come by default along with NumPy. You can check the version in terminal like this: Python 3 and then 2 dashes and then version. So you see I have Python 3.8.5. And you can check the version of NumPy like this: Python 3-C, then you put here a quotation mark, import NumPy, semicolon, print, and then you're going to put here NumPy dot, then you have 2 underlines here, and then you're going to put version, then another 2 underlines, and then another quotation mark here. So here I have NumPy 1.17.4. That's what I received by default. These 2 things I received by default when I installed my Ubuntu 20.04. If you don't have Python 3.8, then you can install it with these commands: sudo opt update, then you put your password here, so it will give you some upgrades, and then you will write sudo, which is super user, then opt install software dash properties dash common, then I'm gonna write sudo add dash apt repository ppa colon dead snakes, then slash and ppa. So I'm gonna press enter, and then I'm gonna write sudo opt and then update, then sudo apt install Python 3.8, not 3.9, 3.8. And then to check the version, you write Python 3 dash dash version. And then if you don't have NumPy, you can add it like this: sudo apt install Python 3 dash NumPy. And so to check the version, you will have Python 3 dash C, then quotation mark, import NumPy, print parenthesis, NumPy dot, then 2 underlines, version, 2 underlines, and then you will have a quotation mark here. So that's your NumPy version here. And now you have to get the Matplotlib library as well. At the time of this recording, the newest version is Matplotlib 3.3.3. However, if you want to run all my simulations, then I recommend you to install Matplotlib 3.2.2. You can do it with these commands: sudo apt update, then sudo apt install Python 3 dash pip. PIP is a Python package installer. So you check the version of your PIP. So PIP for Python 3 would be PIP 3, then dash dash, and then version. So here it is. And now you write pip3 install matplotlib. And now if I press enter now, then I should be able to get matplotlib 3.3.3. However, I want to get matplotlib 3.2.2, so I'm going to put here two equal signs and then 3.2.2. And if you already have matplotlib 3.3.3, then this latest command will uninstall it automatically and replace it with 3.2.2. And now you can run the code, but this is very important. You have to run it in Linux terminal or Windows command prompt. Do not use IDEs like Spider or Jupyter Notebook. The animation does not want to work well in there. The most robust way is to run it from terminal or from Windows command prompt. So I have a file here, calculus sim PID train.py, and I want to run it. So in my terminal I will go to my desktop. So change directory or cd, desktop, enter. I can see all my stuff here with an ls command. And so in order to run this file, I'm going to write python 3 and then calculus sim PID train.py. And there you go, it works. So that has been in Linux, and now let's see how to do this in Windows. Welcome back. So let's now try to install Python and its libraries for Windows. So this is the Python website here. The newest version is 3.9. However, the problem might be that at the time of this recording, the NumPy and Matplotlib libraries might not be ready for this version. So in order to run the simulations, we're going to take an earlier release, Python 3.8. And so here you have Python 3.8.6 at the time of this recording. So if you have a 64-bit machine, then you need to choose the 64-bit one. And if you have 32 bits, then you choose the 32-bit options. So we're going to choose the 64-bit web-based installer. And now we're going to open the file. What we're going to do now, we're going to add Python 3.8 to path. I think it's important so that you could run your Python codes from whatever place in your computer. And now let's customize the installation. I personally don't need the documentation file, but you can leave it if you want. The next. Then we're going to put here install for all users. And now, do you want to allow this app to make changes to your device? Yes. And it's installing. And so we have finished installing Python, and we're going to close it now. And so now we have our Python, and let's check if it works. In our case, we will need to launch our programs from command prompt, so I want to test it from command prompt. The animation does not want to work well in IDEs like Spider or Jupyter Notebook. The most robust way is to run it from terminal or from Windows command prompt. So I've opened a notepad, and let's see if I can write a program here. So I'm going to write here print and then hello world, and now I'm just going to save it somewhere. I'm going to save it like this, hello.py. So here I'm going to put all files and hello.py, and there you go. Now I want my command prompt. Here it is. So now I need to find my way to desktop. So cd desktop. Now I'm here. ls, well, ls is not working because it's a Ubuntu thing, but I think in Windows it's dir. And you see you have your hello.py here. So can we run it? We can, and so it works. Okay, but to run our simulations, we need a couple of libraries. We need NumPy and we need matplotlib. So when we installed our Python, then you can see that our pip here was also included, or PIP. So that's Python Package Installer. And in order to install NumPy, we need to make sure that this PIP is the newest one. So we're going to write here Python -m pip install upgrade pip. Okay, so it now says successfully installed PIP 20.3. And now let's install NumPy. I'm going to write pip install NumPy, then two equal signs 1.19.3, and now I have numpy 1.19.3. Now let's check if it works. I'm going to write here Python, and then I'm going to write here import NumPy. It didn't give me an error, which is very good. So this is our code here. Import NumPy as np, and then I'm going to write here print np.py, so the pi value. And so now I'm going to write exit, and then I'm going to run this hello.py file, and it gives me my pi value. So that's very good, because it means that we also have working NumPy here. And now we need to install matplotlib. I would recommend you to install the matplotlib version 3.2.2. At the time of this recording, the newest version is matplotlib 3.3.3. However, if you want to run all my simulations, then I recommend you to install matplotlib 3.2.2. So I'm going to write here pip install and then matplotlib. Now if I run it now, then I will most probably get the newest version 3.3.3, but since I want to get 3.2.2, then I will put here two equal signs and then 3.2.2. Okay, so it says that successfully installed. So I have here this calculus sim PID train, and let's run it here. So calculus sim PID train, and it works. Now it's a little bit slow here, but that's because I'm running my Windows 10 on a virtual machine. At the moment I am a Linux user, so I use Ubuntu, and so in order to make this demonstration I downloaded the VirtualBox machine, and that's why the simulation is a little bit slow. I'm sure it's gonna be faster on your Windows machine. Welcome back. So let's now install Python and its libraries for macOS, and we're gonna use the latest version, which is Big Sur. Let's start with going to the Python website, and now we're gonna go to Downloads, All Releases, and I would not like to download Python 3.9 because I want to make sure that all the other libraries that I'm going to be using, that they are fully ready for that version. And so all my tests have been successful with Python 3.8.7. And so we're going to go to macOS, and we're going to download the macOS 64-bit Intel installer for Python 3.8.7. Do you want to allow downloads on www.python.org? And of course allow. And so I'm going to go to the downloads folder. So here's the installer that I'm going to click on. And so now I have this text. I'm going to click continue. I'm going to read everything. Again, I'm going to click continue. And of course I'm going to read everything. Continue. Agree. And install. And then here I have to put my system password with which you log in into your system. And so it will start installing Python. And so at some point I will have this folder here with these files, and I can just ignore this folder, and here you can see that congratulations, Python 3.8.7 for Mac OS is successfully installed. And now we don't need the installer anymore, so we move it to trash. We can close this folder, and we can close this website as well. And now let's test if our Python is installed correctly. I'm gonna use terminal in order to launch my Python programs. I would recommend you to do the same. I would not recommend you to use IDEs such as Spider or Jupyter Notebook. The animations might not work if you launch your programs from there. The most robust way is to launch them from terminal. And now let's go into our desktop folder. CD desktop. CD stands for change directory. So I have a Python file here, test.py, and I'm gonna open it with the idle. I'm gonna ignore the shell, and I'm gonna go where the program is written. Now, I don't care about the numpy nor pillow right now. I just want to know if my Python is working properly. For that, I'm just gonna write here print hello world and then exit. That will end the program at that point. And so if I close this file, then it's gonna ask me if I want to save it, and I'm gonna say yes. I'm gonna close the shell as well. And then here, when I'm in my desktop folder in my terminal, I'm gonna write Python 3 and then the name of the file, test.py. And as you can see, it prints hello world. So our Python is working. Very good. But now if I go back to our program and then I delete all this stuff and leave the original program, if I save it now and close the shell and run the program now, then I will get an error because I don't have a NumPy library. In your terminal, write cd so that you would get out of your desktop folder and be in your default home folder again. Before we can install NumPy though, we have to install pip. Pip is a Python package management system. For that, we go to Safari, and then we're going to go to this website, pip.pypa, so pypa.io. Here we go to installation. We're going to make sure that we have Unix or Mac OS here, not Windows. And then we're going to come here where you have installing with get-pip.py, and then we're gonna copy this line and we're gonna paste it into our terminal here and press enter. And then you have to go back to the website and copy this link as well, and then you can paste it here in your terminal. And before you press enter, you have to put here Python 3, so a small modification, and then you press enter. And now it started installing it. And now you have successfully installed the Python package management system, pip. And now you can write pip install numpy 1.19.3. And now you have successfully installed NumPy 1.19.3, and now you can write cd desktop. Now you enter into your desktop folder. Now before we run our file, let's enter into our file again through idle. At this point we don't care about the pillow library. That's the library that you need when you work with images. At this point we're going to ignore it. We just want to test NumPy. And so we're going to write here print np.py, and then we're going to write here exit. And so if our NumPy works, then we should get a pi value. So when we close it, then it asks us to save it. We're going to click yes. We're going to close the shell. And we're going to write Python 3 and then test.py. And as you can see, we get our pi value. And that means that our NumPy library works. In your terminal, write cd so that you would get out of your desktop folder and be in your default home folder again. And now we have to install matplotlib. For that, we write pip install matplotlib, 2 equal signs, and then 3.2.2. In order to avoid any kind of complications, I would ask you to install matplotlib 3.2.2 and not 3.3 series. And so we have successfully installed our matplotlib, and now we write cd desktop because our Python file is in the desktop. And so if we run an animation file here that requires matplotlib, then you can see that the animation is working. Of course, it's very slow, but that's because I'm using VirtualBox. And that's it. Now you have all the necessary libraries in case you use the Mac system as well. So I'll see you in the next video. Thank you very much. Welcome back. In this video, I will explain to you the code for the PID train. So let's go through it together. The first thing that I'm gonna do, I'm gonna import all the necessary libraries that I need. I need NumPy, I need matplotlib, I also need this random library because I want my cubes to appear randomly on the screen. So it has appeared here, and now it has appeared here. And so there is a random function that will take care of that. And then we define some inputs. First of all, we have trials. Here you decide how many times the train needs to catch the cube. So if I put 2 here, then the train needs to catch 1 cube and then another cube. And then the animation will be over. If I put here 20, then there will be 20 different cubes sequentially. You catch one of them, then you catch another one, etc. up until 20. Then here you have your inclination angle. So I have here pi over 6, so that's 30 degrees. So that will give you this kind of inclination. But if I want to make it 0, then I can just multiply this angle by 0, and then my inclination angle will be 0. And there you go. No more inclination angle. Then this g value is the gravitational acceleration on the Earth. This is the mass of the train. And here you have your 3 PID constants. The proportional one, the derivative one, and then the integral one. In this variable, trials global, I store how many trials I have. And the reason why I do that is because this variable trials, it will decrease by 1 in each trial. And I will need that in the future in my simulation loops in order to know which trial loop I'm at that moment. But this variable, it stays constant, and I will need it later in order to create the amount of frames for the animation. Then here what you see is a function. The function is called setXref. It takes in the inclination angle and it gives you a random horizontal and vertical position. So at some point in the code, in fact it's right here, I enter into this function. The purpose of this function is to give me a random position for the cube for each trial. So this is a random horizontal position. The function here is random.uniform, and then I have 2 numbers here, 0 and 120. It means give me a number between 0 and 120 using this uniform probability distribution. As you know, You can also have a Gaussian distribution. So if this was 0 and this was 120, then in most cases I would get my cube somewhere in the middle. But a uniform distribution, it will give you an equal probability for the entire range. And the reason why I have 0 and 120 here is because here on the horizontal axis I go from 0 to 120. So I want my cube to appear horizontally randomly. But then I also want a random vertical position. But here I have to do it differently. I want to tie it up to my inclination angle. Essentially, if this is my rail here, and so here I have 0, and then here I have 120, then I define some kind of region in the vertical direction where this cube could randomly appear. And then of course if I combine it with a horizontal region where I used uniform probability distribution from 0 to 120, that means that my cube will appear randomly somewhere in this area, inside this rectangle. But what if I increase my inclination angle? And now my rail goes like this. And so my cube appears randomly here. Then obviously I will not be able to catch it, right? So what I want to do, I want to tie this vertical distance to this point here. So let's say that if my inclination angle is 0, and then I say that, okay, vertically give me a cube in between 20 and 40 meters. So this distance here is 20 meters. But if I have some kind of inclination angle here, then it would be like this. Give me a cube vertically in this region. So now the distance here would be 20 and the distance here would be 40, like this. And so my cube will appear somewhere in this region. So you see, I tie this vertical distance to the corner of this rail because this is my initial position. That's where I always start from. And so to achieve that, I do it here. Here I have 20 plus 120 times tangent of the inclination angle. If this is my inclination angle and this horizontal distance is 120, then 120 times tangent alpha will give you this distance here. That's your 120 times tangent alpha. And then I add 20 here, so I'm here. And in reality, I also add plus 6.5. That's because this cart here that I have, it's actually shifted up by 6.5 meters. So in reality, to be more precise, the 20 meters goes from this point here up until this point here. So that's actually your 20 meters. So I connect this region to this point here, but from this point to this point, it's actually 20 plus 6.5. And then here you have another point, and that's actually 40 plus 6.5. Because 40 would be from here. From this point to this point, that would be 40. And that's what I'm doing here. And so I get my random x and y position, and then I return it. Next, I define my time interval, 0.02 seconds. Then the beginning of time is 0 seconds. The end of time is 5 seconds. And here I create my time array. I say that I go from 0 seconds to 5 plus dt seconds. So in here I have 5.02. Why? Because in Python this number is included, but this number is not included. So if I get here 5, then my array will be like this up until 4.98. And that's it. Because the last number here is not included. That's if I only had my t-end. But if I have my t-end plus dt, then I will have here 5.02, which is not included, but my 5 will be included. And then this dt is just the interval. It's this one, 0.02 seconds. And so I create my time array. Next, I have to define my force of gravity, which is minus mass times g. So the force of gravity points down. Next, you see that I'm defining a lot of zero arrays here. When you simulate, then you have to deal with arrays. And there are several ways you can do it. You can start with an empty array, and then you can just put your data in, and then over time grow your array. That would make your program very slow. If you already know in advance how big your time array, or maybe X array or Y array will be, and you should know it because you have your time array, that means that for each time value there will be some kind of value for X, for Y, for velocities, for accelerations. For all these variables there will be some kind of value for time equals 0, for time equals 0.02 seconds, etc. So you already know how big these arrays will be in which you are going to be storing all your data. In that case, it is much better to define a zero array with the right sizes. You predefine an array that has the same size like this time array. The only difference is that at the beginning you only have zeros there. And then as you go through your simulation loops, where needed, you replace your 0 with some kind of number, whatever it is. And that kind of programming is much faster. And where possible, you should do it like this. Otherwise, if you start just growing your vectors and matrices, then it will become very computationally heavy. And that's what I'm doing here. I'm predefining my arrays. For example, I have here displacement rail. Well, that's this distance from here up until whatever point along this rail. And of course, if my inclination angle is 0, then my displacement rail would simply be my horizontal displacement. But if I have an inclination angle, then it goes along the rails. And so for each time value, I will have some kind of value here. But at the beginning, I define it as a zero array. And you can see that it has two dimensions. It has trials, and then it has length time. Why do I do that like that? Well, that's because, remember, I have more than one trial. So my displacement rail array, just like all other arrays in this simulation, they will have here trial 1, trial 2, trial 3, and then here in the column you would have your time. This would be your time dimension up until very end. And so when you have your animation, and first of all simulation, and then you animate the data, then you see that once the first trial finishes, then the second trial starts. Alright? And so, let's see if it catches it. Very good. So what just happened was that we first went through the first trial, through time, and then we went through the second trial, through time. And then if I have more trials, then I will have more rows here. And I do that for displacement rail, I do that for the velocity of the rail. I want to know how fast I go in this direction or in that direction. I also want my acceleration vector in this direction or in that direction, like this. That's here. Then I have these position X train and position Y train arrays. Well, all that really means is that I decompose this displacement rail into 2 dimensions. So if this is my displacement along the rail, well then this would be my x position and this would be my y position. Then I also need an array for my error, error dot, and error integral. I need all these values to be stored somewhere, because when the time comes, I take those errors and e dots and e ints out of these arrays and then I multiply them by my PID constants. Then these 2 arrays, they are for the cube. But you see, they all have the same sizes. They all have the number of trials as rows and time lengths as columns. Because you have a value for each time element, and then since you have multiple trials, then the total amount of elements that you have is the amount of trials times the amount of elements that you have in your time array. So here you have your x and y position values for your cube. That's where you store them. Here I decompose my gravity vector and I only obtain the tangential component. I don't need the normal component of my gravity vector. And the reason is very simple. If this is my force of gravity, and then I decompose it like this is my force of gravity normal, and this is my force of gravity tangential, and this is the inclination angle that I also have here, then this normal component will be automatically cancelled by this normal force here. Just like when you stand on the ground, you don't accelerate downwards. Why? Because your force of gravity is equal to the normal force, like this. In this case, however, the normal force that you have is equal in magnitude and opposite in direction to the normal component of your gravity force. So they cancel out. Their net result will be 0. So the only component that really matters is this tangential component. In fact, if you don't apply any other forces, and we neglect the friction force and then the air resistance force, in other words, the drag force, then this tangential component will make this train slide down. That's why I only extract this component, the tangential one, and I forget about the normal component. To extract this tangential component, you multiply your gravity force times sine alpha, and that will give you your tangential component for the force of gravity. And that's what I do here. Then I have to define my initial position in the x and y dimension. Essentially, I'm saying that start from here. And here, this is my initial displacement rail. So my initial displacement rail value is this distance. And in order to get this distance, it's just the Pythagorean theorem, right? You take the horizontal component, which is 120, then you take your vertical component, let's put it y, and let's just say that the horizontal component is x. So to get this distance, it's very simply x squared plus y squared and then square root. And that's what I'm doing here. And then I say that my initial velocity along the rail and my initial acceleration along the rail, they are 0 meters per second and 0 meters per second squared respectively. And then here I take my initial position in the x dimension and I assign it to another variable, because this variable will be changing. But I need this very initial variable later on for the animation purposes. And I need these variables to keep track of my trials, whether I'm in my trial 1 or 2 or 3. And now this is where the simulation starts. Because of the fact that I have more than one trial, I have trial 1, trial 2, trial 3, etc. You can expect that I have 2 loops, one loop inside another loop. So loop 1 is to run the trials, and then the inner loop That's to run my simulation through time per each trial. And that's exactly what I have here. My outer loop will be while, and then this would be my inner loop that simulates my simulation through time. You can see that while trials is bigger than 0, run this loop. What does it mean? Well, if at the beginning I say that my trials is 2, and let's say that it's 5. If my trials is 5, then 5 is greater than 0. Then I enter into this loop, then my inner loop starts, that simulates one trial through time. My inner loop finishes here, and then I have some stuff in the outer loop in the end as well. And in the very last row, I have trials equals trials minus 1. It means that if my trials has been 5 so far, then now it will be 4. So 4 is still greater than 0, so I run it again. Then it becomes 3. I run it again, 2, I run it again, 1, I run it again, and then it will be 0. 0 is not greater than 0. Therefore, this becomes false, and I do not run this loop again. Now, when I enter into my loop at the very beginning, then here I take my random x and y positions for my cube. This here simply means that if my trials at the beginning is 5, and then I had assigned this variable to this variable right here, then 5 minus 5 would be 0. So it would be my 0th time. Remember, in Python you should start counting from 0, not from 1. Usually we count from 1. But the thing with Python is that when you have some kind of array, and let's say that you have 3 elements here, 5, 6, 7, if you want to get this 5, then you have to write t and then bracket 0. Not 1, but 0. Then you will get this one. T1 would give you this one. And then t bracket 2, it will give you this one. In MATLAB, it's different. In MATLAB, you would put 1 here, 2 here, and 3 here. But in Python, you count from 0, then 1, and then 2. So this would be here 0 row, 1, 2, and then in terms of columns, 0, 1, 2, 3. And then later, when my trials is 4, then 5 minus 4 would give me 1. Then when my trials is 3, then 5 minus 3 will give me 2. So that will tell me that I'm in this outer loop already for the 3rd time. 0, 1, 2, it means for the 3rd time. And then here, I give x and y array values for my cube. My x value will not change. You see, my cube only changes in terms of y. And when you have a new cube, then again, it only changes in terms of y. It doesn't move diagonally. So my x stays the same, and then my y value, well, that's just the initial y value minus this gravitational acceleration divided by 2 times time squared. Well, that equation just comes from physics. So it's your initial position minus 1/2 times g times t squared. And of course, here I assume that my initial velocity is 0. So the distance covered in the vertical direction would follow this rule. Then we'll look at these variables a little bit later. And now we start with our inner loop. We start simulating through time per each trial. At the very beginning, when my I equals 1, I assign my initial values for displacements, then velocities, accelerations, to these predefined 0 arrays that I had defined right here. So you see times, and that's why I needed this one here. Because at the very beginning, when my trials was 5, and then trials magnitude was also 5, then times was 0, so I had 0 here. That means that I said that I want to be in this row, the 0 row. Then, In the second trial, my trials is 4, 5 minus 4 is 1, and then I will have 1 here. So I will have this row here. And then here I give you the position of the column. So the very first column, 0 column. Here I assign my initial displacement, position in the x and y direction, the velocity, and then acceleration values. That's at the very beginning. I don't do that when my I is greater than 1. I just need to do it at the beginning. Then I compute my horizontal error, the x position of the cube minus the x position of the train. Notice I'm using the x position of the train, not the displacement value, but the x position of the train. So if my cube is here, then what I want is this horizontal position. That would be my error. And then here I compute the time derivatives of my errors for my derivative part in my PID controller, but not in the first inner loop. Why? Because in order to compute my error derivative, and not only error derivative, also my error integral, so in this block I do both, I compute my error derivative and the integral of my error over time. But in order to do that, I need error values from 2 samples before. So you can see from these indices here that if I enter into this block in the first iteration, then I will have an index error. Because then, for example, when I have 1 minus 2, I would have minus 1, which in fact would not give me an index error, because in Python, if you have minus 1 here, then that means the last element of the array. So it will probably not give you an error, but it will give you wrong values. Instead of values from the beginning, it will give you values from the end. But then in other programming languages, it would give you an index error, because you would be asking an element from an array from the position that does not exist in this array. And the reason why I use indices I-1 for the errors and error dots and then error integrals is because later on, when I compute my applied force with my PID controller and then compute the net force where I add my applied force to the tangential component of my gravity force, and then when I take this net force and divide it by the mass of the train, then this I index is used for acceleration along the rail, for the velocity along the rail, displacement, position x and position y. And then here in this block, I want to enter here in my last iteration inside my inner loop. Because remember, I first defined all these arrays as 0 arrays. But naturally, because of the fact that I have indices I-1 here, I will never reach the last array element here. But I don't want the last array elements in these arrays to be zeros. So I just take the penultimate values, the values from one sample time before, and then I put them into the last elements of my arrays. And so once I have my errors, error dots, and then error integrals, then I can take my Kp, Kd, and Ki values and compute my applied force. Then you know that the tangential component of the gravity force is always in this direction, it never changes. But then the applied force can be either in this direction or it can be in that direction. And depending on that, you will either have a huge net force in this direction or a smaller net force in that direction. You just add the tangential force of your gravity to your applied force. And then you will get your force vector that goes along the rails. You divide it by the mass, and then you get the acceleration vector along the rails. Then here, in order to get the velocity vector along the rails, I perform this trapezoidal integration. In order to get the displacement along the rails, I again perform the trapezoidal integration, but now with velocities. Before it was with accelerations, now it's with velocities, like this. And then, to obtain values for my position x and position y, it's just simple trigonometry. I take the displacement value along the rails times cosine, so that will give me this one here. If I take this red vector times cosine alpha, I will get my position x. And then if you have this red vector times sine alpha, then you will get your position y. And that's what I do here. Now, of course, you can see that once the train catches the cube moves with the train. Like here, you see, now the cube moves with the train. To achieve that, I do it here. And let's see how I do it. You can see that I have two if statements here. Let's for now forget about this one. And let's focus on this line here. Essentially, with this first line, I'm saying, if this is my train, and let's say that I have some kind of center line, and this is my x position. So imagine that I have my cube here. And so you have your first condition. If position x of the train minus 5 is less than position x cube plus 3, then this part of the conditional statement is true. So this would be from position x, and this would be position x minus 5, then this would be position x of the cube, and this would be position x of the cube plus 3, right? Because our convention is that x is positive in this direction. So here I have this sign here. So this value needs to be less than this value, which means that this wall needs to be more to the left than this red wall. This blue wall needs to be more to the left. Then you can see that indeed you can catch the cube. The second conditional statement says position x of the train plus 5 needs to be greater than position x of the cube minus 3. Well, this is position x of the train plus 5. And let's now assume that our cube is here. So this is position x of the cube minus 3. It's this side here. So if this blue side is greater than this red side, then the condition is also true. And so I have an AND statement here, which means that both of these conditions must be true. And they are. If my cube is here, then this blue wall on the right is definitely greater than this red wall here. What I have to worry about is this edge here and then this edge here. And the same logic applies to the other side. So that's how I check if I'm able to catch this cube horizontally. But I also have to take care of the vertical part. What if this condition is true, but my cube is somewhere here? Well, then it's too late, right? Or maybe my cube is somewhere here. Then it's too early. And so for that, I have this second if statement. And here I essentially say this lower side of the cube and this upper side of the cube, they have to be in some kind of threshold. So I define two thresholds here, like this. If my cube is inside this threshold, then it's true. If at least one edge, let's say the upper edge, is out of this region, then the condition is false. These numbers here, they are obtained through trial and error, because in this section I didn't really think about the dimensions of this train or the dimensions of this cube. Actually, when I run my simulation, then to me what really matters is this center point here, that's for the train, and then this would be the center point of the cube, and then here as well. And so from Python point of view, these are just lines with some kind of width. And then I gave them some kind of width, and so these lines are wider. But there is no exact science between these kind of dimensions here. So all these numbers here I obtained through trial and error. When the animation was good enough, then I kept these values. But the PID controller only works with these center points. The PID controller does not care about these dimensions here. So for the PID controller, the error between this train and this cube would be this one. You would take one center point and then you would measure the distance to another center point. But in order to make it visually appealing, I wanted to create an animation using Python animation tools, and then I had to do some trial and error with these dimensions. But that's essentially the logic. I defined some kind of channel here, and if my entire cube fits into this channel, then the condition is true. Then actually that means that I have caught my cube. So remember, there are two conditions. One was for checking the horizontal distances, where I worked with these edges. That was this condition. And the second condition, that's when I check if my cube fits into this channel that is fixed to the train. So if the train goes down, then this green channel would go with the train. And so when both of these conditions for the horizontal and vertical motion are satisfied, then I enter into this loop, and then I make my win true. At the very beginning, my win is false. It means that I haven't caught my cube. Then, once I catch my cube, I say that win equals true. Why? Because the next time I run my inner iteration, I don't want to check all these conditions again. I already know that I had caught my cube. And I know that because of this win variable, which is true. And this one as well. So if win equals true, then that means that I had already caught my cube. Then here you can see that since I have caught my cube, then whatever values I have in the arrays for my cubes, for the x and y position, I overwrite them with the values that I have in my arrays for the train. That will make the cube move like the train. So it will stop falling, it will simply move along, you see? Okay, and then the reason of this block is that if I don't have this block, then I will not be able to compute this one. I call this one change. Then I know that this cube needs to stop here. If I don't have this change, then my cube will magically appear here, because the central lines of these two objects would align with each other. So I have taken away the change, and now look what's going to happen. You see? The cube and then the train, their center points simply align with each other. It's better to see with an inclination angle. You're about to see it now, you see? And there you go. And you'll see it again, and as you can see, the two center lines would align with each other. And that's why I compute this change, and then I have to put here minus and then this change. And then this is in order to keep that cube together with the train in the y direction. And again, this number here is through trial and error. And that's the end of the inner simulation. Now you can see that once the cube is caught, then when the new trial starts, you don't start from the beginning. You start from your last position. And that happens thanks to this block here. Because here what I do, I take the last values from these arrays for my current trial, and then this would be the last column, and these last values for this trial, for all these arrays, will be assigned as initial values for all these variables for the next trial. So for this trial, I take my last velocity value, I make it the initial velocity value, I decrease my trials number, that's the end of the outer loop, and then I go back up, and then I start with my new outer loop with my new trial. I get my random x and y positions for my cube, and then I again create arrays for my cube in the x and y direction. I make my win false, and then once I start with my inner loop, the very first iteration, I assign my initial velocity as the first value for this velocity array, but for the new trial. But this initial velocity value, it got updated before here. The initial velocity value for the new trial is the last value of the old trial. And that's how I make sure that when the new trial starts, then my train doesn't start from the beginning. And finally, this delta, well, that's for this block here, that's to compute this change. Once I've caught my cube, then I don't have to compute that change again. So I make my delta 0, then I don't enter into this block again. But then, when I start my outer loop again, I make my delta 1 again, because now there is a new cube that I need to catch. And that's the end of the simulation. This is where the simulation ends. This is where all the data generation ends. The rest is just Python animation. All this is just to create those animations with Python animation tools. The main function responsible for Python animations is this one here, func animation. Now, Python animation, it's a topic in itself, and it requires a separate course to really explain to you all the different nuances here. Nevertheless, I'm going to give you a quick overview of the general idea of Python animations. Remember, animations is not simulation. Simulation is what we did here. Here we computed all our data. Here we applied our PID controller. Here we computed our positions, velocities, accelerations. Essentially, we generated our data here. So that's simulation. Now, since we have all this data, the question is how we are going to present it to other people. We can either plot it or we can animate it. And of course, animations look cooler. And in Python, you have certain tools to do that. In the library called matplotlib, you have a function that we usually put in the end of the animation, which is right here, func animation. One of the arguments is fig. That's the name of the figure that you use for animation. This figure here, it's called fig. And you define this figure called fig right here. You see, here you give it a size, resolution, dots per inch, color, and here you have grid spec. Grid spec 4,3 means that if this is your figure here, then you have chopped it like this into these equal rectangles. And with these grids, you determine where your subplots will be and how big they will be. For example, this big subplot here, it occupies these rectangles. That's this big subplot. Then you have one subplot here, one subplot here, also one here, here, also here, and here. As you can see, you have here a subplot, then here one, also you have one here, and then here as well. So in total, this figure is divided into 4 by 3 rectangles, 4 rows, and then 3 columns. And so the way you assign those subplots to those positions is like this. Subplots, they also have names. For example, I called the big subplot AX main. This big subplot, its name is AX_main. And then I write fig, which means that I'm talking about this figure here, then dot, and then a function called add subplot. And then here, GS, which is the name of this action here, this GS tells Python that, okay, this figure has been chopped like this. And out of these rectangles, take 0, 1, and 2 rows, and then 0 and 1 columns. And that's how you get your big subplot. And then these functions here, they are there to design your axis. So here I say that my x values range from 0 to 120 in the x direction, and I also want my y dimension to be that big. Essentially, I want to go here from 0 to 120, and also from 0 to 120 till here. And then x ticks, they essentially determine the intervals of these numbers here. And so if we go back to our animation function, that's our figure with all its properties. Then this update plot, it's a name of another function, and it's the function where you can design your animation. So if you go up, then this update plot function, it starts from here. So this function is continuously called. And now this num variable is very important. Every time you call this function, this num increases by 1. So at the beginning your num is 0. Then it's 1, 2, 3, 4. The total amount of times that this function is called is determined by this frame amount. As you know, a video contains of frames. It's like having a lot of pictures that you change very fast and then you see it as a movie. So you need to define your frame amount, and then if you go down, then you put your frame amount here. Then here you have interval, which means that you're changing your frames every 20 milliseconds. Here you can write if you want to repeat your animation or not when it finishes, and this option makes your animation smoother. It optimizes the pixels that it draws on your figure. And then of course you need this function in order to see all that on your screen. And so the way animation in general works is that you need to think in terms of objects. So let's, for example, take this blue line for the horizontal error. This horizontal error, this line, this blue line, it's an object. Like everything else that you see here, it's an object, you see? And that object needs to be created somewhere. And I create it here. I call it E_f. Now it's also very important that you put a comma here. That's a Python thing. If you don't put a comma here, then you will get an error. But the name of this object, of that blue line that you saw, it's called E_f. We give it a color, blue. We give it a line width, which is 2. And these two empty arrays, they are reserved for x and y values. And then here you say that this object, E_f, is in this subplot. This subplot is also an object and it has a name. It's this one here. This is your subplot. You called it AX1H. And then in this subplot AX1H, you create an object that you call E_f. Then this function here, funcAnimation, calls this other function update plot. And so you're inside your function, and then here you see that this is your E_f. Then you put dot set data, and look what's happening here. Essentially, you're starting to extract something from 0 up until some kind of value. And this value depends on num. And remember, every time this function is called, num increases by 1. I'm going to give you a simpler example. Say that this is our time array, and it looks like this. Now what happens if I write t bracket and then 0 colon and num? At the beginning, num equals 0. So what you have is this, 0 colon 0. 0 colon 0 will give you an empty array. So you will not extract anything from this time array. Then the next time this update plot function is called, from this function funcAnimation, then your num variable becomes 1. In that case, you have 0 colon 1. So you will have 0 here because Python will extract this one, but it will neglect 1. In other words, here you will have t bracket 0. In other words, you will extract this element. Then that update plot function is called again, and your num becomes 2. 0 colon 2 would give you an array 0 and 1. So instead of this, you will extract this, and then you will also extract this. So you will extract 2 numbers. Then num becomes 3. You go from 0 colon 3, then you will end up with an array 0, 1, 2. Then this t bracket 0 colon num, it will extract 3 numbers. And then it will extract 4 numbers. So every time it extracts more and more numbers until you reach the very end of your array. And it does the same thing with your error array. Say you have error 1, error 2, error 3, etc. If you extract one value for time, you will extract one value for error. If you extract 2 values for time, you will extract 2 values for error. 3 values for time, 3 values for error. And that's why in the animation what really happens is that if this is your time axis and this is your error axis, then in the first frame your object e underscore f that we have here and that we had defined in the past here, in the very first frame there would be nothing, emptiness. In the second frame you would see a point. In the third frame you will see 2 points. In other words, you will see a short line. Python will not show you points, it will show you a short line. Then in the fourth frame your line becomes longer. In the fifth frame your line becomes even longer. So think of it like this. Here you have emptiness, here you have this, here you have this, here you have this, here you have this, and if you change that every 20 milliseconds, then what you will see is a line that becomes longer and longer. And that's the logic with pretty much everything here, but with small modifications. But that's the very idea of Python animations. You define your objects and then you use this funcAnimation function to jump into this update plot function where your num variable increases all the time, and then you put your objects inside this function where at different frames you extract different elements from your arrays, from your time arrays, displacement rail arrays, etc. And that's how you animate in Python. But like I said, to really explain everything, it really requires a separate course because you do have a lot of nuances there that you need to take into account. So that's it on this PID train explanation, and I'll see you in the next video. Thank you very much. Welcome back. I've decided that I'm also gonna create a small video about explaining this code file for the water tank. So let's go through it together. This radius here, that's the radius of the tank. So you can imagine that your water tank is cylindrical. So this is the radius of the circle that is on the XY plane. So in the simulation, you see that the water tank is like this, but actually your water tank is a cylinder. So it looks something like this, and so here you have your radius. So this radius here, that's your 5 meters. That's this one here. Then this here pretty much says that the minimum of volume of water that you can have in the tank is 0 cubic meters, which makes sense. And then you also have the maximum volume that your water tank can have. That's your 100 cubic meters. They do not tell you how much water you actually have in the tanks. It's just, it shows you that, okay, this is the minimum value, and then this is the maximum value. And the reason why I do that is because in the simulation, you see that you have here 0, then you have here maybe 10, and then 20, up until 100. So these values here, they are my volume values. So if this is the level of my water here, well, that's just means that I have 20 cubic meters of water inside the tank. And so this bottom equals 0, that's just to establish this level here, the 0 level. And then this final volume, that's just to establish this level here, the maximum level. So d volume equals 10, that's the change of volume on the vertical scale. So it's essentially this difference here. That's your d volume. Alright, that's this one here. And so this width ratio here, that's necessary for the horizontal axis. So here you see the simulation, and that width ratio essentially determines that, okay, here you have 0, then here you have 5, and then here you have -5. So it governs this horizontal axis. Then your dt is your time interval. So it means that you have a time vector, and then this time vector with this 0.04 time interval would be something like this. 0, then 0.04, then 0.08, and then etc. Alright? Up until you reach your final time, or t sub end. Then this is the initial time of the simulation. So you start from 0 seconds, and then you finish at time equals 50 seconds. And then this is frame amount, and that's for the animation. In the end of this code, in this section here, you determine the parameters necessary for your animation. And one of the parameters is frame amount. So you can think of it like a movie. A movie consists of several frames, or actually there are many frames, kind of like snapshots in time, like pictures. And then you change those pictures very fast, and then you have a movie. So here you determine how many pictures you have. And then, well, here you create your time vector. You go from 0 up until 50 plus 0.04. And the reason why I have to put it like this is because, remember, in Python, the last number here is not counted. So if I put here 50, then I'm gonna go from 0 till 4.96. So I have to put here 50.04 in order for the last time element to be 50 seconds. And then this is your density water, 1000 kilograms per cubic meter. And then these are your proportional constants for your first, second, and third tank, because it's your proportional controller, right? So these are your proportional constants. then this is the initial volume of your first tank. So if your initial level of water is 30 cube meters in terms of volume, well then that just means that at time equals 0 seconds, this would be your water volume. And then this is the initial water volume reference value, so 70 cube meters. That's where you want to be. So I can say that, okay, this is my initial volume reference value, which is 70 cube meters. And of course, this is not up to scale. And then here, it's the same thing, only for the second tank. And then also here you have the same thing, but for the third tank. Now, your initial true volume and then your initial reference volume, these were your initial values, but they will change as a function of time. So, in order to keep track of all those numbers, you need a vector for them. So for the first tank, you have your 0 vector that has the length of the entire simulation. You see, len t. You will have a vector containing all these elements, and inside this vector you're going to be storing your reference values as a function of time. And the same thing with true values. You create a vector in which you're going to be storing your true volume values. And here you insert the initial true volume as the initial element of the vector. So you see I have the 0 here, and that's my initial volume, which was defined here, 30 cube meters, and that's going to be the first element of this vector. Then you also create a vector for the error, and the amount of elements that you have in this error vector will be equal to the length of the time vector. And since this one is a 0 vector, then if you take the 0 vector and then you multiply it by this proportional constant for the first tank, then you will also have a 0 vector here. So this 0 vector here, that will be the place where you're going to be storing your mass flow values, so your control input values. And the same thing for the second tank. In the third tank, it's a little bit different, because in the third tank, I define my reference values for the entire simulation. So you see, I have this function here, and then I take this t, which is a vector that goes from 0 seconds till 50 seconds with this 0.04 interval. And so I will get a reference vector for the third tank, and then the elements will depend on the time values and this function in general. And you see this variable here, that's this variable here, 50. In other words, in comparison to other tanks, here you don't create a 0 vector for the reference values where you're going to be storing those values in the future. Here you create a reference value vector right away. And then everything else is the same. And then you start the simulation. Not the animation, but simulation. Animation comes later. Animation is the part that creates this movie so that it would be fun to watch. But then the simulation, that's actually computing the values and going through the control loops and etc. So here in this for loop, you see that your I goes from 1 up until the number that is equal to the length of the time vector. So the length of your time vector is here, 1251. But since the last number is not counted, so your I will go from 1, and by the way, the 1 is counted, so in Python the first number is counted. So if it's 1 here, then your I will be 1. But then if it's 1251 here, then the last I that you will have will be 1250. And so if your I is less than 300, well, then you determine your reference value vector for tank 1 and 2 for this region if it's less than 300. So basically you're saying that if your I is less than 300, then the reference value for the first tank will be this one here, which was this one here, 70 cube meters. It means that it's constant. And then you have this second tank, and here the reference volume values will not be constant. They will be dependent on time. You see, here you have your time vector, and then here I put this I here. So every loop I will be extracting some kind of element out of this time vector, and so I will have a different number here, and so I will have a different reference value for tank 2. But essentially you can see that this is a linear function with an offset. So this is like y equals a times x plus b. Only now instead of x you have time. And instead of b you have this initial reference value for tank 2 water volume. And then this a here, that's your 3. You see, that's your 3. And then your y here, that's this one here. So you take your vector that you had previously declared, you made it a 0 vector for storing reference volume values, and now you store the volume values inside this vector. And then the same thing happens if your I is less than 600 but greater than 300. Because if your I is less than 300, then it will never reach this block. It will always enter this block first. But then if it's greater than 300, then it will skip this block. But if it's less than 600, then it will enter this block. Then if it's greater than 600 but less than 900, then it will enter this block. And if it's greater than 900, then it will enter this block here. And essentially these blocks, they tell you what the reference values for water volume are. So you see that here it's first 70, then it's 20 cube meters, then it's 90 cube meters, and then it's 50 cube meters. That's for tank 1. But for tank 2, I have a linear function here with an offset, and then it continues here. So you see here now I have another equation for tank 2 for its reference values, and then here as well. So if you see, then this is your reference value here for tank 1, 70 cube meters, and then it changes to 20 cube meters, and then it changes to 90 cube meters, and then it changes to 50 cube meters. But you see, for tank 2, the reference value follows a function, a linear function. And so here, when it starts going down, then that's when you enter this block here. And so you see that your reference values here, they follow a linear function with an offset. And then in tank 3, you have another function for the reference values for tank 3. You see, it's a very chaotic sinusoidal function. And so here it's the same thing. That's when you are equal to 900 or greater than 900. So these were all for the reference values for tanks 1 and 2. Essentially here, what you've been doing, it's what you did here with tank 3. In tank 3, you determined your reference values right away, but then in tank 1 and 2, you first created 0 vectors, and then here you would fill in those 0 vectors, creating some kind of reference value vectors. And then here you compute your errors. So your reference value vector at certain I minus 1 minus the true value in the volume tank at I minus 1. And then here I compute my control inputs. You see, I have my proportional constants here, and then I have my errors, and then I compute my control inputs. And then, through this numerical integration that we have studied in this section, I compute new values for the volumes in tank 1, tank 2, and tank 3. They are my new water tank volumes. And then when I start with a new loop, then I will compare these values to the new reference values. And so this loop here will go back and forth until the end of the simulation. And that's the end of the simulation. Starting from here, I start with the animation. In this animation, I have a special function here called update plot. That's a feature of matplotlib. And then it has this special variable num, which is also a feature of matplotlib. And so this num variable, it will run from 0 up until the amount of what you have here, frame amount. And so this num variable will be like this. It will be 0, then 1, then 2, up until the number that you have for your frame amount. Okay, till here. Now, the thing is that what can happen many times is that this num variable at the beginning will be 0, and then again 0, and then it starts counting 1, 2, 3 until frame amount. That's a feature of matplotlib, and I don't know exactly why they did that, but perhaps there is some kind of reason for that. I don't think that it's a bug or something. So at the very beginning, you're gonna skip this function, and then your program will move here where you will define your figures, and then you define your objects. So what you see here, it's a figure full of objects. For example, this red line is an object, this one, and then also this blue area, that's also an object. And then these lines here, they are objects. And so I define them here for tank 1, and then for tank 2, for tank 3, and then also for this lower graph. And by lower graph, I mean this one here. So I define all these objects there. So for example, this blue line here, it's this object here, TNK sub 1, so tank 1. And then your program comes here, and then here you say that, okay, I'm working with this figure fig, which is this one here. Then I have to go to the function called update plot. That's this function here. Then here I tell you how many frames I have, so my frame amount. Then this interval, that's how fast I go from one frame to another, so 20 means 20 milliseconds. Then repeat equals true means that when your animation is over, what will happen then? If it's true, then the animation will start all over again, but if it's false, then it will not start again. And then blit equals true, that's also a matplotlib feature. I've tested that. It makes the animation more efficient. It deletes some unnecessary pixels, so it determines what pixels are necessary and what pixels are not necessary, and then it deletes the unnecessary pixels. I think it does that. But if you put here false, then your animation will not be that nice. And then after that, you go into this function here. And so this part here, this is like a safety feature. So I want to avoid a situation where my num is bigger than the size of a vector. So let's say that if I have 10 elements in a vector, so if that's my vector here, and then I start counting from 0 and then up until 9, then in total I have 10 elements here. But I start counting from 0. That means that the last number that my num can be is 9. So if I have my vector here and then I put 9 here, or num, which is 9, in this example, then what's going to happen is that I will extract this element out of the vector. So actually it doesn't have to be a 9. It can also be an 8 or 85 or whatever number you have here, but if your num equals 9 and then you put this 9 here, then you will extract this element here and then you will have, for example, 85 here. But what if for some reason num equals 10? So if I put 10 here in the index, then I will get an error because there are no more elements in this vector. And so here I essentially say that if my num in this particular example is 10, then subtract 1 from it and make it 9. So that's the purpose of this section here. And well, here I simply animate things. So this is for tank 1, this is for tank 2, and this is for tank 3. And so for example, let's take this blue line here in this subplot. The object for this blue line is this one here. And so here I say this blue line set data, then this is for the horizontal axis here, and then this is for the vertical axis here. So let's say if my num equals 15, for this example, let's say that my num equals 15, then that means that I have 15 here, right? Instead of num, I could put here 15. And then instead of num, I could put here 15 as well. So from this time vector, I take the elements from 0 up until 15, and the same thing from this volume tank 1 vector that I got from my simulation. It's this one here. So from this vector, I take elements from 0 to 15. And 15 will not be counted here because in Python the last numbers are not counted. So you will have 15 elements that you will take out of your time vector and your volume tank 1 vector. But those 15 elements, they will start at 0 and then they will finish at 14. And then if you do that, then you will create a line here. Then the next time you call this function, your num will be 16. So you put here 16 and then you put here 16. And then you will have a little bit longer line. And that's how this animation works. And then you have to take these objects here and then you have to return them. Now, one final thing, you might be wondering why I have 63 here. These numbers I got from trial and error. This object here, tank sub 1, 2, that's this blue area here. But in reality, it's not area. In reality, if you look at it, then tank 1, 2, it's just a line with a huge line width. So you can imagine that I have my tank here,
and then I want to create some kind of blue area here. And so I create an object here, which will be a thin line. But I want the thickness of this line to be as thick or as wide as this tank. So if I put 260 here, which is a pretty big line width, then this thin line will become a very thick line. Alright? So it will be a very thick line. And then I can use it to represent water in the tank. So this is not simulation, this is just for animation purposes. The problem is that if I give such a huge thickness to this line in the horizontal direction, then this line will also become very long in the vertical direction. And so the height of this line will still vary according to the data that I get from the simulation. So right now it's here, and then if the water volume goes down, then this thing here will go down, and then also this thing here will go down. But still, you can see that this is nonsense because that's not what I want to represent. So through trial and error, I found that if I put minus 63 here and minus 63 here, then I'm essentially cutting off this extra area that I don't need. So I still have the thickness of this line, but I don't have the stuff that I don't need anymore. And so the only thing that I have the area that I'm covering inside my water tank that very closely follows this line here. You see, 70 here, then it was 70 here, and now it's 20 here and 20 here. So if I put here, for example, minus 50, and then I'm gonna put here minus 50, then you see I should be at this 70 cube meters, but I'm a little bit above. And you see here as well, I'm a little bit above. That's this extra area here that I don't need. So this number here, minus 63, and then here as well, minus 63, that was just my trick to create this animation. Alright, I hope that this video has clarified this code file as well. And I'll see you in the next video. Thank you very much. Welcome back. In this video, I want to show you a vehicle that is driving on a straight road, attempting to change lanes. This is the vehicle right here. These are the lanes 1, 2, 3, 4, and 5. The blue line is the reference trajectory that the vehicle needs to follow, and then the red line is where the vehicle actually goes. This is the zoomed in version of the vehicle. This is the vehicle's body, and this is its front wheel that creates a steering wheel angle that makes the vehicle turn. The goal here is to find the right front wheel steering angle so that the car would follow the trajectory as close as possible. This is the system that we are going to be using as we start our journey in Model Predictive Control. I will treat the simulation in a more detailed way in the end of the course, where I will explain to you the code as well. Here I have the control input, the vehicle's orientation, and the vertical position as a function of time. But now the question is, why should we learn Model Predictive Control, or MPC? I mean, can't I just apply a PID controller and that's it? The answer is yes and no. You can do it, however it is trickier, and a well-tuned MPC controller with a good mathematical model gives you a better result than a well-tuned PID controller. In fact, here I have applied a PID controller to the vehicle. As you can see, The vehicle is following the trajectory, but it could be better. And note the oscillations here. The front wheel and the vehicle oscillates a bit. And now I'll show you the same simulation but with an MPC controller. Much better, right? MPC is more advanced than PID, and it is widely used in complex systems like airplanes, drone, complex water management systems, and others. So it is worth learning. In the end of the course, when you have mastered MPC, I will show you why it is superior to PID. We will compare them more. I wish you a great learning experience. Every now and then, a very powerful technique appears in the engineering world that is so universal and which can be applied to so many systems that it becomes unbelievably popular. One of these techniques is called Model Predictive Control, or MPC for short. MPC is heard by many engineers, but not so many truly understand it, because at first glance it seems complicated, very abstract, and quite non-intuitive. Nevertheless, I'm here to show you the exact opposite. MPC is not difficult at all. It fuses with real-world applications beautifully, and it is quite intuitive as well. So if you truly want to be great in solving engineering problems, you have to have all of these three basic abilities. You have to understand your problem intuitively, you have to be able to quantify it mathematically, because even though intuition is great, it's definitely not enough. And finally, you have to be able to translate it all into a code. And with me, you will learn all that. Welcome back. In this course, we're going to apply our MPC controller to a simple autonomous car case. We're going to make it very simple. We're going to assume that our car has a constant forward velocity. So if I draw a car here, top view, then this car will have a constant forward velocity. It's not gonna change. And we're gonna try to achieve a lane changing maneuver. So essentially what the controller needs to do, it needs to make the car change the lane autonomously. And we're gonna use an MPC controller for that. Now how will it happen? This is again a car, and these are back wheels here. And here I'm going to draw the front wheels. And so in order for the car to turn, the front wheels need to turn, right? And these front wheels, they will make a certain angle with the forward velocity. And this angle here will be delta, or steering wheel angle. And so if you turn the front wheels, then you're going to turn. And the MPC controller that we're going to design is going to decide autonomously without human help which kind of delta is best, so that the car would then change the lane. So if this is a lane here and we want the car to go to another lane, the controller will decide how much it needs to turn the front wheels in order to achieve that. So the reason why we are keeping the forward velocity of the car constant in our course is because that will make the application of Model Predictive Control to our car very easy. And that's very good, because that will allow you to fundamentally understand how this technique works. I want to make sure that you guys understand MPC intuitively, but I also want you to learn how to quantify it mathematically, and then in the end I will teach you how to code it. And it's good to do it on a simple system at the beginning, then you won't get caught up with all the nuances and difficulties. Also, our system is going to be a 3 degree of freedom system. So in order to describe the position and the orientation of our car, we're going to need to have an x coordinate, a y coordinate, and a yaw angle. So let me just draw our coordinate system here. you have an X here, you have a Y here, and let's say that your car is here, and the center of mass of the car is here, and so you have the X coordinate, you have the Y coordinate. So with these two variables you determine the position of the car, but the car doesn't only have a position, it also has an orientation, and you need to be able to measure that as well. And so we're going to measure that with a yaw angle, and we denote yaw with a psi, angle psi. So X and Y, they are measured in meters, but psi or yaw angle, it is measured in radians. So it's a 3 degree of freedom problem. That's what the degree of freedom means. The degree of freedom is the amount of variables you need to specify in order to know the car's position and orientation in space. And in our case, it's X, Y, and then the yaw angle psi. Since our car doesn't drive up the hill nor down the hill, then we don't have to consider the z-axis. Because even though normally you have a 3D space, X, Y, and Z, however, in our case, our car will be essentially driving on an XY plane. So in the next video, we're going to talk about forces and moments, and we're going to focus on their physical meaning. And we're going to do the same for the masses and mass moments of inertia of an object. We're going to look at their differences, their physical differences, how they affect the acceleration and rotation of an object such as our car. And I think it's very important, because then everything that I'm going to tell you later on in the course will make much more sense. So thank you very much, and I'll see you in the next video. Physics is truly an amazing thing. It has given us so many useful tools with which we can describe our environment and also to a certain extent control it. One of the most classical notions in physics are forces and moments. Without them, we wouldn't have been able to accurately drive, fly, or send satellites to space. So let's now learn forces and moments, and let's try to understand them fundamentally, and let's try to understand what they do to objects that they are applied to. Now, a good way to understand what a force is to look at its units. We denote force with a capital F, right? And we measure force with a unit called Newton. And what's Newton? Newton is equivalent to kilograms times meters per second squared. The kilogram is a unit of mass, and meters per second squared is acceleration. So already from the unit, you see what a force really is. Force is accelerating some kind of mass, and that's why you also have this famous formula, force equals mass times acceleration. So if you have some kind of box and the mass of that box is, let's say, 2 kilograms, and you apply a 6 Newton force to the box, then that box will accelerate how much? 3 meters per second squared, because acceleration equals F divided by m. And then if now we have another box and the mass of the other box is 6 kilograms, then what's the acceleration? The acceleration would be 1 meters per second squared. So in a way, from this formula, you can see what the mass really is. Mass is resistance to acceleration. If you apply the same amount of force to a box, then a heavier box will accelerate less. So mass really is a resistance to acceleration. And so what is a moment then? Moment, that we denote with a capital M,
or torque, capital T. And by the way, moments and torques, they're the same thing. They are used in different contexts, but their physical meaning is the same thing. They have the same units. And their units are newtons times meters. So what you need to know is that forces, they make an object accelerate in space. But moments or torques, they make the object accelerate rotationally. So in the case of forces, we have this kind of acceleration where we have meters per second squared would be the units for the acceleration. But when we deal with moments, then the result will be angular acceleration of an object. So let's say alpha double dot. Alpha is an angle, and the double dot, it would be the second derivative of that angle. So it would be d squared alpha dt squared. And the units here would be radians per second squared. So for example, let me draw a rod here. This rod can rotate about this point that we call A. And let's say that we have another point here, B, and we apply a certain force to that point. And now, if we want to calculate the moment that this force exerts on this rod about this point A, then what we have to do, we have to decompose this force into the X and Y component. So we have force Y here and force X. Now why do we decompose it? First of all, you have to calculate the moment by taking this force and multiply it by this distance here from A to B. And so the moment about the point A, right, about this point here, the moment about the point A would be force in the y direction times distance. And whatever answer you have there, it will have the units newtons meters. And so the reason why we had to decompose this force vector here is because when you multiply your force times distance, then the force has to be perpendicular to this distance. So there must be this 90-degree angle here. And as a result, the moment will accelerate this rod rotationally. So this rod will start to rotate about the point A. So how do we now find the relation between the moment and the angular acceleration of this rod? Well, let's see. When we had our force, then our force equals mass times acceleration. Now we said that the mass was resistance to acceleration. So if you have the same amount of force but you have more mass, then the acceleration of the body will be less. So you could rewrite this formula like this. So for a bigger mass, assuming that the force is the same, for a bigger mass you would have less acceleration. So mass is resistance to acceleration. So when we talk about moments, then you need to have something here times the angular acceleration, the double dot alpha. So if here m was resistance to acceleration, then here in this box you should have resistance to, what do you think it is? Resistance to rotation. So moment equals resistance to rotation times angular acceleration. And this resistance to rotation is called moment of inertia. And again, if you rewrite this equation in this way, moment divided by the moment of inertia, then you will see that for the same amount of moment that you have, if you have more moment of inertia, you will have less angular acceleration. So your object will accelerate angularly less. So the moment of inertia here is resistance to rotation. Now, question to you. Can you, without looking it up online, can you figure out the units of moment of inertia? Just pause the video and then I will tell you the solution. So what are the units of a moment? It's Newton meters, right? Equals x, which are the units of the mass moment of inertia, I, times radians per second squared. Okay, so we can rewrite this part of the equation in the following way. Kilogram times meter divided by s squared, which is the Newton part, times m, which is this m here, equals x radians s squared. So what you can do now, you can just put this s squared here, and you can put radians here. Okay, so you can cancel s squared and s squared, and the radians, it's dimensionless. Why is it dimensionless? Because radians is calculated the circumference of a circle divided by the diameter of the circle. When you calculate it, when you take the circumference of the circle and you divide it by the diameter of the circle, you get pi. But both of these quantities are meters, right? The circumference of the circle is meters and the diameter of the circle is meters. So you divide meters by meters and you get radians, but radians is meters by meters, which means that radians is a dimensionless unit. So here you can just make it disappear. And there you go. The unit for your mass moment of inertia is kilograms meter squared. That's the unit of mass moment of inertia, and it is the resistance to rotation. So the more of mass moment of inertia you have, the harder it is for the object to rotate or to accelerate rotationally. The more moment you need to apply to accelerate rotationally some kind of object in order to get more radians per second squared. So there is one more thing that I want to cover. Let's say that you have a cube here, and this cube has an equal distribution of mass inside it, and then the center of mass is in the center of the cube. And then you have another cube-like object that looks like a cube, but it's empty inside. So it's bigger, but it's empty inside. So the question to you is, if they have the same amount of mass, both this object and this object, if their masses are equal, which one of them have a higher mass moment of inertia? In other words, which one of them have a higher resistance to rotation? You can pause for a second, and then I will let you know the answer. So the answer is that the second object, this bigger object, has a higher mass moment of inertia even though they have the same mass. Why? Because one thing with mass moments of inertia is that if you have a center of mass somewhere, the more mass you have away from the center of mass, the higher your mass moment of inertia is. Even though they have the same amount of mass, in the first case, most of that mass is clustered close to the center of mass. But in the second case, all of that mass is further away from the center of mass. So it's all further away. And therefore, because of that reason, the mass moment of inertia is bigger for the second object. Welcome back. So before we finish the force and moment section, I want to do a small fundamental exercise that I think will really help you fundamentally understand forces and moments and their differences and what happens with the objects that they are applied to. So I'm going to ask you to participate in this exercise. I'm going to be asking you several questions, and then I'm going to ask you to pause the video, and once you think you know the answer, just unpause the video and I will tell you the answer. So let's get started. Let's assume that we are somewhere
far, far away in the universe, far away from the Earth, so there is no force of gravity. You simply have a rod that is tilted at a 60-degree angle, and in the center of this rod you have a center of mass. So right now there is no force applied to this rod, so it just exists there, it just hovers there. So now what I'm gonna do, I'm gonna apply a force to this rod, but to the location of the center of mass. So the question to you is, what do you think is gonna happen with the rod after some time? Where will this rod be? And at which angle this rod will be? So pause for a second. So the answer is that you have to look at the center of mass. The center of mass will only go in the x direction. It will not go in the y direction. It will only go in the x direction. And the rod will still be at an angle of 60 degrees. If we apply this force again, then after some time, again, the center of mass will only move in the x direction, but it won't move in the y direction. So the y direction would be up and the x direction would be to the right. So the rods would only move in the x direction, and it would still be at an angle of 60 degrees. But how about if now I apply this force like this? What's gonna happen with the rod? So the answer is that now the center of mass of this rod will move up and also along the x direction. So your center of mass will be here, but the rod will still be at an angle of 60 degrees. So the angle won't change. Okay? So again, if I apply a force here, then you already know the answer for that. The center of mass will only move in the x direction and the angle won't change. So it will still be 60 degrees. Alright? And now if I apply a force like this, then I guess you already know what's gonna happen with the rod. The center of mass will move down and the rod will still be at an angle of 60 degrees. So this kind of motion is called translational motion. So the object is translated, the center of mass of the object is translating along some kind of path, right? But it's not a rotational motion. As you can see, the angle of the rod didn't change. Why? Well, because there was no moment, right? Remember, what is it what makes an object rotate? It's a moment, not force. You need to have a moment in order to change the angle of your object. And the moment, in this case, is 0. Because even though you have force, but this force is applied directly to the center of mass. And so, since moment equals force times distance, and then the distance is 0 because the force is applied right at the center of mass, so the distance is 0, and therefore moment is also 0 Newton meters. And therefore you only have this motion where the center of mass moves, but the orientation of the rod doesn't change. Essentially you can have this kind of motion of the rod where the rod moves along some kind of trajectory, but the orientation of the rod doesn't change. It's at the same angle. Okay, but now let's do something more interesting. Suppose that I have another rod here, and initially that rod again is at an angle of 60 degrees, and you have the center of mass here, and I'm gonna apply a force, but this time I'm gonna apply it here. So what do you think is gonna happen with this rod in terms of
the motion of the center of mass and the rotation of the rod. Don't worry about the specific angles, just think about whether the angles will decrease or increase or stay the same, and whether the rod will go up or down or only in the x direction. So the answer is, remember, the force only makes the rod accelerate, right? So this force is only applied in the x direction, which means the center of mass of this rod will only move in the x direction. It will not move down, it will not move up, it will only move in the x direction. However, now, pay attention, you have a distance here, right? The distance which is perpendicular to this force. And that creates a moment, right? So you have force times distance. So you have some kind of moment. And what do moments do? They make bodies rotate. So now this rod, its center of mass will still be at the same height, but it will have a smaller angle. So instead of 60 degrees, it will be 45 degrees. Let's take another one. I apply a force, but now like this. And now this force vector is perpendicular to the rod. So what's going to happen with the rod now? So now, if you look at the force vector, it also points down. It has a component in the x direction, but also in the y direction. And so because of that, the center of mass will move down. But now, you also have a distance here. So because of that, you also have a moment. And since you have a moment, the object will rotate as well. So because of that, this rod will be even at a smaller angle, let's say 30 degrees. And finally, if we take two forces and we're gonna apply one here and one here, only in the x direction. And so the distance to one of the forces is d, and the distance to the other force is also d. So actually the distances here are equal, okay? They don't look like equal, but they're equal. So what will happen with the rod now? The answer is that now the center of mass will move only in the x direction because both forces are in the x direction, and the rotation of the rod does not change. It will still be 30 degrees. Why? Because even though you have one moment from this force, but another moment is caused by the other force in the other direction. So this moment here will try to make the rod rotate in this direction, but the downward force will try to make the rod rotate in this direction. And so because of that, both of these moments, they will compensate each other, and the body will not rotate. So you will end up being in this position where the center of mass only goes in the x direction, but the rod stays at 30 degrees. Okay, so I hope you've enjoyed the exercise and now you understand the moments and the forces. And starting from the next video, we will start working on the car and building the model of the car, and after that we're going to start building the controller. So thank you very much and see you in the next video. Welcome back. So starting from this lecture, we're really going to start working on the car now. So the first step is, let's try to understand what is it what we're trying to achieve. What is it that we want our controller to do? So what I'm going to do, I'm going to draw a road, a nice wide road, and I'm going to have a broken line here that will separate the two lanes. And so my car right now is in this lane. Our forward velocity would be 20
meters per second, and it is constant, it doesn't change. And so we want to perform a lane changing maneuver, and we have a trajectory, a common sense nice trajectory that will allow us to change the lane in a smooth way. And maybe we have it as a pre-planned trajectory, or maybe we have some kind of camera on top of the car that looked at the road and decided that, okay, this is the best trajectory to follow. But the bottom line is that we have a reference trajectory, and so the control's job is to make the car follow this trajectory autonomously without human help. And let's say that we want to complete this maneuver in 7 seconds. So at the beginning, it's going to be t equals 0 seconds. Then it's going to be 1, 2, 3, 4, 5, 6, and 7. So here, time equals 7 seconds. So this is what we want to achieve, and this is what our controller will need to achieve for this car by manipulating its forward wheels. So I'm just gonna create a box here, and inside the box we're gonna have our open loop system. And by an open loop system, I mean we're gonna have a mathematical model that relates the input of our system to the outputs of our system. Now, in our case, the inputs of the car would be delta, the rotation of the front wheels. So we have a car here, and we have the backwards wheels, and our front wheels, they will be at an angle, and so this angle will be the steering wheel angle delta, which we measure in radians. So this will be the input into our open loop system, and so our mathematical model will produce our outputs, which will be x, y, and psi, all these 3 degrees of freedom values, right? In the real life, of course, you will have sensors that will measure these values, x, y, and psi. Once we have these values, we have to compare them to the reference values, so to the reference x, reference y, and reference psi. So at some point we're going to have reference values, so xr, yr, and psi r. These are the values that tell us where we want to be, right? These are the values where we are, and these are the values where we want to be. So we're going to now perform an operation where we're going to subtract the values that we have from the reference values. So I'm going to put a plus here and minus here, and in the end we're going to have an error term for the x, an error term for the y, and an error term for the psi. And so these error terms will then enter into our controller, which in our case will be the MPC controller, but it doesn't have to be an MPC controller, it can be another controller as well. But that's the general picture of the situation. And so the MPC job will be to find the right delta, the right steering wheel angle, so that the errors would go to 0. Because when the errors go to 0, then that means that the values that we have here, that's where we are, where we really are, that means that these values match where we want to be. Because remember, let's say the error in the x direction is xr minus x. So that's going to be the job of the controller. Now, luckily, we can make our schematics even easier in our case. We can get rid of x, we can get rid of the error x, and we can get rid of the reference x. And let me show you why. So again, we have a road here. Imagine that we have a road here, and this is our trajectory that the car needs to follow. Now this entire world is measured in global
X and Y reference frames, right? So you have an X here and you have the Y dimension. So imagine now that your car is here and the center of mass of the car is here. In order to control the car and make it to be where the reference line is, what you need is the distance from the center of mass to the reference line, right? So we can draw it here. So this would be your Y error, right? It would be this one, Y error. So if you manage to get that to 0, then the center of mass of your car will be here, in this point. However, you also need to consider the orientation of the car. So right now you can see that the yaw angle of the car is different from the yaw angle of the reference frame. So the yaw angle of the reference frame right now is something like this, but the yaw angle of the car is bigger, so it's something like this. So you also have to control the yaw angle. So here, this would be your yaw angle reference. It's this one. This is the yaw angle of the trajectory. And this is the yaw angle of the car. And so the yaw angle error would be the yaw angle of the trajectory minus the yaw angle of the car. So if you manage to get that term to 0 as well, then the trajectory's yaw angle will equal the car's yaw angle. And then what you will have a car whose center of mass is where the center line is, and also the orientation of the car will match the orientation of the reference line. And so in our case, you truly need only two variables to control the car. You need the Y dimension and you need the yaw dimension. And in our case, these are the variables that we're going to be working with. And by the way, the reason why we can make this simplification is because we have a constant forward velocity that was 20 meters per second. And the thing is that we don't have to control this forward velocity, right? We only control the steering wheel angle, but we don't have to control the forward velocity in our case. So we don't have to think about applying more gas to the car or applying the brakes to the car. So that's one reason why we can make this simplification. However, it's also because we have to consider that the yaw angles here are actually pretty small. You might think that they are like maybe 45 degrees or something, but actually they're extremely small. Because if you think about it, this entire operation would happen in 7 seconds, right? So t equals 7 seconds. So if you travel 20 meters per second, then let's say that the distance here is maybe maximum, I don't know, maybe 3 or 4 meters. Let's say it's 4 meters. But since your forward velocity is 20 meters per second and this entire thing happens in 7 seconds, then that means that in the x direction you will approximately travel 140 meters. So 20 meters per second times 7 seconds, you will have 140 meters. So you will travel approximately 140 meters in the x direction, but at the same time you will only travel 4 meters in the y direction. So you can imagine that actually the angles, the yaw angles that we're talking here about are going to be very small. So essentially you don't have to worry about the x dimension, because this x dimension you pretty much know how it's going to be. You pretty much know that in 7 seconds you're going to travel 140 meters because your velocity is constant, it doesn't change. Therefore, you don't have to worry about the x dimension because you approximately know where you're going to be at every second. And finally, I want to highlight something. Even though this course is about the MPC controller, you really can have different kinds of controller there. For example, you can have a PID controller there. But here's one nuance that I want to point out. Here we have two outputs. We have Y and we have the yaw angle. And so that's why here we have the reference Y and reference yaw angle. And here you will have the error Y and the error yaw angle. So, of course, if you have your MPC controller here, then your controller will give you the delta so that the car would drive in such a way that next time these errors would be zero. Now, if you want to use a PID controller for that, then notice one thing. In this system, we have one input, but we have two outputs. But a PID controller is a single input, single output system. It's called CISO. So CISO is single input, single output. So it's a term used in control engineering. You also have something called MIMO, which is multi-input, multi-output system. So, in fact, in our case, it should be SIMO, even though I'm not sure if they are using this kind of term, because we have single input and multi-output system, right? So we have two outputs, one input. But a PID controller can only handle CISO systems. So you're going to have two PID controllers here. So you're going to have one PID controller where it takes in the error in the Y direction. So error Y. And then you have your PID, PID1. And then you get one delta. And then you will have another error, the yaw error. And then you will have another PID. And you will have delta 2, and then you will add them up or maybe do something else with them, and then you will have this combined delta that will then enter into your open loop system. And remember, the PID had three constants that you had to tune: the proportional, the integral, and the derivative constant. And since you have two PID controllers here, in total you have 6 parameters to tune. And so it could be quite a challenge. The advantage of a model predictive control is that MPC can take in multiple outputs and multiple inputs. So MPC is scalable. PID is not scalable, but MPC is scalable. So that's the great advantage of the MPC controller. It has other advantages as well, and I'm going to share them with you when we start designing the MPC controller. But one of those advantages is that MPC is very suitable for MIMO systems. Welcome back. Here I want to get back to this simulator. Right now I'm applying a PID controller, and in fact I've done exactly what I explained to you in the previous lecture. Since PID is a CISO system, then I applied two PID controllers, one for controlling the yaw dimension and the other one for the big Y dimension. So I have 6 constants here with which I can tune my two controllers. Through trial and error, I decided to go with these values here. I get two deltas, delta for yaw and delta for big Y, and then I add them together and then I apply them to the vehicle. Like I mentioned, could be better. And again, one obvious advantage of MPC is that it naturally scales up to deal with MIMO systems, multi-input, multi-output systems. CISO was single input and single output. However, there are more advantages. I will cover them in the last section where I explain to you the simulator. Thank you. So before we start mathematically modeling our open loop system, the model that will connect the inputs and the outputs of the system, so in our case the steering wheel angle and then the Y and the yaw angle, before we do that we have to talk about the reference frames as well, because in our case
we have two different reference frames. One reference frame is the global Earth fixed reference frame. So this reference frame is fixed to the ground. It doesn't move. It's an inertial reference frame. However, you also have a car, and on that car you have a body frame. The body frame is attached where the center of mass is, and this body frame is attached in this way. You have a small x here and you have a small y here. So the x direction is the longitudinal direction, and then the small y direction is the lateral direction. So when we talk about the constant forward velocity, then it's also called longitudinal velocity. So our longitudinal velocity is constant and it's 20 meters per second. But how about if the car travels in a circle? Does it mostly experience longitudinal or lateral velocities, or both? So the answer is that in normal circumstances, the car mostly experiences longitudinal velocities and negligible amount of lateral velocities. So let's say that in this case, if this car travels in a circle, and let's say after some time this car is here, then remember the body frame always travels with the car. So wherever the car goes, that's where the body frame goes. So in this case, the longitudinal direction of the body frame would be in this direction, and then the lateral direction would be outwards like this. So this would be small x and this would be small y. And again, if the car is here, then the lateral direction would be outwards, but the longitudinal direction would be forwards. And as you can see, as you drive in a circle, then you drive in the longitudinal direction. Now, of course, nothing in the world is perfect, and maybe you slip a little bit, a couple of millimeters here and there, so sure, I guess you have a little bit of lateral velocity, but you can neglect it. Now, of course, things are different when you have sideways slipping. For example, if you're on the ice and you're driving along a road with very high curvature, then your car is here, and okay, you go forward, you drive longitudinally, but because you're on the ice and it's very slippery, you also start slipping in that direction, and in that case you will have lateral velocity as well. Or also when you are in Tokyo drift, then you will also have lateral velocity. Now, since we have two reference frames, we have this inertial reference frame with capital X and capital Y, and then we also have this body reference frame, small x and small y. And if we take the change of small x with respect to time, so x dot, then it's going to be the velocity in the longitudinal direction, which in our case again is constant. And then if you have some kind of slipping and you have velocity towards the lateral direction, then that would just be the change of small y with respect to time, or y dot. Now, for control, it's important to be able to represent these velocities, the longitudinal and lateral velocities, in the global reference frame. So essentially what we want the capital X dot and the capital Y dot. So the change of capital X with respect to time and the change of capital Y with respect to time. And why is this important? It's important because our trajectory is described in the global reference frame. So if I take a random point here, then this point is described by this capital X and capital Y. So it's going to be like this, XR and YR. So if you want to compute an error in the Y direction, then it's like this: yr minus the position of the car in the y direction in the global reference frame. So it's going to be capital Y. Now, in order to compute this, you need to know how fast the car drives in the direction of the capital Y. In other words, you need to know the velocity in the direction of the capital Y. And that's why you need it. And also, if you had another system and you needed to calculate an error in the x direction, then it would be the same thing, xr minus capital X. And in order to compute capital X, you're going to need to know the velocity in the direction of capital X. But what you have the longitudinal velocity, and if you have some slipping, then also lateral velocity. So you need to decompose these two vectors, and you need to transform the longitudinal and lateral velocity onto the global reference frame. And you do that like this. Let's say you have your longitudinal velocity here and your lateral velocity here. So we assume that it's pi over 6 radians, so it's 30 degrees. The x component of Vx is this. The y component of Vx is this. The x component of Vy is this. And the y component of Vy is this. So, in order to compute capital X dot, what do we have to do? We take Vx, which is our constant longitudinal velocity, which was 20 meters per second, and we multiply it by cosine pi over 6, because then we get this component of the vector. And then we have to subtract Vy times sine pi over 6. Why do we subtract it? Because here the velocity vector in the lateral direction produces a component in the capital X direction in the negative direction, you see? So in the first case you had a positive component in the case of Vx, but in the case of Vy a negative component is produced, and that's why you subtract. And now it's going to be an exercise for you. I would like you to pause now and try to find an equation for y dot. Welcome back. So the answer here is Vx, which is this vector here, and now you need to get this vertical component, and you get that by multiplying sine pi over 6. And now, do you need to subtract or add? Well, in this case you need to add, because now both of the components are upwards, right? So you have to add Vy times cosine pi over 6. And again, now you add, because now this Vy vector produces an upward component. And there you have it. That's how you go from the body frame to the global inertia frame. That's how you transform the velocities in the body frame to velocities in the inertial frame. Okay, so this is it for now, and in the next video we're gonna start building the open loop mathematical model for our car, and then after that, once we have this model, we can start designing our MPC controller to control our car. So thank you very much, and see you in the next video. Welcome back. This is a quick follow-up video. First of all, I want to thank you for enrolling in my course. I'm very glad that I can be your teacher. I would like to point out that the simulation codes in this course for the PID section are at the end of the first section, the last lecture, and the codes for the MPC part are at the end of the MPC coding section.
last lecture as well. Also, I want to thank you for all the reviews that I have received from you. However, to be honest with you, I would love to have more of them from you. It is very important to me to get your feedback, and it's also important for my future potential students so that they would know your opinion about this course. Your feedback is very valuable. Thank you very much, and let's continue with the course in the next video. Welcome back. So now that we finally have all our fundamentals in place, we can finally start deriving a mathematical model for our car in the lateral direction. So remember, we only consider lateral motion in our case. So if we have a car here, this is the top view, then the lateral direction would be in this direction, and the longitudinal direction would be like this. So the car's longitudinal velocity or forward velocity would be in this direction, and then this is the lateral direction. And our model is going to describe motion in the lateral direction. Now this model is called plant or also open loop system. And we need that model in order to later on design our controller, because our controller will be designed and tuned based on the model here. And that's why it's important that the model that we're going to derive here will represent the reality as closely as possible, or at least as closely as necessary, because you can always go more specific and more precise, but then your models will also go more complicated. So sometimes you have to make a trade-off between how complicated you want your model to be versus how easy you want it to be, and the precision. So sometimes when you don't need that much precision, then your model could be simpler. When you need a lot of precision, you need a model that is more complicated. And essentially, what this model is trying to achieve, it's trying to relate the system input with the system outputs. Okay? So our system input, which is a steering wheel angle, if that goes into our model, when we get something out of our model, we should get our outputs out of the model. Alright, so essentially we need to find a connection between our outputs, for example our y as a function of delta, and our yaw angle also as a function of delta. Very often when people design controllers for their vehicles, and when they build a mathematical model for their car, very often they use a simplified version of the model, which is a model for a bicycle. So they are using a bicycle model to design a controller for their car. The reason for that is because the bicycle model makes designing the controller much simpler, but it turns out that the bicycle model still represents the car's dynamics well enough that it enables people to design their controllers reliably. So that's why in many cases, when not too much precision is needed, people, in order to design their controllers instead of an entire vehicle, they use a bicycle model as their mathematical model to describe the inputs and the outputs of the car. So, in other words, instead of building a mathematical model for a car with 4 wheels, 2 in the back and 2 in the front, instead of building a plant model for that, we're going to build a plant model for a bicycle. And in order to do that, we're going to take the 2 front wheels of the car and we're going to lump them into one big front wheel for the bicycle. And we're going to do the same thing for the rear wheels. We're going to take the 2 back wheels and we're going to lump them into one back wheel. And finally, we're going to add a center of mass here. And so now, this is a bicycle or a motorcycle. It's a 2-wheeled vehicle. And this is what we are going to
build our mathematical model for, which will take in our input, which is the steering wheel angle, and then it will return us the y coordinate and the yaw angle. And the steering wheel angle here would be then by turning the front wheel, right? So if we turn the front wheel, then the steering wheel angle would be this one. Nevertheless, I want to treat a couple of differences that a car model and a bicycle model have. So I'm going to do it on this side of the page. So let's assume that we have a normal car with 4 wheels. 2 wheels in the back and 2 wheels in the front. If I want the car to turn, then the very first cars that appeared, I guess, around 100 years ago, the way they turned the entire front axle, right? So this entire front axle became like this. These are the 2 front wheels. And so you had some kind of angle here. And so if you draw a line perpendicularly from the back wheels, right, and it's perpendicular to the back wheel, and then you draw another line from the front wheels, also perpendicularly, then at some point these 2 lines meet, right? So this is also perpendicular, and so we're going to call this point R. And so this point where these 2 lines meet, that's the instantaneous center point around which the car is driving. And so if the angle of the front axle doesn't change, then this instantaneous center of rotation, this point R, won't change either. So the car will simply be driving in circles around this point. And this point doesn't change, and so the distances here won't change either. Let's call it R back and R front. So it's the distance from R till the wheel. They won't change. However, if I now change the angle of the front axle and I make it, let's say, smaller, then if I draw a new line from the front wheels, then you will see that the center of rotation, this instantaneous center of rotation, will change. It will be further away. All right? This is all instantaneous. If at time equals 0 seconds, your axle is like the red one, then your turning is sharper and your center of rotation is closer to the car. But then if at time equals 1 second you decrease the angle of your front axle, then your center of rotation will be further away from the car, which means that your turning will not be as sharp. Now the problem is that making this entire axle turn is not mechanically very efficient. So another option would be to, for example, turn 2 wheels separately. So something like this. You have your back wheels here, and this is your front axle. And let's say that both of our front wheels, they are turned, and the angle at which they are turned are equal. So let's say this one is turned at angle delta, and also this front wheel is turned at angle delta, and they are equal. So we could do it like this. It would be easier, but then look what happens. If I draw a line here, and then I draw a line from this wheel here, and then I draw a line from this wheel here, then I'm gonna have 2 instantaneous center points. So what does it mean in real life? It means that when the car tries to turn, then at least one wheel, if not both, will be slipping. And that's not good for the tires, that's not good for efficiency. It's better to avoid that. So what would be the solution for that? How can you turn these 2 wheels without turning the entire axle in such a way so that you would only have 1 instantaneous center of rotation? What would be the solution for that? Pause the video for a second and try to think about the solution. The solution for that is actually quite straightforward. If I want to turn to the left, then if I turn my first front wheel, the inner front wheel,
if I turn it at an angle delta, and then I turn my outer front wheel also at some kind of angle, but that angle will be different and less. Okay, different and less. Then look what's gonna happen. And let's say it's an angle alpha. If I now choose the right angle alpha, there is one angle that is the right angle that will give you one center of rotation. So if we draw a line from here and then from here, and if this alpha angle is correct, it has to be smaller than the delta angle, but if it has the right magnitude, if you draw a line from here, then you will actually converge and you will have one single center of rotation. Alright? So that's how modern cars drive nowadays. And okay, in real life it's not ideal. In real life they are almost in the same place because nothing can be 100% ideal, but they're almost ideal. But that's the logic. If your front wheel, you turn it by delta, then if you turn your outer front wheel by a smaller angle, if you know the right angle, then you will have one center of rotation. And then you can avoid the inefficiencies like tires slipping on the ground, etc. So this is actually one of the things that the bicycle model doesn't take into account, right? Because in the case of a bicycle model, you only have one front wheel and you only have one back wheel. So in the case of a bicycle, you have your back wheel and you have your front wheel, which is turned by an angle delta. And so if you have a car and you use a bicycle model, then you are not taking into account this effect that the two front wheels, they turn at different angles. However, the difference between these angles, between delta and alpha, they are usually so small that for many cases it doesn't matter. For many cases you can neglect it and still use the bicycle model. But that's one of the differences that I wanted you to know. But now, let's say that you have found your delta using your bicycle model, using your MPC controller. And now the question is, how do you apply it to a four-wheeled car? How do you go from here to here? Well, one way to approximate ideal steering, which is having two steering wheel angles that are different, such that they form one instantaneous center of rotation, and this is called ideal steering. One way to achieve that is to use Ackermann steering. It's a clever mechanism to approximate ideal steering, and it looks like this. So you have three pictures here, and you can see this trapezoidal shape here. So when the car starts turning, then this mechanism allows the inner wheel to the rotation to make the steering wheel angle larger, and then automatically the outer wheel will have a smaller steering wheel angle. And it applies when you rotate to the left and when you rotate to the right. So here you can see that delta 1 is bigger than delta 2, and here delta 1 is smaller than delta 2. And this mechanism approximates ideal steering. It's not ideal, but it approximates it. So the delta that you get from your MPC, you can assign it either to the left wheel or to the right wheel. And then the other one will have a slightly bigger or smaller delta depending on the turning direction. Now, if we want to make our bicycle model rotate, then we have to do the following thing. I'm gonna draw a bicycle here, and this is the back wheel here and the front wheel, and we're gonna make the front wheel turn. Now, in order to find the instantaneous center of rotation, we follow the same logic. This is the center of mass. So we're gonna draw a line from the back wheel and also from the front wheel perpendicularly, and wherever they meet, that's your center of rotation. And we're gonna call this point R. So the bicycle rotates around this point for as long as this front wheel is turned at an angle delta. Now, do you remember when we had a car, then we said that we have a body frame that would be attached on the top of a car, right? So if I'm gonna draw a top view of the car, and now I'm gonna put a body frame on top of it, then we said that when the car drives and then makes a turn, then the car will mostly drive in the longitudinal direction, in the direction of the small x, and not in the direction of a small y, unless there is slipping. Now, this is true if you have really simplified your situation. However, now we're going to dig a little bit deeper. First of all, let's define our body frame. Our body frame for the bicycle would be like this. This white line, the body of the bicycle, it would be the longitudinal direction. This would be our small x. So it goes along the white line. So the lateral direction would be this one. So this would be small y. So that's how we define our longitudinal and lateral direction for the bicycle. The longitudinal direction goes along the body of the bicycle, and perpendicular to it you have a lateral direction. But now this front wheel, its velocity is in this direction, and the back wheel, its velocity goes along the longitudinal direction. So if you now think about it, then if you go from the back wheel to the front wheel, then whatever point you take on the bicycle, whatever molecule or atom you take on the bicycle, the motion of that molecule does not go directly along the longitudinal direction. It has to go something in between this direction where the back wheel goes and this direction where the front wheel goes. Meaning that as you go from the back wheel to the front wheel, the direction of the velocity of that point on this bicycle is something in between this, the back wheel, and the front wheel. So here, since you are closer to the back wheel, here the velocity of this point, it's not exactly in the direction of the longitudinal direction, but it's almost in that direction. So it does have a small angle, right? Now here, you're much closer to the front wheel. The direction of your velocity at this point matches more the direction of the front wheel. So it's gonna be maybe something like this, okay? Something like this. And now, when we are here at the center of mass, then here also, this point here, its direction is something in between the back and front wheel. So this point here actually travels maybe something like this. And since it's the center of mass, this angle here has a special name. It's normally denoted with beta, and it's called a slip angle of the vehicle. So when you create a model for this bicycle, you have to know that the center of mass of this bicycle not only travels in the longitudinal direction, but it also has a lateral component. So in the past we talked that this car of ours would travel longitudinally at a constant velocity, and I think we said that it was 20 meters per second. So this constant longitudinal velocity, it's this one. It's this component, because we define our longitudinal direction along the body of the bicycle. However, when you build the model for your bicycle, then you will see that there will also be some kind of velocity in the lateral direction. Alright, Now this velocity, even though it seems quite big here, this velocity will be very small compared to the longitudinal velocity. However, it will not be completely zero. Now, one more thing that I want to show you is this. If you look at these red lines here, these red dotted lines, they are perpendicularly to the wheels, right? So a good way to think about these other points on the bicycle is that, okay, if you want to know in which direction a certain point on a bicycle travels, then assuming that the front wheel will keep its steering wheel angle constant, assuming that you're not going to change that angle, then obviously the bicycle would be travel in circles. Then in that case, you can draw a line from this instantaneous center of rotation to that point that you're interested in, and it has to be perpendicular. And then you will know in which direction that particular point on the bicycle is traveling. So in this case, we could draw a line till here. So here you would have a 90-degree angle. And we can also do the same thing with the center of mass. We can draw a line here to the center of mass, and you guessed it, it will also be perpendicular here. So when you have your center of rotation, then each point on the bicycle, its velocity is in the direction that is perpendicular to the line that leads you to the center of rotation. Also, what we can do, we can formulate the angles that the velocity vectors make with the bicycle. We can formulate them mathematically. So let's say that the angle between this velocity vector and the longitudinal axis is theta 1, which is 0 radians. Then let's say that this angle here is theta 2. This is beta. This is theta 3. And this is delta. And so we don't have to worry about the exact values, but the logic is this. Theta 1 is the smallest angle, then you have theta 2, then you have beta, then you have theta 3, and finally you have delta. Welcome back. So now let's connect the car's input, the delta steering wheel angle, with its outputs, which are the y coordinate and the car's yaw angle. So to create this mathematical model, we are first gonna write down the equations of motion. What are the equations of motion, by the way? The equations of motion are equations that connect all the forces that are applied to an object to its acceleration, and also all the moments that are applied to an object to its angular acceleration. So essentially, the equations of motion are equations where on one side of the equation sign you have the sum of all the forces applied, and on the other side of the equation sign you have mass times acceleration. And then you have another equation where on one side of the equation sign you have the sum of the moments, and on the other side of the equation sign you have the mass moment of inertia times the angular acceleration of that object. Now, if you look at the bicycle here, then you can see that here the distance from CM, center of mass, to the front wheel is LF. And the distance from CM to the back wheel is LR. And since we're dealing with the lateral control, then we're going to consider the forces in the lateral direction. So when the front wheel turns at an angle delta, then due to friction with the ground, you will have two lateral forces, one coming from the front wheel and one coming from the back wheel. So these are the two forces. And so what we're going to do now, we're going to write an equation of motion for the lateral direction. The equation of motion in the lateral direction would be then the sum of the forces in the lateral direction equals mass times acceleration in the lateral direction. Now, the equations of motion, they don't have to be only in the global x or global y direction. They can also be in the longitudinal or in the lateral direction. And since it's lateral control, we only consider the lateral direction. We don't consider the longitudinal direction. So it would be then Fyr plus Fy front equals mass times acceleration in the lateral direction. Now, this is not all, because we also need to consider the moments, right? Because this bicycle, it doesn't only translate, it also rotates, so there must also be some moments involved. So pause the video for a second and try to write down an equation of motion, but for the moments. Welcome back. Okay, I hope you've tried it yourself. So for the moments, we also need some kind of convention, and the convention is that if something rotates counterclockwise, then it's positive, and if something rotates clockwise, then it's negative. So in this case, the moments in the counterclockwise direction would be positive. So the counterclockwise moment would be Fyf times Lf. Fyf times Lf. However, this component of the moment, Fyr times Lr, makes the bicycle rotate in another direction, clockwise, and that's why it's negative. So you have to subtract Fyr times Lr, and that equals the mass moment of inertia, and instead of alpha double dot, we can very simply write psi double dot, because here our yaw angle is psi, so psi dot would be radians per second, right? It would be the angular velocity, and so the angular acceleration would be psi double dot, which is radians per second squared. All right, so there you have it. These are your equations of motion. And from these equations, then you will continue working to find the relation between delta and then the yaw angle and the y coordinate. Now, let's talk a little bit about the acceleration in the lateral direction, a sub small y. Let's unpack it. So in fact, the acceleration in the lateral direction has two components. It has two contributions. One contribution is small y double dot. It's the change of the lateral velocity. So because of the slip angle, you have some kind of velocity in the lateral direction, which is y dot. And so if you take the derivative of y dot with respect to time, you get y double dot. It's the change of lateral velocity with respect to time. However, there is another component to it, and this component is called the centripetal acceleration. And so the centripetal acceleration, we can write it down like this: x dot times psi dot. So the change of longitudinal velocity with respect to time times the change of yaw angle with respect to time. Now, you might ask that, wait a minute, didn't we say that the longitudinal velocity is constant? Yes, it is constant, but it's constant in the body frame. So it's always constant in terms of magnitude. However, remember, the acceleration doesn't only appear when your magnitude changes, also when your direction changes. So if at some point in time your longitudinal velocity, which is, let's say, 20 meters per second, if at some point it's like this, and then at another point in time it's like this, right? It's still 20 meters per second, but in this inertial frame, right, in this global frame, the direction of this vector has changed. Even though the magnitude is the same, the direction of this vector has changed, and therefore you also have acceleration. And that's actually happens when something is turning, right? So when you have a roller coaster, right, and then you have some kind of train, some kind of roller train, then as this roller coaster goes along the rails, then you have some kind of centripetal acceleration into the circle. And so this is the second component that you need to take into account in the lateral acceleration. And it makes sense because your bicycle is turning. The trajectory is something like this. So since the bicycle is turning, you have to have centripetal acceleration. And in fact, it's the centripetal acceleration that makes the bicycle rotate, because the centripetal acceleration appears when you have forces in the direction of center of rotation. Right, so in this case, you have the normal force from the track that is pushing the train to change its direction. Its magnitude might be the same, but its velocity vector is changing because its direction is changing. So the force and therefore the acceleration is towards the center of rotation. And here in this case, you have the friction forces that do the same thing and make the bicycle rotate. So without friction, this bicycle wouldn't be able to rotate. It would just slip, I don't know, maybe in this direction. Now, why is it that we can write down the centripetal acceleration like this, in this form? Well, if you look at this bicycle here, then if you want to calculate the centripetal acceleration of the bicycle, so right now this is the center of mass, and this is the instantaneous center of rotation, and the distance between the center of mass and this point is r. So it's like the radius of a circle, right? So if you have some kind of circular motion, then that would be your center of rotation, and this would be your r as your object travels in the circle. And so if you want to calculate the centripetal acceleration, you would take this v here, right? Remember, you have the slip angle here, the slip angle of the vehicle. You take this v, you square it, and you divide it by r. And that's how you can calculate the centripetal acceleration of the vehicle in this point. Now, the thing is that in the lane changing problem, the turns are so small, and therefore the slip angle, they are so small that we can simplify our problem and we can neglect it. And instead of v, we could just write our longitudinal velocity here. So we could write it down like this: small x dot squared divided by r. So it's a simplification because the slip angle is just so small that instead of using v, we can just take our constant longitudinal velocity that doesn't change in magnitude but changes in direction, and we can approximate our centripetal acceleration like this. When you have an object moving in a circle, and this object has some kind of velocity, and this is the center of rotation, and this is the distance, then you can calculate the angular velocity of that object like this. V equals the angular velocity, let's say that it's theta dot in this case, times r, right? And the theta dot is in radians per second. And if you multiply it by the radius, then you get this velocity, which means that you can calculate theta dot like this: v divided by r. And in our case, we have psi dot. Therefore, psi dot equals small x dot divided by r. So in that case, we can also write that our small x dot, our longitudinal velocity, is psi dot times r. And so now, since here we have this small x dot squared divided by r, we can also write it down like this: x dot times x dot divided by r. And so what we can do, we can just substitute it like this: psi dot times r times x dot divided by r. So the r's cancel, and there you go, you are left with this expression. So this is your centripetal acceleration. Well, to be more precise, it's an approximated centripetal acceleration because we forgot about this slip angle here. And so just to make clear why we could have this kind of relationship where the velocity equals the rotational velocity times r, it comes from this fact that when you have the circle here and you have this angle theta, which is in radians, and then this is this part of the circumference, not the entire circumference but part of it, and so if this is r, this distance d, you can calculate d equals r times theta. So when theta is in radians and you multiply it by the radius of the circle, then you get the length of the arc. Now if I now take the derivative of d, then essentially it's this velocity, right? So it's the change of d with respect to time. And now you have this multiplication rule, right? So you first of all have r dot theta plus r theta dot. It comes from calculus, the multiplication rule. And so since the radius is constant, the radius doesn't change in time, so this term is 0. And that's why you're left with d dot, or v, equals r times theta dot, which is essentially, in our bicycle example, psi dot, yaw dot. And so finally, when you now look at this part of the equations of motion, then you can rewrite it like this: fyf plus fyr equals m, and instead of ay, we can rewrite it like this: y double dot plus small x dot psi dot. And then this equation is then for the moments. Welcome back. Here, very quickly, I want to explain to you better why the lateral acceleration equals y double dot plus x dot times psi dot. So you have a vehicle that goes from configuration 1 to configuration 2. You can work either in the inertia frame, which is fixed to the ground, or body frame, which is fixed to the vehicle. And so when the vehicle rotates, then the body frame rotates with it. And due to the fact that the body frame rotates with the vehicle, we chose to work in the body frame because it simplifies our equations. If you go from configuration 1 to configuration 2, and the magnitude of y dot stays the same, and by magnitude you could think of it as the length of the arrow. If from this configuration you go to this configuration and the length of the arrow y dot stays the same, then that means that y double dot equals 0 meters per second squared. That is because even though the y dot vector changes its direction in the inertia frame it was first like this, and then it was like this, as you can see it here. So here you can see that the magnitude of y dot didn't change, and actually the vertical component of y dot didn't change that much either. But what changed was the horizontal component of the vector. And so you can see that in the inertia frame, the direction of y dot did change. But in the body frame, it hasn't changed its direction. In the body frame, the direction of y dot is still the same, and that is because the x dot and y dot vector are attached to the xy body frame. So here you have your x dot, your y dot, your x dot, and your y dot. So the x dot and y dot, they rotate together with the body frame. So the term y double dot appears when in the body frame the magnitude of y dot changes. For example, if in the first configuration that was your y dot, and then in the second configuration your y dot becomes bigger, that's when your y double dot appears. But if the magnitude of y dot doesn't change, then y double dot will become 0, and that is because you are working in the body frame. If you had worked in the inertia frame, then also the change of direction of y dot would matter. And then even if the magnitude of y dot had stayed the same, still you would have had a change in this vector. But we worked in the body frame. And so the presence of y dot meters per second indicates that there is a bit of slipping in the turn, which can be so small that you might not even see it. And y double dot meters per second squared indicates that this slipping has gotten bigger or smaller. The other term, which is this one, which is the centripetal acceleration term, appears because the body frame is rotating with respect to the inertial frame. If the body frame didn't rotate, the second term would be 0 meters per second squared, because psi dot would have been 0 radians per second. And so this term would have been 0 meters per second squared. So in conclusion, A sub y equals y double dot plus x dot times psi dot. This first term, y double dot, is the change of the y dot vector in the body frame. In other words, it is the lateral acceleration of the vehicle, assuming that the body frame is not rotating. But in reality, the body frame is rotating, so you have to add the centripetal acceleration to account for that rotation of the body frame with respect to the inertia frame. So this is like a correction factor. It accounts for the fact that your body frame is rotating with respect to the inertia frame. This first term assumes that you're not rotating, and the second term takes into account that you are rotating. And it makes sense because the centripetal acceleration makes objects rotate. And if you attach a body frame to the object, then that means that the centripetal acceleration makes the body frame rotate as well. That is why you have two terms here in this lateral acceleration. Again, if you had worked in the inertia frame, then even if the magnitude of y dot had remained constant, then y dot in the inertia frame would have still changed its direction. It was like this, and now it's like this, and that's your change. Let's say delta y dot. And then in the inertia frame, you would have had y double dot. And so that's why you also have acceleration when your velocity vector changes its direction but does not change its magnitude, because when your velocity vector changes its direction, then that means that there is some kind of change in the components of your velocity vector. And also, if we had worked in the inertia frame, then the second term would have been 0. But then you would have had to consider acceleration and forces both in the inertial x and y direction. So in the inertial case, this would be your inertial reference frame, and then you would consider forces in the x direction and also in the y direction. And so you would have had acceleration in the x direction and also in the y direction. But since we work in the body frame and we only deal with lateral control on a straight road in a lane-changing maneuver, then we can only consider the lateral forces and accelerations. So that would be your net lateral force, or the sum of the forces in the lateral direction, and the acceleration in the lateral direction. However, since the body frame itself rotates with respect to the inertia frame, then you have two terms. You have one term which is dy dot over dt, which is essentially your y double dot, and that is the lateral acceleration assuming that the body frame is not rotating with respect to the inertia frame, plus the centripetal acceleration that makes the object and therefore the body frame rotate. And that's why our lateral acceleration had these two terms. The second term accounts for the body frame rotation.
Finally, I want to show you why the centripetal acceleration is A sub c equals v squared over r. Have you ever wondered why it's like that? When you travel in a circular motion, and let's say this is a circle and you are here, and then your velocity is in this direction, have you ever wondered why the centripetal acceleration that points towards the center of the circle, why this thing is v squared over r? I don't want you to take anything for granted, so I'm going to show you why it's like that using calculus. So let's say that this is your center of origin here in the center of the circle, and then you have some kind of body that travels at a fixed velocity v. And then when I say fixed velocity, I mean the magnitude. So of course the direction of the velocity changes, but the magnitude of the velocity stays the same. Now, if this is the center of our coordinate system, 0, 0, and our coordinate system is here, big X and big Y, and if we say that this is the origin, so the X is 0 and then the Y is 0 here as well, then we can have a position vector from here that goes until the body that travels in a circular motion. So this position vector here represents the position of this body with respect to this origin. And we're going to call this position vector P, arrow. We're going to say that the magnitude of this position vector is R. And the magnitudes of vectors are denoted with an absolute value. So if you take a vector and you put it inside an absolute value, then you say that it's the magnitude of that vector. So in this case, it's the length of this vector. And the length of this vector is r. We also said that the magnitude of the velocity vector is constant. So we can write it like this. It means that this body here rotates at a fixed rate. It doesn't rotate faster and it doesn't rotate slower. It rotates at a fixed rate, at a fixed radians per second. Now if the magnitude of the velocity is constant, then you can also write it like this. D, the absolute value of velocity with respect to time, equals 0. And this is a calculus way to say that something is constant, because that means that the magnitude of the velocity vector doesn't change in time. The change of this magnitude is 0. And therefore the variable itself, which is the magnitude of the velocity vector, the variable doesn't change. But okay, let's decompose this position vector now. This position vector in this coordinate frame has an x component and a y component. And let's say that you have an angle theta here. That means that we can rewrite the position vector like this. P arrow equals r, which is the magnitude of the position vector, times cosine theta. And that would be the x component of the position vector. The y component of the position vector would be r times sine theta. And so now we've rewritten it in a vector form. And then you can also take r out of the vector and put it here as a constant. So you can rewrite this thing like this. Now if you think about it, what is a velocity vector? A velocity vector is the change of the position vector with respect to time. And so you can write it like this. V arrow equals d p arrow with respect to time. So you take the derivative of the position vector. But not the magnitude, but actually the vector. So you take the derivative of each component of this vector. So let's do it. To take the derivative of this vector, we're going to use the product rule from calculus. So first of all, it would be dr dt times this vector cosine theta. Now here you would have sine theta plus r times, and now you take the derivative of this part here, it would be minus sine theta. However, you also have to take the derivative of the theta with respect to time. So you use the chain rule. So it's going to be times d theta dt. And then here it's going to be cosine theta times d theta dt. Now the magnitude of the position vector r is constant. So again you can write it like this. D absolute value p dt. And what do you think you would have here? Well, if it's constant, then it must be 0. But the absolute value of p is r. And therefore it's the same thing. And so since this thing here is 0, then this entire term is 0. So you're left with r, and then I'm gonna take d theta dt's here, and I'm gonna put them here, d theta dt, and then you would have minus sine theta and then cosine theta. And that would be your velocity vector. But now we also want the acceleration vector. And what would be the acceleration vector? Well, the acceleration vector is the change of the velocity vector with respect to time. So it would be d v arrow over dt. So we would take the derivative of this part here. And again, we're going to use the product rule. We're going to say that it's dr dt times d theta dt times this vector minus sine theta and cosine theta plus, then we leave r alone. We're going to say it's r times, now we take the derivative of this term here, so it's going to be the double derivative of theta with respect to time, d theta dt,
and then again this vector minus sine theta and cosine theta, and then plus, we're going to leave these two elements alone, r d theta dt, and now we're going to take the derivative of this guy here, so it's going to be minus cosine theta d theta dt, and here it would be minus sine theta times d theta dt. Okay, again, our radius is constant, so it's fixed. It doesn't get longer, it doesn't get shorter, and therefore this part here is 0, and that makes this entire term 0. Now, what is d theta dt? Well, it's angular velocity, right? It's this radians per second. It's how fast this object rotates in a circle. And we said that since the magnitude of the velocity is constant, then that means that this object here, it rotates at a fixed rate. It doesn't rotate faster and it doesn't rotate slower. It rotates at a fixed rate. So there is no angular acceleration. If d theta dt is radians per second, then the double derivative of theta with respect to time would be angular acceleration. It would be radians per second squared. And so therefore, since the object doesn't accelerate nor decelerate, then this part here would be 0, and therefore this entire term would be 0 as well. And so you're left with only this term here. And we can rewrite it like this. We're going to take these minus signs, we're going to put them in front, then r, then these d theta dt's, we're going to put them as a scalar in front of the vector as well. So it's going to be times, and now it's going to be like this, d theta dt squared, because first of all you had it when you computed your velocity vector, and now when you computed your acceleration, you have another d theta dt in each element that you can put in front of your vector as a scalar. And then you have cosine theta and sine theta. And in fact, you can rewrite it like this, minus d theta dt squared times r, and then cosine theta and then sine theta. And now, if you look at this part here, then what was this part? Well, this part was the original position vector, right? It was this guy. Therefore, your centripetal acceleration can be rewritten like this. Minus d theta dt squared times p vector. Now, in our vehicle example, d theta dt was yaw dot, right? It was radians per second. Now, right now, we have this acceleration in a vector form. So, this minus here, it gives you a direction, right? However, if we take the magnitude of this acceleration, then it would be like this. The absolute value minus d theta dt squared times p vector, and then you close your absolute value. So if you put things inside the absolute value signs, then you can get rid of your minus sign. And so what you're really left with is something like this. d theta dt squared. And we're going to have another absolute value sign here, which is the position vector, which we put inside the absolute values. And so this guy here, it's nothing but r. And so you have the angular velocity squared times r. And if you remember, then our velocity was, in the vehicle example, y dot times r. So in this case, it would be d theta dt times r. That means that d theta dt equals v over r. And so the magnitude of the acceleration vector, which is the magnitude of the centripetal acceleration, would be like this. It would be v squared over r squared times r. You cancel out the r's and you're left with v squared over r. And there you have it. You have the form of the magnitude of the centripetal acceleration. You can also do it in this way. You can say that this vector is this, minus r d theta dt squared times cosine theta and minus r d theta dt squared times sine theta. So now you have it in a vector form, and if you want to take the magnitude of your acceleration vector, then what do? You simply rewrite this thing like this. You would have a square root, then minus r d theta dt squared cosine theta, and this entire term is squared. So essentially you're taking the Pythagorean theorem plus minus r d theta dt squared sine theta, and then this entire term will be squared as well. And you will have a square root that will cover everything. You can rewrite this thing like this. You can factor things out. And in the end, you can have something like this. Minus r d theta dt squared. And then this would also be squared. And then you would multiply it by cosine theta, which is squared, plus sine theta, which is also squared. And I'm going to put square root here, close the bracket. And now what is this? Well, this is a trigonometric identity, right? So this entire thing here would be 1. It comes from trigonometry. This is a trigonometric identity. So you're left with square root minus r d theta dt squared, and then this entire thing will be squared. And the reason why I rewrote this thing like this, well, it's just pure mathematics. If you factor these terms out and use the rules of mathematics, then you will get it in this form. And so if you take the square root of these guys here, you will be left with r times d theta dt squared. And we have already seen how to rewrite this form in this form. And there you have it. That's how you can derive the centripetal acceleration of an object that travels in a circle and whose radius, or the magnitude of the position vector, is constant, and whose magnitude of the tangential velocity is constant. But the good thing about this kind of derivation is that what if your radius is not constant? What if it changes? Or what if the object rotates in a circle faster and faster and faster? Then here, in this kind of derivation, you can take all that into account. So if the radius is not constant, then this term will not be zero, okay, when you compute your velocity vector. And also when you compute your acceleration vector, then again, this term would not be zero. And if the object rotates faster and faster, that means that when you compute your acceleration, then this term here would not be zero. And so you can take into account all the possible combinations. You will just leave these terms there and you'll see what the mathematics shows you. And so thank you very much, and I'll see you in the next video. Welcome back. Now before, the assumption that we made was that when we have a bicycle, then the velocity of each wheel is in the direction of that wheel. That has been our assumption so far. However, this assumption is true when you have low vehicle speeds, but when you have higher vehicle speeds, then you have deformation. And so what happens when you have higher vehicle speeds is something like this. This is your back wheel, then this is your front wheel. So this is your longitudinal axis. This is the direction of your wheel. The angle here is delta. But now, because of tire deformation, what really happens is that the velocity vector of this wheel will not be in the direction of the wheel. It will be somewhere in between the longitudinal axis and the wheel. So it will be something like this. Okay? So that happens at higher vehicle speeds because of tire deformation. And when you turn, then the same kind of thing happens here. Even though your back wheel doesn't turn, still, because of tire deformation, the velocity of this wheel will be a little bit tilted in this way. Alright? And so now we're going to define two new angles. We're going to define an angle here and here. So this angle here, we're going to call it theta VF. F stands for front. And this angle here, we're going to say that it's alpha F. And this angle here is theta VR. And so R is the rear angle. Now, this angle here, theta VF, is the angle that you have between the velocity vector of the front wheel and the longitudinal axis. And now this alpha F, this is a slip angle of the tire. Alright, slip angle of the tire. Don't confuse it with the slip angle of the vehicle. The slip angle of the vehicle, if this is the center of mass, then the slip angle of the vehicle was here. The slip angle of the entire vehicle. But this is the slip angle of the front tire, and it is defined in the following way. Alpha F equals the steering wheel angle, delta, minus theta VF. Alright? And how about the slip angle of the back tire? Well, actually it's the same formula, but in this case, delta is 0. So alpha R equals 0 minus theta, and now VR, which you have here. So the slip angle of the back tire is minus theta VR. So these are the new angles that we need to care about when we drive at higher vehicle speeds, because there is tire deformation. Now the slip angles are important because it has been experimentally determined that for small slip angles they are proportional to the lateral forces. So when you have small slip angles, when this angle alpha F and also alpha R, when these angles are small, alpha F and alpha R, when these angles are small, then they are proportional to the lateral forces, which means that FYF is proportional to alpha F and FYR is proportional to alpha R, which means that there is some kind of proportionality constant there. And in fact, you can write down these forces in the following way. FYF equals 2C alpha F times the slip angle of the front tire. And also for the rear force, FYR equals 2C alpha R times alpha R, which is the slip angle of the back tire. Now, what is this C alpha F and C alpha R? Well, they are cornering stiffnesses. This is the cornering stiffness of the front tire, and this is the cornering stiffness of the back tire. And the reason why we have this factor 2 here and here is because, remember, we went from a car model to a bicycle model. So we have lumped 2 back wheels into one and 2 front wheels into one. And that's why we have this 2 here and here. And again, this is valid for small slip angles. So if I write down an axis here, and I'm going to say that this is force, and this is the slip angle here, alpha, then it would be something like this. So you see, there is this region where the relationship is linear. So you have force and then the slip angle. And here in this region where the slip angle is small, the relationship is proportional. If you take an individual tire, then a C alpha F, it would be like a slope, okay? And so what do you think, what would be the units of the slope? So the units of the cornering stiffness would be newtons per radians, which makes sense because if F equals C alpha F times the angle, right, then it would essentially be Newton radians times radians. They would cancel out and you would have newtons, which is the unit of the force. So remember, this relationship is valid for as long as you are in the region of small slip angles of the tire. Welcome back. Now that we have expressed our slip angles of our tires in terms of delta and then theta VF and theta VR, we can rewrite our forces in the following way. FYF equals 2 times C alpha F and then parenthesis delta minus theta VF. And also the rear force FYR equals 2c alpha r multiplied by parenthesis minus theta vr. So that's good that we can rewrite our forces in this way, because now you see delta, right? In our equations of motion, one of the variables that we needed was the steering wheel angle, because that would be the input into our system. This will be the value that will be provided by the controller that we will ultimately design. Now the thing is that we still need to rewrite this angle and this angle in terms of other variables, other known variables. And so what are the known variables? Well, we have the longitudinal velocity, we have the lateral velocity, we have LF, which is this distance here, we have LR, which is this distance here, and we also have the rate of change of the yaw angle, which is this. So this will be now your exercise, and I'm gonna show you the solutions in the next video and the explanation. Try to write these angles, theta VF and theta VR. Try to write them as a function of these variables. You might not use all of them, but try to do it. And then I'll see you in the next video. Welcome back. So let's try to rewrite these angles in terms of known variables, theta VF and theta VR. So how would we do it? So let's look at the front wheel. So we have a longitudinal axis, and I'm gonna draw the wheel, which it will be here. Now our velocity is in this direction, and this is the angle that we are looking for, theta VF. Now this is our longitudinal axis. This is the white dotted line. And so you can see that we have two components here. We have one component which goes along the longitudinal axis, and we have another component which goes along the lateral axis. Now, what is the component along the longitudinal axis? Well, this is our longitudinal velocity, right? Which in fact is, in our example, 20 meters per second. So we have one component. Now there is another component. Let's call it VL for now. Let's just call it VL. So if our velocity here is this one, and we want to express this angle, then what we have to do, we have to use tangent, right? We could say that tangent theta VF equals VL divided by x dot. Now the trick is to find VL. What would be VL? Well, let's think about it. First of all, when your bike is driving and then let's say turning to the left, first your bike is here and it has its two wheels, the center of mass, and after some time the bicycle is maybe somewhere here, and so you have your wheel here and you have your wheel here, and this is your center of mass. Now what has happened? The center of mass has moved to the left. That's the distance of the center of mass. That means that there is some kind of lateral velocity. So we know that if I draw a bicycle here, we know that in the center of mass there is a lateral velocity because this is the slip angle of the vehicle here, and so because of that you have this lateral velocity which is small y dot. So one component of VL would be this small y dot. But is it the only one? Well, let's look at this point here. Right now you're in this point, and now you are in this point. The center of mass has moved from here to here, but the bicycle has also turned. So this point here is not where the center of mass is. This point is further away. So there must be another component. And so this other component comes from the fact that the bicycle has been turning, and the bicycle turns at a rate of psi dot, so the change of yaw angle with respect to time. If you imagine that your bicycle is first like this, and this is your center of mass, and then let's say that the bicycle doesn't move anywhere, at least the center of mass doesn't move anywhere, but the bicycle has turned like this, then how would you find the velocity in this place? So at the beginning you are like this, and now you are like this. So now, what would be the velocity in this point? Well, if this is LF, and you know how fast you rotate, then this would be like the rotation of a circle. Remember when we had a circle, and then we had a radius, and then you had some kind of V here, and you knew the rotational velocity, let's say theta dot, then you could calculate this V by multiplying theta dot by R. V equals theta dot by R. And the same thing here. So you can say that this point here, assuming that the bicycle is not moving to the left itself, assuming that the center of mass is not moving to the left, that the bicycle is only rotating, this point here, due to the rotation only, has a velocity of LF times and the rotational speed, right? The rotational speed of the vehicle. So LF times psi dot. So even if the center of mass doesn't move anywhere, or maybe it only moves forward, so you have a situation like this, and then a little bit later you are somewhere here, and your center of mass is still here. It has moved forward, but it hasn't moved to the left, but the bicycle has turned, because maybe you have some weird wheels there. And so because of that rotation, this point here does have some kind of velocity, and this velocity is LF times psi dot. Alright? And therefore, this VL that we have here, it has two components. It has small y dot plus LF times the angular velocity of the bicycle. Alright? Now, if we, for example, neglect this term, right, if we make it 0, if it doesn't exist, if it's 0, if you only have this, then essentially what it means is that your bicycle, after being here, after some time, this bicycle will be here, but it hasn't rotated. So this kind of motion would have happened because of this term. But because you also had rotation, you also need to consider this term, LF times psi dot. And so now you can compute this entire thing. You can say that tangent theta VF equals, and now VL is small y dot, which is the lateral velocity, plus the velocity of the front tire due to the rotation of the bicycle. So your bicycle rotates, and because of that, this speed at the front tire is actually higher than the speed of the center of mass. And so all that you divide by x dot. And there you have it. Now, what about the rear velocity? Now, how about the rear velocity? How about the velocity in the back? So, at the beginning, you have your bike like this, and then your bike is like this. So this is your center of mass, and this is your center of mass. So you have moved to here. The center of mass has moved here laterally, right? Now when we looked at the front wheel, then you saw that there was a boost in velocity due to rotation of the bicycle, right? Because the bicycle rotated like this, which means that the back wheel rotates like this. But now, if your lateral velocity is in this direction, and the bicycle, as it turns, it causes the back wheel to turn in this way, So there must be some kind of velocity in this way as well. So in fact, in the case of the back wheel, there is an effect that slows the total velocity down. And well, how would you calculate it? Again, if this is LR and you know how fast the bicycle rotates, then you can calculate this rotational velocity very simply by multiplying LR times the change of the yaw angle with respect to time. But now the resulting velocity that you get is in this direction. So you have this small y dot that is in this direction, but then you have this velocity that is in another direction, because as the bicycle turns, this point turns and moves this way. Now, if you look at the back wheel, then in the case of the back wheel, you also have this tire deformation, and it also has two components. One is this, and the other one is lateral. So the longitudinal component again is just small x dot, and the lateral component, VL, let's say back, would be then again small y dot because of the motion of the center of mass. But now you have this slowing down effect due to the rotation of the bicycle, so you have to subtract. It's going to be minus LR times yaw angle dot, psi dot. And so that means that you can rewrite the rear theta angle tangent theta VR rear, which is y dot minus LR times psi dot. So that's the VL part, and then you divide it with a small x dot. And so if you want to get these angles, then you very simply take the arctangent of these values. So it would simply be theta VF equals arctangent, and so you would just put this thing inside here, and the same thing for this angle. Now the thing is that we don't really like arctangents here, and we don't like them because at some point it's going to make our model very complicated, more complicated than needed, because at some point we need to separate y dot and psi dot, and when they are inside an arctangent function, then it's a lot harder to deal with it. But luckily, if you think about our case, then what are we trying to do? We're trying to change lanes on a straight road, right? And we're driving at 20 meters per second. That means that as we change lanes, our steering wheel angles would be very small. Now, when our steering wheel angles will be very small, then our theta VF and theta VR will be very small as well. And so we can have a small angle approximation. So if you look at the tangent function, so you have an angle here, and so this is your tangent function. So if you think about it, for small theta angles, we can say that tangent theta, let's say VF, is approximately theta VF, right? And the same thing, tangent theta VR is approximately theta VR. And it's because of this, because this is your angle, theta, let's say theta VF, and this is tangent theta VF here. And you see that for small angles, for as long as you stay in this period here and here, the relationship is almost linear. And that's why you can make this kind of approximation. Now this is very good, because now since we can make this kind of approximation, we can very easily write theta VF equals y dot plus LF psi dot x dot, and theta VR equals y dot minus LR psi dot divided by small x dot. Now this is a much more convenient form, because now when we put this inside our model, it will be much easier to detach small y dot and psi dot. And this is actually what is done very often in engineering. This is a typical thing that is done there. We simplify where we can. We lose a bit of precision, but in turn, it will be much easier for us to design our controller. Avoiding arctangent demands less computations by the computer, but more importantly, we will be able to rewrite our equation where we can separate our small y dot from the rest of the variables. So this is called trade-off. This is something that engineers do all the time. Where they can, they simplify. But of course, when you do these kind of tricks, then you have to know when they are valid. So in this case, it's only valid when our theta VF and theta VR, when they are small. So obviously, if you're somewhere here, then it's not valid anymore. Then you get wrong responses. That means that your model is wrong. That means that your controller won't work properly. So you have to, let's say, honor your assumptions. If you already create your model with these kind of assumptions, where you just neglect tangent and you just write it theta, then you have to know that this is only valid for situations where theta angles, where they are small. Just like with the slip angles, where you had your force and then here you had your slip angle. So only for small slip angles you could have this relationship where F equals 2 times cornering stiffness times the slip angle of the tire. It was only valid for small slip angles. If you have big slip angles, then you cannot make this kind of assumption. Then you have to do it the hard way. Alright, so now we have our equations of motion and we have our lateral forces that we have described in terms of delta and then these two angles. And these two angles, we have been able to describe them in terms of known variables as well. So now you have a big exercise, and I'm gonna provide you with the solutions in the next video. But essentially what we want to do, we want to put these equations of motion in the vector matrix form. So your exercise will be the following. If I have a vector here, and I'm going to put here y double dot and psi double dot, and then I'm going to have a matrix, and then here I'm going to have another vector, and I'm going to write here y dot and psi dot plus another vector and delta. So your exercise now is to fill in this matrix and this vector. Can you do that? So try to do that, and then in the next video I will show you how to do it. Welcome back. So let's try to solve this exercise together. I hope you tried it yourself as well. And so I have written all these equations back up here and also our objective. And so essentially this exercise is about variable substitution. So we're going to start with our equations of motion. So first what we're going to do, we're going to rewrite our forces in terms of these variables here. And let's do that. So m y double dot plus psi dot x dot equals, and now I'm just gonna rewrite the forces, which is 2c alpha f delta minus theta v r plus 2c alpha r minus theta VR. Okay, now we have that. Now let's open up this equation. We can open up like this. M times y double dot plus m times psi dot x dot equals now 2c alpha f times delta, and now minus 2c alpha f times theta v. Now this is actually f, right? It should be f. So I made a mistake here. So this is f, and then minus 2c alpha r times theta v r. Okay, so we have done that. Now what we have to do, we have to substitute these angles with these variables here. So what I'm gonna do, I'm gonna leave this term here on this side, but this term will go to the other side, minus m psi dot x dot. Now I'm gonna write this term here, minus 2c alpha f, and now I'm gonna put this part here, which is y dot plus lf psi dot divided by x dot, and minus 2c alpha r, and now this part here, y dot minus lr psi dot divided by x dot. There you go. Oh, and we also need to add this term here. I put it in the back. The reason why I put it in the back is because I want delta here. So 2c alpha f delta. Okay, so now what we have to do, we have to open up these parentheses here. Well, first of all, what we can do, we can get rid of m and here, and that means that here we have to add it, and here we have to add it, and also here we have to add it. So you see, I'm with y double dot here, and that's what I need here. So y double dot equals minus psi dot x dot, now minus 2c alpha f times y dot divided by mx dot minus 2c alpha f times lf psi dot, and divided mx dot, right? And the same thing here, minus 2c alpha r times y dot divided by mx dot. And now be careful here, minus and minus, so you have plus 2c alpha r times lr psi dot m small x dot comes here, plus 2c alpha f divided by m, and you have delta here. Now what we need to do, we need to factor out y dots and psi dots, right? So we can rewrite this entire equation, y double dot equals, now the first thing is, I'm gonna write down this thing here, minus 2c alpha f divided by mx dot, and also have another term with y dot, so it's gonna be minus 2c alpha r. Remember, these are different cornering stiffnesses. So this is the front wheel cornering stiffness, this is the back wheel cornering stiffness, and we divide that with mx dot, and so we close the parenthesis, and we have y dot here. So we have factored out y dot. And now we have to do the same with the psi dot. So what do we have here? We can put it down like this, plus parenthesis. We have one term here, which would be minus x dot. Then this one, minus 2c alpha f times LF divided by mx dot. And here I have plus 2c alpha r times LR divided by mx dot. And so this one has this variable here. So I have factored it out from all these three terms, plus c2 alpha f divided by m and delta. So now you can already see that if you look at this one, since it's going to be a 2 by 2 matrix, then since this is y dot here, then this entire thing, let's call it A, this entire thing will go here, right? And now this entire thing here, let's call it B, will go here. And of course we could have simplified it by having a common denominator, but that's just a mathematical formality. And so now we have this, and now we have to find two more terms here. Oh, and also this one is E, let's call it E, and E will be here, and so here we will have something else as well. Welcome back. So let's finish this exercise now and find the remaining parts of the matrix, which will be C, D, and F. So again, it will be a variable substitution exercise and a mistake avoiding exercise as well. So let's see, now we're gonna work with this equation of motion, right? The one with the moments. And well, it's gonna be similar. So I psi double dot equals LF, and now instead of this force we're gonna write down this one times 2c alpha f delta minus theta vf. Alright, and now minus LR and 2c alpha r minus theta vr. Now we can now make this a plus, and so now what we have to do, we have to substitute these angles here again with these formulas. So let's do that. So I psi double dot equals LF 2c alpha f. So LF was the distance between the center of mass and the front wheel, and LR was the distance between the center of mass and the back wheel. So okay, I can rewrite it like this. I'm gonna put delta minus LF 2c alpha f, and now instead of this angle I'm gonna write this one. So y dot plus LF psi dot divided by x dot, right? And then plus LR 2 C alpha r, and now this angle here, which will be y dot minus LR psi dot divided small x dot. Great. So we have this. Now what we can do, well, we can get rid of this mass moment of inertia here if we divide it on the other side like this. Then we can put it here and here. And so the next step would be just to rewrite the entire thing and open up these parentheses. Okay, and again we have to now separate or factor out these variables y dot and psi dot. Okay, and there you have it. And so what we can now do, we can say that this one is C, this one is D, and this one is F. So CDF. So C will come here, D will come here, and F will come here. So there you go. We have taken our equations of motion. We have figured out how to write the forces in terms of delta or steering wheel angle and other variables. And now we have rewritten our entire system in this form, where we have a lot of constant terms here, because if you look at them, these are all constant terms. They don't change in time, right? A, B, C, and D. So here I have A, B, C, and D, and also E and F. They're all constant. They don't change in time. And that's also because we have a constant longitudinal velocity. If our longitudinal velocity was not constant, then these terms here, A, B, C, and D, these matrix elements, they wouldn't be constant either, right? Because you divide everything by the longitudinal velocity. So the fact that it's constant, it also makes this matrix constant, and that is good, as we will see in the future, because that will make the design of our controller much simpler. And so just to make it explicitly clear, you can get this form that we have here if you just do matrix vector multiplication, right? So essentially, if you write the system out in a non-vector matrix form, then it would be y double dot equals, so this double dot equals A times y dot plus B times psi dot, right, plus E times the steering wheel angle. And now you have psi double dot equals C times y dot plus D times psi dot plus F times delta. Now the equations here have become pretty long, and perhaps now you're beginning to lose the connection with the physical explanation. Well, just remember that for example y dot is just the lateral velocity, and psi dot is just the angular velocity of the bicycle, and delta is just the steering wheel angle of the front wheel. Psi double dot, it's the angular acceleration of the bicycle, and then y double dot is just the change of the lateral velocity with respect to time. And so A, B, C, D, E, and F, they are composed of all the information that we had given to our bicycle. That, for example, LF and LR, their dimensions, C alpha R and C alpha F, they are cornering stiffnesses. I is mass moment of inertia, and small x dot is the constant longitudinal velocity. So in the next video, let's talk more about this form. Let's talk about why we put our equations of motion in this form, and why is it so good to use them to design controllers. So see you in the next video. Thank you very much. Welcome back. So let's first talk about this format here. This is a very important format actually. This format is used in this open loop section. So now I'm going to try to explain to you what actually happens here in this open loop box. What actually happens here is integration, right? You get your input, which is the steering wheel angle, and you get your outputs, and the way you get those outputs, you integrate. And in the open loop system, the equations are normally in this format. And now, what is so special about this format? Well, this format here is called a state space equations. What are state space equations? State space equations are first order differential equations. It means that you have something like this. x1 dot equals, let's say, a times, and now these are just random things. So a times x1 plus, let's say, c times x2 squared plus, and let's say, d times x3 cubed, right? And now, so you have three variables, x1, x2, and x3. And now you have x2 dot equals, let's say, c squared times x1 plus sine, these are just random examples, sine x2, and let's say you also have x3 here, x3 dot equals f times x1 cubed, and etc. So an example like this, so f, c squared, a, c, d, these are all constants, okay? And you can see that here you have some non-linearities, and so a nonlinear function is a function which is not like this, right? A linear function would go through zero and it would be a straight line function. But we also have functions that are not linear, like for example this one, sine, and also x2 cubed and x3 cubed. So these are state space equations, and as you notice, they are first order differential equations, right? So you x1, you have x1 dot that depends on x1, x2, and x3, and x2 dot and x3 dot. And these state space equations, they can also have inputs, right? Like in our case, we have delta, and then they can have, let's say, u1 plus u1 plus u2. These are like system inputs, like our delta here. Now you might ask yourself that, is our system a state space equation? Is our system a first order differential equation? And you might think that no, you have a y double dot here and psi double dot. Well, that's true, but you have y double dot with respect to y dot and psi double dot with respect to psi dot. So you have y dot and then you have y double dot, right? And so you have psi dot and psi double dot. And so this could be like x1 and this x1 dot, right? And this could be like x2 and x2 dot. So actually it is a first order differential equation with respect to the variables that you have here, which are y dot and psi dot. And these variables here, since it's a state space equation, right, then these variables here, y dot and psi dot, they are called states, all right? States. And now you might ask yourself, what are states? So the meaning of states in control engineering is that states are the variables that we need to describe how our system behaves. So again, they are the variables that we need to describe how our system behaves. In our case, our system is the car. And for example, y dot and psi dot, right? The change of lateral velocity with respect to time and the change of yaw angle with respect to time, they describe the behavior of the car. They tell us the lateral and angular velocity of the car. And you can have many states. Like for example, you can have a state like a temperature on the body of the car, right? But is this information relevant to achieve our control object? Do we need to know the temperature on the body of the car? Well, not really. So we don't choose it as a state. We try to keep the amount of states at its minimum, to keep things simple. So usually the rule is as much as needed, but as little as possible. And we try to simplify where we can, like the small angle approximation. Do you remember this small angle approximation? Like tangent and then theta VF, and then we said that it's just theta VF. Well, that's valid when this theta VF is small. And so we can make this kind of approximation for as long as we honor this condition that this angle is small. We can make this kind of approximation. Now, knowing what the states are, this will be your exercise, and I'm going to tell you the solution in the next video. Do you think we have all the states we need to control our car? So we have y dot and we have psi dot. They are our two states. They are here, right? And this state space equation, when you multiply these constants by the states and also you add your inputs that you also multiply by some constants, right? Then you get the derivative of your states, right? So that's why it's called the state space equation. That here you have your states, and also your inputs. And when you multiply them by some constants and add them together, then you have the change of your states, right? You have the derivative, the first order derivative of your states. So that's why it's the first order differential equation, which is state space equation. This is your state, and this is your state, and this is your input, and what you get is the first order differentiation of your states, okay? Y double dot and psi double dot. So it's a system of equations, a system of differential equations, and in this case we have the most general state space equations, which are called non-linear state space equations. But then later on we will see that there are also linear state space equations and linear time invariant state space equations and linear time variant state space equations. So I'm gonna talk about it in the next videos as well. But now again, your exercise is this. Do you think that we have all our states, or do we need some more states to describe our system here to achieve our goal, right? So we have a road, we have some kind of road, we have lanes, and we want to achieve the lane changing maneuver, which is following this trajectory. Do we have all the states we need, these two states, to achieve that? See you in the next video. Welcome back. So in the previous video, the question was that, do we have enough states to control our system, which is our car? And the answer for that is no. We don't have enough states for that. Because remember, we also have our outputs, global Y and psi, right? These are our outputs. We compare them against the reference values, YR and psi R, right? So these are our outputs. Now normally the way it works is that the outputs are just the states that you choose. So let's say if my states are Y dot and psi dot, and then also psi and Y, and I say that these are my outputs. So right now I have 4 states, but I say that, okay, I need 2 outputs because I have 2 reference, let's say data, 2 reference variables that I need to compare it against. So I have global YR and psi R, so I need 2 outputs, Y and psi, and I have 4 states, and out of these 4 states I choose 2 states and I said that they are my outputs. Okay, but that means that we need more states, right? Right now we only have Y dot and psi dot, but we need psi and Y. So how do we incorporate these missing states into our existing state space equation? So a standard procedure is like this. You do it through variable exchange, all right? So, or variable substitution. So let's say our first state is small y dot, and let's call it x1, right? Now our second state, let it be psi. This is what we need, right? We don't have it, but we want to incorporate it into our existing state space equation. So our second state is psi. We say it's x2. Our third state is psi dot, and we say it's x3. And then our fourth state would be the global y, and we say it's x4. So now our states are x1, x2, x3, and x4. Now, the state space equation is a set of equations, or a set of differential equations, where on the other side of the equation sign you have the first order derivative of your states. So now if I take my state x1 and I say that x1 dot, then what would be my x1 dot? Well, it would be y double dot, right? Because x1 is y dot, so x1 dot is y double dot. So x2 dot would be psi dot. What about x3 dot? Well, it would be psi double dot, and then x4 dot would be big Y dot. Okay, and so now what we can do, we can rewrite our state space equations in the following way. Just gonna do it here. So instead of these variables that we had before, we're gonna use our new variables. So x1 dot, and by the way, these x's, they're completely different from these ones here. This was just like a dummy example of a nonlinear state space equations. So here I have x1 dot, and that would be then a times x1, right, because x1 is y dot, plus b times x3, right, plus, and by the way, in control engineering, when you deal with general equations, then inputs are usually denoted with a small u. So we could say that our input delta would be u. So that means that we would have E times u. Okay, now let's continue. We have x2 dot, and what is x2 dot? Well, it was psi dot, but also x3 is psi dot. So we're gonna write it down like this, x3, then we have x3 dot, which is psi double dot, equals, and then I have c times x1, right, plus d times x3, plus f times u. And finally, our x4 dot is the global y dot, right? So it's the global y coordinate. Now, how did we calculate it? If you remember, we had a picture where we had a global x and global y, and then you had a car. It had a body frame which was small x dot, so small y dot, so the longitudinal velocity, and then the lateral velocity. And so if we want to know, let's say, x, the big X dot, then we had to decompose this vector and this into the x dimension. So that would be then, let's say if this is psi, then you would have cosine psi. Now minus, because you have the other component that goes in this direction, that comes from here, from the lateral velocity, minus, oh, and of course you have to multiply it by x dot, and here it would be minus sine psi, and you multiply it by the lateral velocity, right? But now we didn't need that, we needed the other one, we needed the big Y dot. So the big Y dot would then be the longitudinal velocity times, now it would be sine psi, plus lateral velocity times cosine and again psi, right? So look, this is one of our states, right? Y dot. What was Y dot? Well, it was x1. That means that I can say that x1, which is y dot, times cosine. Now what is psi? Psi is x2, and plus, and now I have small x dot. But remember, this is our longitudinal velocity, which is constant. It doesn't change. So in our case, in our course, this forward velocity is constant. And then we multiply it by sine, and again it would be x2, okay? And so in these new variables, this would be your state space equation, your entire state space equation that incorporates now all the states that you need, okay? Now, we are more used to these variables, right? We want to have these variables. So we can just rewrite them. We can just rewrite the entire thing where we say that x1 dot would be y double dot equals a times y dot plus b times, again, omega dot plus e and then delta. Now x2 dot equals x3, so essentially it would be just psi dot equals psi dot. Then you have psi double dot equals c times y dot plus d psi dot plus f delta. And finally you would have big Y dot equals Y dot times cosine and then psi plus small x dot times sine and then again the psi angle. So you can also rewrite your state space equation in this form. So now we have our state space equations here, and now the question is, why did we have to put our system in this format? So if you remember, we just started from our car model, we derived our equations of motion, right? And then we reformulated our equations of motion into state space equations. Why did we do that? Well, it turns out that in control engineering they are a very useful form, and one of the benefits is that it's easier to deal in this box here. But now, since we have our state space equation here, then it makes our life easier. We don't actually have to perform this numerical integration in this box. So let's say that our lane changing maneuver, its duration is 7 seconds, right? So we go from time equals 0 to 7 seconds. And our sample time is 0.1 second. Now the sample time being 0.1 second means that this loop completes one cycle in 0.1 second, right? So it's 10 hertz. So that means that if you have your outputs here, y and psi, then let's say that if my delta here is I minus 1, then my y would be I and my psi would be sub I as well. And so in the end, what we really want coming out of the box are all our 4 states. We want our new y dot, and if our delta is I minus 1, then this would be I. Then we want psi I, we want psi dot I, and we want big Y I. Okay, so these would be our new states, right, that we get out of the open loop box. And then out of our states we choose our 2 outputs, right, this and this. And so once we have chosen those 2 outputs, then they will be compared against their reference values. Now the question is, once you have your system input, how do you get this next state, this state after one sample time, right? So if this is 0.9, then this would be 1. How do you get that? Well, it turns out that it's pretty easy when you have the state space equation form. And the reason for that is because here you have your states, and then once you know your states and you know everything else like A, B, C, D, E, F constants, then you can right away know the first derivative of your states. And this is very useful because, well, let's go through it. And so here on this axis I will have my y dots, right? And then here I will have my, well, I'm going to put it here, I'm going to have my psi, right? Psi dot and y, right? These are my states. Now I always need my initial states, okay, because I need like a starting point. I always need a starting point. So I'm just gonna say that my small y dot 0 at time equals 0 seconds. It's the very first. Let's say it's 0.1 meters per second, and then okay, this will be 0 radians. Then this will be maybe 0.2 radians per second, and y could be maybe 10 meters, right? So these are your initial states, okay? And so once you know all your initial states, right away your computer can compute their first derivatives, all of them, right? You just put them here into these equations, and then the computer calculates the first derivative of all of your states right away. You know, y double dot, psi double dot, and your big Y dot, right? So that's good, because let's say this is 0.1 here, right? Then this would be 0, and then this would be 0.2, and let's say this would be 10 meters. And so let's say that we have some kind of well, function here, and so at time equals, and this is the time axis, by the way, this time, at time equals 0.1, we want to know our new state. What is this new state? And also here, new state, and the new state, what is it? Well, actually, since we have our derivatives, our first order derivatives of all our states at time equals 0 seconds, so that means that we know right away the slope of this curve, at this point at time equals 0, the slope of this curve, and the slope of this curve here. Now, if we know that, then we can very simply calculate a new state with this numerical equation, which of course is an approximation. So our new state, y dot at 0.1, would be y dot at 0 plus, and since we know our y double dot, we just multiply it by the sample time, right, which is 0.1 second. And the same thing for psi at 0.1, psi at 0 plus psi dot times ts. And also the same thing for psi dot at 0.1 second, psi dot at 0 plus psi double dot times the sample time. And finally, y at 0.1 would be y at 0 plus y dot times ts. Okay, so now when we do that, right, then you have this initial slope, right? So these first order derivatives, they give us the slope at time equals 0 seconds, right? So you have this first order derivative. So this slope here, now I'm gonna extend it to here, right? And this is all slope at time equals 0 seconds, not 0.05 or anything. This is all the slope at time equals 0 seconds, and I just extend it over the entire period. And so what you have this triangle, right? And then you have this delta y. And since you have this delta y, right, this would be your change in the vertical direction, and then your ts is your change in the horizontal direction. Now that means that actually your y dot here is delta y over ts, right? That's your y dot. So if you multiply this by ts, then they get cancelled out and you're left with delta y. So essentially you would have y 0.1 equals y0 plus, and then you will have delta y, right? So you were here at the beginning, you were here at time equals 0 seconds, and at time equals 0.1 second, you are here. So as you can see, it's an approximation. You didn't quite reach the exact point. It's an approximation. So, but still you are following the curve in this way. Now, once you have done that, right? Once you're here, then you have your new state, right? You have your y at 0.1, right? And the same is true for the other states. So you will have your new set of states. And so you have them here, you choose your outputs, and then you compare them against the reference values. And then you have the error, it goes into the Model Predictive Controller, and so the controller calculates the new system input. And once you have your new system input, then you have to find your new states. So that means that you have to find y dot at 0.2 and psi at 0.2, okay? And psi dot at 0.2 and y at 0.2. And so your previous state would now be y dot at 0.1, psi at 0.1, psi dot at 0.1, and y at 0.1, which you put inside your state space equations, and then you will get new y double dot 0.1, psi dot 0.1, psi double dot 0.1, and y dot at 0.1, which are your new derivatives, which are your new slopes, right? So your new slopes at time equals 0.1 second. So you put your new states in, you get your new derivatives, and then you get the states one sample time later, right? So, and using this information, you calculate the states at 0.2. Again, it goes into the loop. You get your new input, and then these numbers become 0.3. These numbers here become 0.2. The numbers with 0.2 enter into these equations, and you will get the new derivatives at time equals 0.2 seconds, which are the slopes of these four functions at 0.2 seconds. And so that's how you go with an interval of 0.1 second until you reach 7 seconds. So I have rewritten this algorithm for one state, for y dot, in a general way. So starting from 0 up until 7 seconds. So just pay attention to these sub-indices here. So again, once you have 0 here, 0 here, this is the derivative of the state at time equals 0 seconds. You get the new state, then again 0.2. Here you have 0.1, 0.1. And if you want to generalize it, then you can have I here, I minus 1, and I minus 1 times TS. Now, this is the easiest way to do it, and this is the easiest method, and it's also the most imprecise method. And of course, there are more advanced methods out there. But can we improve this method? Can we still use this method but improve our precision? Because remember, we had an error, right? When you had time and then you had some kind of state, let's say y, and then at some point you had some kind of error, right? Because our new state was here but not here. So you had some kind of error here. So can we make this entire thing more precise? Well, yeah, it's not actually very hard to do, because what you can do, you can just chop your sample time into smaller pieces. And this is what I did in the code. In the code, I chopped my sample time into 30 pieces. So what that means is that if I draw a timeline here, and by the way, this one, I did it for one state, but it's the same for the rest of the 3 states. And now I'm also going to do it only for one state, and it would apply to other states as well. So I'm just going to do it again for y dot, small y dot, and let's say that this is 0.1 here, right? This is time equals 0 seconds, 0.1 second. And well, in my code, I chopped this timeline into 30 pieces. Now I'm just gonna chop it into 5 pieces. So that means that I will have here 0.02, 0.04, and 0.06, and 0.08. And so if I have my initial state y dot at 0, and then I have some kind of function here, well then I will just apply this algorithm, but many more times, even though the control loop will still be at the sample time of 0.1 second, right? I'm not changing the control loop. The control loop stays the same. The controller still calculates a new delta every 0.1 second, right? But what I'm modifying this method of getting the most precise states. Okay, so that's what I want. So what I'm modifying right now, I'm modifying things inside here, inside this box. So essentially, once I have my new delta, right, then my new delta will be the same for the entire period, right? For the entire period, I will have my new delta. And remember, this delta, I use it here, right? I use it here, and I use it here to compute these derivatives. So I'm gonna use the same delta that my controller gave me, both here at 0.06, 8, and 0.1. Alright? So essentially, what I'm gonna do, I'm gonna write my equation in such a way that, okay, my y dot at 0.02 equals y dot 0 plus, once I've put my initial state into this equation and other initial states as well, I will have my y double dot times, and now of course I'm not gonna multiply it by ts. I chopped ts into 5 pieces, so I have to divide it by 5, right? So I'm gonna divide it by 5, and so what I'm gonna do now, I'm gonna have my initial slope here, right? And I will still have some kind of error, I guess, but this error will be much smaller. And so I will have my new state at 0.02 seconds, right? And now what I'm gonna do, I'm gonna put my new state at 0.02 seconds, and the same applies to other states. I'm gonna put them into these equations, and I'm gonna get my new y double dot at 0.02, right? But remember, delta is still the same. Delta will be the same here and up until 0.1 second, when then the controller will give me a new delta for the period of 0.1 to 0.2. Okay, so that's important to know. And okay, then I think you already know the next step. The next step would be 0.04 plus equals y dot 0.02 plus y double dot 0.02 times ts, and remember, divided by 5. Okay, and then again I will have my new slope here, and again it will follow the same procedure, and you'll be here, here, and then once you reach your 0.1, right, then this state here, this will be what comes out of this box. This entire procedure, it's the inner, let's say, inner loop procedure, right? So it stays here, it stays inside the loop, right? And what comes out of the box is this final value, right? But the reason why I do it with more iterations is because thanks to these extra iterations, my final answer will be more precise, because at each sub interval I calculate a new derivative, and that new derivative will give me a more precise new state in each sub interval, and therefore in the very end I will get a more precise answer. Just to be clear, this loop still works at 10 Hz. The controller calculates the new input still every 0.1 second, but here inside this box you will have this extra inner loop to increase the precision of your final new states, okay? And the same thing applies to old states. So right now I did it only for one state, but I could have done it for the 3 other states as well. And I also want to point out that, you see, that's one of the advantages of the state space equation. It allows us to compute the new states inside this open loop box in a quite an easy way, using an easy algorithm. Of course, for a human it's a lot of computation, but for a computer it's nothing. You just put it inside a for loop somewhere and you just let it run. So that's a good thing about it. And also I want to point out that there is an error here. Here it should be I minus 0.1, and also here I minus 0.1, and we are not assuming the extra iterations here. So, and also here with the delta, it should be also I minus 0.1. Alright, so that's what's gonna be happening inside this box. And now in the next video I want to talk about why we put these state space equations in the vector matrix form. You will see that it makes the design of the controller much easier, and we're getting very close now to starting designing the controller, because we're essentially done with the open loop system. We know what's happening inside. Essentially this algorithm, but with inner iterations, right? And then in a couple of videos, once I've explained to you this part, the vector matrix notation, then we will start designing the controller itself. So thank you very much, and I'll see you in the next video. Welcome back. So before we start talking about this vector matrix notation, just very quickly I want to go over this algorithm again that we're going to be using in this open loop box. This is the algorithm that we will have in the code, and so this algorithm is about going from the system input delta to the states on the other side of the box, right? So remember, our sample time was 0.1 second, so after 0.1 second you would have a new set of states here, 4 states, y dot, then psi, psi dot, and the big Y. And the way you calculate the new state is the following. Now we are using the more precise approach, where we cut our sample time into 5 equal pieces, and so that means that the algorithm will work like this, that your new state y dot, the next state y dot that you will calculate will be at time equals 0.02, and then that will be calculated by putting here y dot at time equals 0 plus y double dot, which is the derivative of the state, at time equals 0 times sample time divided by 5. Now the next state that you will calculate will be at time equals 0.04, and your previous state now will be y dot at 0.02, what you get from here, right? And so that will be your previous state now, and you will also have a new derivative of that previous state, which you will get by putting this thing, right, into your state space equation. And also you would put the psi dot at time equals 0.02 into your state space equation, and then you will get your y double dot at time equals 0.02, again multiplied by ts over 5, and the same thing here. So this is the general version. So now you have I minus 0.02 and y double dot I minus 0.02. And now the important thing that you need to notice here is that this delta 0, right, which is your initial system input, this applies to the entire period of the sample time. So this entire thing here, it's the ts equals 0.1 second sample time, because you go from time equals 0 to 0.1, right? So for that period of time, for all these 5 iterations, you will use 1 delta. And the final answer that you get from here, once you get your y dot at time equals 0.1, it's this one that comes out of this red box, okay? Everything else happens internally, but the final calculation, the final state that you calculate at the end of your sample time, is the one that comes out of that box, okay? And then you go through the loop, the controller calculates a new delta, and this new delta, it will be applied to the new set of iterations. So now you go from 0.1 second to 0.2 seconds, and you use 1 delta in these equations, right? These deltas will go into these equations, and so this delta will be used for this entire period, for this entire time period from 0.1 to 0.2 seconds. And so you have these 5 iterations here with the interval of 0.02, and the final one, once you get to the state at time equals 0.2, it's this one that comes out of this red box, right? And then again you will have your new delta up until you reach your final, let's say, final state at time equals 7 seconds. That's when you complete your maneuver, your lane changing maneuver. And this is only for one state, y dot, and the exact same procedure happens for psi dot, and y, the big global y. So I just made this video to really clear this thing up. And this algorithm will go into the code, and it will be inside a for loop, and so the computer will be able to make these calculations very fast. So in the next video, let's really start talking about the vector matrix notation. See you in the next video. Thank you very much. Welcome back. So let's talk now about why we want to put our system in this vector matrix form. Well, our MPC controller, on a large scale, I would say we have three different versions of it, so to say. So we have MPC basic, MPC robust, and MPC nonlinear. Now, you have to understand that all what they are, they're controllers. And what are controllers? Controllers are computer algorithms. They are some kind of computer algorithms that are implemented later on in the code, that take in errors as their input, and then they give you a system input, in our case delta, they give it as an output, right? So essentially you have your controller, right? You have your error coming in, and your system input comes out. And what's here inside the box is just an algorithm, right? So some kind of algorithm that, based on your error, computes the right delta. And MPC is an optimization algorithm, so it's very much related to optimization mathematics. So we're gonna obviously write it all down mathematically, so you will see how all the math works behind it, and it will become very intuitive for you. And I'm gonna talk about the optimization as well. But on a large scale, what you need to understand is that this algorithm that you have here, it tries to find the best possible delta to minimize the error. And not only the error, essentially your MPC will try to minimize the error and also minimize the change in your delta. So obviously you could minimize your error very fast by being very aggressive, by turning your wheel very aggressively. But if you turn your wheel very aggressively, then it might not be very comfortable for the passengers of the car, right? So what MPC tries to do, it tries to find a compromise between minimizing the error and minimizing in how much the front wheels turn. The MPC will try to find like a compromise, and so it will try to find the best delta for that compromise. So it's an optimization problem. And so there are MPC basic, robust, and nonlinear. So essentially this is the easiest version. The basic is the easiest version, and MPC robust just has more elements to it, and MPC nonlinear also has more elements to it. And so MPC basic, it's very good for linear systems. MPC robust, it's also designed to deal with some kind of uncertainties, like when you have some kind of noise in the system. And then MPC nonlinear, it deals with nonlinear systems. But okay, now you might ask yourself, what are linear and nonlinear systems? Now, when we are talking about systems, remember, we just have some kind of situation. Like in our case, we have a car, right? And then we can also have a drone, we can have a train, we can have an airplane, a rocket, a satellite, an electric system. And all these systems we try to model mathematically. And so when you try to model them, then the mathematical model that you get, it tells you whether the system is linear or nonlinear. So essentially whether your equations that you describe your system with are linear or nonlinear. And so if your equations are nonlinear, then that means that your system is nonlinear. Now, the truth is that almost all systems in the world are nonlinear. And almost all of them, they also have some kind of noise. Now the problem is that, of course, you might think that, okay, then we should use MPC robust and MPC nonlinear, but they are quite difficult algorithms and they are quite heavy computationally, so engineers try to avoid them. They still want to use this easy basic MPC for linear systems, but then most systems are nonlinear. So what we try to do, we try to approximate. So for certain situations, right, you can say that your system is linear for as long as you honor those kind of assumptions that you had made that allow you to describe your system linearly. So for example, if you have this angle example, remember, and then we had some kind of formula here, y dot plus LF times, what was it, it was psi dot divided by small x dots. We made an assumption that, okay, it's gonna be like this, but this assumption is valid for as long as our angle theta stays small. In other words, for as long as our steering wheel angle delta stays small, because this angle is also related to the steering wheel angle. And so the same thing with linear and nonlinear systems. For certain situations, we can, let's say, approximate our nonlinear system and say that, okay, let's describe it in a linear form, and then for this specific situation we can use this basic MPC, okay, this basic algorithm that is easier to implement, but which only works for linear systems. And so we use it, and we keep in mind that we have to honor whatever assumptions that we had made that allowed us to describe our nonlinear system in linear terms. And so to know when your system is linear or nonlinear, well, there are different ways. We're going to use state space equations to know whether our system is linear or nonlinear. So first, let's look at these equations. And I'm going to show you how you will be able to see from the state space equations whether your system is linear or nonlinear. If you look at these equations, let's for now ignore the last one. Let's ignore the big Y. Right? Let's just assume that we have three states. We have y dot, we have psi, and we have psi dot. Three states. Now, how would you put it in the vector matrix form? So you know how to do it with two states, and could you for a second pause the video and try to put these three states and their derivatives in a vector matrix form? So just pause the video for a second and try to do it. Okay, so to put these three states in the state space equation, it would be very easy. You would just have y double dot here, you would have psi dot here, and you would have psi double dot here, right? Equals, so you would have here some kind of matrix, and you would have here your states, and your states would be y dot. Now you would have psi and psi dot, right? And then you would have another vector, and then you would have your input. Now you need to fill in these matrices. Well, it would be like this: A, 0, B. Now here it would be 0, 0, 1, and here you would have C, 0, and D. Do you agree? So here you would put E, 0, F. If you write out this vector matrix form, you will get this form here. Now remember that these are our states, right? But we didn't only care about states. We also cared about outputs, right? So remember, the outputs were the states that we chose from our collection of states that we needed to compare against our reference values. So let's say that because we ignored this big Y, right? So we only have three states right now. For the output, we would only choose psi, the yaw angle. How would you mathematically, let's say, choose your output out of these three states? Well, you create another mathematical equation, and it would be like this. Psi equals, now you will have your states here again, y dot, psi, and psi dot, and then plus, and then actually you would also have something here, another vector, and your input, right? So how would you fill them in? How would you choose your psi here? Well, you would choose it like this: 0, 1, and 0, right? And here you would put 0 here. Now, if we call these matrices A, B, C, and D, and if we say that our states are now X vector, because it is a vector, right? Then how would you rewrite this entire state space equation? Well, you would rewrite it like this: X vector dot equals A X vector plus B delta. And then you would have your psi equals C X vector plus D delta. And this format is the official state space equation format for linear systems. Okay? So that's what you will see in textbooks and you will see in schools. That's the official format of the state space equations for linear systems. And how do you know that they are linear systems? You know that because these matrices are constant. A, B, C, and D. Now, when these four matrices are constant, when they don't change in time at all, right, then they are called linear time invariant systems. It's a linear time invariant system. In other words, if you're able to rewrite your state space equation in this format where you have these four matrices and they are constant, then you have a linear time invariant system. Now, if you would have, let's say, time here, a time variable, right, then that means that your A matrix would change in time. And then you would have to rewrite this entire thing like this: X dot equals A as a function of time and X. And also remember that the states, they're always as a function of time. Okay, so I should have written this thing here. Okay, but I didn't do it. Well, I can do it now to make it complete. And also your system input changes with respect to time because your controller always calculates a new system input every 0.1 second. But now, if you were to add a time variable here, then also your matrix A would change as a function of time. And let's say maybe you also have here some kind of time variable, who knows? And so you would have B as a function of time and your system input. And then your output would be psi equals, and then C, and let's say that it also depends as a function of time. So it would be X as a function of time plus D as a function of time and delta. So if these matrices A, B, C, and D, or even only A, if even only A matrix changes with respect to time and other matrices don't change with respect to time, right, then this system is not anymore called a linear time invariant system. It's called a linear time variant system. So if you think about the name time variant, it means that your system varies in time. So not only your states vary in time, your states and your inputs always vary in time, but now also these matrices vary in time as well. And so then the system is called a linear time variant system. Okay. However, if our matrices become more complicated and I say that c times y dot, right? Then if you write out psi double dot, then what would you get? You would get psi dot equals c times, and now you have y dot here and you have y dot here, so you would have y dot squared plus d psi dot plus f delta, right? So now when you have something like this, then you have a nonlinear system, okay? So in this case you have a nonlinear system, or it doesn't have to be y dot. You could also have, for example, instead of b, you could have b multiplied by sine yaw angle, right? You could have this thing here instead of this, and that would also make the system nonlinear, right? Because your state changes in time, and if your state changes in time and your state is also inside this matrix, then also this matrix will change in time. And so in this case it's a nonlinear system. Now of course you might think that, okay, even when I just had this time variable here, then even then my matrices changed, but I still call them linear. Well, yes, they're still linear, but they're linear time variant. So it's just how we define and how we classify these equations, right? And with each classification, it becomes harder and harder to deal with those equations. So with linear systems, when the matrices are completely constant, it's the easiest way to deal with them. If you have a linear time variant system, then it's a bit harder to deal with them when you design your controller. But then if you have something else, not time here, not purely time, but some kind of state that depends on time, right? Well, then it's even harder to deal with these equations, and so we call them nonlinear equations, and therefore you have a nonlinear system. So it's how we classify things. And so the reason why I've given you this kind of lengthy explanation is because I wanted you to understand this classification. And the thing is that this MPC basic, right, is suited for linear time invariant systems. In other words, if your matrices are not constant, right, if they are not constant, if they change in time, if A, B, C, D, if they change in time, then you cannot really use this MPC basic, and you will have to use, let's say, MPC nonlinear, which is also an algorithm, but it's a more complicated algorithm, harder to implement, needs more computational power, and it's not even guaranteed with nonlinear MPC that you will get the best solution for your steering wheel angle, right? Because remember, the Model Predictive Control tries to give you the best delta, right? But the problem with nonlinear MPC is that you might not get the best delta. I will explain it to you more in the MPC session. But now I just really want you to understand this classification. For now, think that you have three different forms of systems, right? So you have the linear time invariant system, where only your states and inputs change with respect to time, and A, B, C, and D, they are constant. Then linear time variant system, where also your A, B, C, and D matrices depend on time. They are a function of time. And then nonlinear systems, they would also depend on other states. So let's say maybe your matrix depends on y dot and psi, right? And then you have your state, which itself depends on time. And of course your y dot depends on time, and also your psi depends on time, but it's not a direct relationship, right? So they depend on time, but then the matrix A depends on y dot and psi. So the matrix depends on states as well, which also makes the matrices change. And so in this case you would have a nonlinear system. Welcome back. So now that we understand the difference between linear time invariant and linear time variant, and also the nonlinear systems, let's go back to these equations. Do you remember these are the equations that we had derived previously? And here you can see what A, the constant A, what it stood for, and what B stood for, and what E stood for, C, D, and F, right? So these are all the things that we derived from the equations of motion. Now, when we had our two states, only y dot and psi dot at the beginning, before we added the other two states, psi and big Y, so when we had these two states, right, we could say that our constants, A, B, C, D, E, and F, they are all constant. Now, one of the reasons why they're constant, remember when I said that pretty much all systems are nonlinear systems? Well, in our case, that's also true, but we made an approximation and a certain assumption as well. So one assumption was that we had a constant forward velocity, right? So we assumed that when we drive on a straight road and when the car changes the lane, then its longitudinal velocity, small x dot, doesn't change. It stays constant at 20 meters per second. And because of that, we can say that our A, B, C, and D constants, that they don't change in time. And so, thanks to that, we can say that this, let's say, this system, right, with two states, we can say that it's a linear time invariant system. But we can only say that because we assumed that our longitudinal velocity was constant. So when we design our controller, we have to honor that assumption. So meaning that when we apply that controller to a real car that changes a lane, it means that its longitudinal velocity shouldn't change. Of course, it might change a little bit, maybe 0.01% here and there. Maybe it becomes a little bit slower, a little bit bigger, but it doesn't matter. These changes, these small mini changes, you can neglect. But it's important that when you design a controller for that, it's important that when you apply that controller to your car, that essentially your car's longitudinal velocity almost doesn't change. So it might vary a little bit. And so because of that, we were able to say that our constants are constant, and we had a linear time invariant system, which essentially in this case we could use this basic MPC, right? So MPC basic, which was valid for linear time invariant systems. And also remember that we had made another assumption as well, another, let's say, approximation, it would be a better word, an approximation that allowed us to have this linear time invariant system. We said that our tangent theta VF, we approximated it as theta VF. If we had not done it, then we would have had something like theta VF would be tangent, well, arctangent, and then you would have this ratio over there that would calculate your angle. So if we had not made this approximation, then in order to calculate this angle, you would have had to use the arctangent. And then again, your system would be nonlinear. So because of this approximation, we can also say that our system is linear time invariant, which means that our controller when applied to a real car, should also honor the assumption that this angle should be small. So essentially, you should honor the condition that your delta, your steering wheel angle, should be small. Because remember, you had your slip angle equals delta minus theta VF. And so your theta VF would then be delta minus slip angle. So it really means that your delta should be small. It means that for as long as your steering wheel angles don't turn too much, right? For as long as they turn only a little bit to the left or to the right, for as long as you do that, you can assume that your system is linear time invariant, even though in reality it's not, but it's very close to it. And so you can assume that your system is a linear time invariant system, and only in these conditions you can use this most basic MPC algorithm for your controller that is designed for linear time invariant systems. But now in reality we have four states. We have y dot, we have psi, we have psi dot, and then we have the big Y, the global Y coordinates. Now these are our state space equations. Now the question to you is, can we reformulate these four equations in the LTI format? Can we put them in this vector matrix notation like we did it here with these two states? Can we do the same with four states? What do you think? Well, the answer is no, we cannot. And the reason is because of this last line, y dot equals small y dot times cosine psi plus your longitudinal velocity times sine psi. So one problem is that you have one of the states inside the cosine and sine functions, right? So it's very hard to just get them out of it and then separate them and put them in the state vector. So you could try to put them in the linear time invariant format, but you wouldn't be able to succeed right now because, well, we can try it like y double dot psi double dot and y dot equals, okay, you would have your matrix here, your A matrix, right, your state vector. This is your state vector here. You have y dot psi dot and y, and then plus your B matrix, right? So your B matrix would be then E0 F0 and delta. And now here, okay, you could put A 0, you would have B 0, here this would be 0 0 1 like this, and then okay, here you would have C 0 and D and 0. And now how would you do it with this one? Well, you have y dot here, right? You have y dot here, so you could put it here cosine psi. So already this thing makes your system not linear time invariant system. Okay, so and now what about this one? Well, you see you have your psi angle here, right? But I mean, you can't just take it out of the sine function, and this small x dot is just your constant longitudinal velocity, so here is just a constant. And well, you can do it in this way. For example, you can just put 0 here and 0 here, and maybe here you can put, let's say, x dot sine psi, and then you have to divide it by y, right? Because if you write it out, then you would have y dot equals cosine psi times y dot. So that would be okay. And then plus, well, x dot sine psi divided by y times y. Then you would cancel them out, and then you would have this equation here. But it's not a linear time invariant system, okay? So your cosine psi would change, your sine psi would change, and also your y would change, right? So you would have three places where this matrix would change. It would change here, it would change here, and also your y would change. So it's not a linear time invariant matrix, and therefore we can't use our MPC basic algorithm for that. However, we still want to use that because it's easier. And now the good thing is that if you have a straight road, then you can actually use it. So let me show it to you in the next video. Now, if we look at our situation, what is it what we want to achieve here? We have a straight road, and all we want to do, we want to change the lane. We want to autonomously change the lane. We want to go from one lane to another lane, and that's it. And so the car drives longitudinally at a constant longitudinal speed of 20 meters per second, right? And that means that in 7 seconds, if the entire maneuver happens in 7 seconds, then in the global x direction, the distance that the car will travel in 7 seconds will be pretty large, right? So let's say it would be 20 meters per second times 7 seconds. So in total the car will travel in this global x direction approximately 140 meters. Okay, so it's approximately, maybe a little bit less, because at some point the longitudinal velocity will be in this direction, and so you will drive a little bit slower in the global x direction, but it's really small, this difference. But then when we look at the vertical direction, right, then the distance that the car will travel vertically in 7 seconds is actually quite small. Let's say maybe it's maximum 3 meters or 4 meters. I don't know, let's say it's 4 meters, depending on the width of the road. So in 7 seconds, the car travels 140 meters in the x direction and 4 meters in the y direction. Now, what does that tell you? It tells you that the yaw angles that we're talking about are pretty small. So this is 140 and this is 4, right? So the angle would be the yaw angles that we are considering in our situation are actually pretty small. So far when we drew our cars, then okay, I have drawn them like this, and I would say that okay, this is our yaw angle, right? But in reality, in our situation, the actual numbers for the yaw angle would be very small. So that's a good thing, because we can make, for this final line here, for y dot, we can make a small angle approximation. So for example, since we deal with small yaw angles, we can say that, okay, cosine psi. So for small angles, what could we say what it would be? Well, if our cosine function is something like this, right, then at small angles, so this would be yaw angle and this would be cosine yaw angle. Then for small angles, this is 1, for small angles, we could approximate that this is 1, right? And what about the sine angle? What about the sine psi? Well, if we draw it here, a sine function, right, it would be something like this, I guess. So at very small psi angles, just like with the tangent angles, so I'm going to put here sine yaw. So for small psi angles, we can approximate that this could be simply psi, right? So you see that at very small angles, at very small yaw angles, this relationship is kind of linear. So we can make this kind of approximation. And that is very good, because if we honor this assumption and we don't let our yaw angles get big, and let's say that on the screen your road is not horizontally, right? Let's say that instead of this kind of road you have maybe this kind of road. Well, I mean, then you can just, if this road is still straight, then you could take this global reference frame and you could just put it like this, right? So relative to the global reference frame, the yaw angle would still be small, because then you would be measuring your yaw angle from this part, from this point, right? So it's all how you represent your situation. But when we can approximate that our yaw angle is small, then that's really good, because now what we can do, we can take this equation here, y dot, and we can write it like this: small y dot times 1 plus x dot times the yaw angle. So for as long as we keep our yaw angle small, we can write this final equation like this. And now if we can write it like this, then guess what? We can write our entire system in the linear time invariant form. So I have rewritten this system here almost, and now since we were able to make this approximation for very small yaw angles, thanks to this approximation, we are now able to fill in this last row like this. So you have y dot here times 1, so you can put here 1, and then you have your psi here, right, which you have here, and you have your constant term, which is the constant longitudinal velocity, which is your small x dot, right, and 0 and 0, and you put here 0 as well. And so these are your states. And now remember, in the formal state space equation format, you need to have another vector matrix equation as well, which is the output vector matrix equation, where in this case you have two outputs, right? You have your psi, and then you have your big Y as your outputs, because you want to compare your psi and Y against your reference values. So now it would be like this. Your output would be psi and Y. These are the states that you choose, let's say, that you choose from the collection of your states in your state vector, right? And you nominate them to be your outputs, right? And so now your C matrix will be different because you have two outputs. Here you still have your states, y dot, psi, psi dot, and y. And so how would you fill in this matrix? Pause for a second and try to fill in this matrix. Okay, I hope that you've paused and tried it for yourself. Well, it's actually pretty easy. It would be 0 here, 1 here, 0, 0, and here you would have 0, 0, 0, and 1. And that's because if you write out this entire form, then you will get your outputs, right? Because you would have psi equals psi and, well, essentially y equals y, because everything else would be 0. For example, 0 times small y dot would be 0. Now, of course, you have this other matrix as well, like 0 and 0 and delta. And I would say that in most cases, this D matrix, right, in most cases, it's almost always 0. So almost always in real life you can neglect it, but it's still there because in some cases it's not 0. So that's when probably you have some kind of output that is not directly taken from the state vector, but it's some kind of combination that also changes on the input. So, but it's a very rare occasion. Normally the D matrix is 0. And so now what you see is that all your matrices A, B, C, and D, all of them are constant, right? Your A matrix is constant because your longitudinal velocity here is constant. It doesn't change in time. And well, 1 is also 1. And all these A, B, C, and D constants are constant. E and F are constant. Here your C matrix is constant, D is 0. So now your system is a linear time invariant system. It's in the linear time invariant form, and because of that, now we can use this MPC basic algorithm, which we will use and which I will teach you in the next video. So as a recap, what did we do? We had a car, right? We had some kind of car, we had some forces, and well, instead of the car we actually used a bicycle model, right? A bicycle model. And so we had our forces, we then created our equations of motion, we reformulated our equations of motion to have the state space equation, but then we realized that okay, we need more states, so we added psi and big Y, and then we made a series of approximations that we need to honor once we have our controller and once we implement that controller in our car, right? So our controller will really only be valid for a straight road and just for a lane changing operation. So that's why it's called a lateral control. So what we're doing here is lateral control. And the approximations that we had were that okay, our tangent and theta VF, we approximated it to be theta VF, which means that this angle needs to be small, and because of that also your delta needs to be small. So this delta actually, it should be small as well, so your wheels shouldn't oscillate too much. And then we also had an assumption with the constant forward velocity, right? So in real life, okay, maybe it can change a little bit, but not too much, okay? So maybe it's okay if I go from 20 meters per second. If I go plus minus 1 meters per second, but not 10 meters per second. So that was another assumption that we have to honor, and we have to honor the assumption that our yaw angle needs to be small. So this controller wouldn't be valid for roads like this or something like that. So our controller will be valid on a straight road. You drive nicely on your lane, and maybe there is some kind of obstacle here, right? And then you need to change the lane, all right? Or maybe you just want to change the lane because you want to turn to the left or whatever reason it could be. That's what this controller will be for. And so for as long as we honor these assumptions that we made, the constant longitudinal velocity, the small theta angle, and the small yaw angle, for as long as we honor these assumptions, our MPC controller will work just fine. Now, I do want to specify something. Here in this open loop box, we will still use this original state space equation, even with these nonlinear terms, cosine psi and sine psi. Okay? So, these four state space equations that include the nonlinearities will be here, and for these equations we will still apply this algorithm that we had before, alright, where we compute the new states. So this LTI format that we had derived, right, with the constant A matrix, this format will go into the controller. So the controller will work with these matrices, with these A, B, C, and then D matrix. So the controller, the MPC controller, will take in these matrices, alright? So the mathematics in this controller box will be made with these A, B, C, D matrices. But in the open loop section, we will work with these state space equations with the nonlinear terms. So that means that when we calculate our new states, it will be a bit more precise, because here we didn't have this assumption for the small yaw angle. But then for the controller, we will use LTI, because if we use LTI for the controller, then we can use this MPC basic, the easiest MPC algorithm that we can use. And so starting from the next video, we will start deriving this basic MPC controller mathematically, and once we are done with that, then we're gonna code it all, and you're gonna see a simulation and a little bit of animation as well. So thank you very much, and see you in the next video.